Okay, this one it is. By the way, there's probably still the echo problem.
Better?
Still, I think. Is it better? That's weird. Is there an echo? I think so. When I speak like this, the audio just like goes down. Testing, testing. But yeah, so now there's no music. You can't unmute yourself. Which one is you? Chris. Okay. I can't force. Why?
You have to maybe make me co-host.
Oh, you're not co-host. Let me try. Yes. Okay, now it's on YouTube. You can watch it. You can try watching it.
Yes, we should also record it to local disk, but I can do that.
How does that work?
I click on record on this computer.
Okay. It won't run out of disk.
Let me see. I have 300 gigabytes. That should be fine.
Yes.
Okay, then for further organization, we can probably hop on a Slack call.
Interesting. It says the meeting is being recorded by the host or participant. It detects your recording. Oh wait, did you just like click the Zoom recording or?
I did.
Oh, okay. But I think in one of the emails they say they will send us the recording later on if we click on that. Does that save to your local computer?
I save it to my local disk. That's higher
okay.
quality than.
I see. Does that work? Do you want to try stopping it? And
I can stop it. Where does it save those?
I'm gonna turn off my video. Okay, I think it's about time. Andrea, you're muted.
Yeah, hi there. It's my privilege to introduce this workshop. So you are connected to unsupervised 3D learning in the wild. This is a workshop we have intended to promote the research in, well, essentially three things. One is unsupervised learning, and the other one is learning in 3D, or learning the 3D structure of objects. And the third thing is to learn from data in the wild, which I would say is very...
By the way, I think, do you want to share your screen? It's not sharing yet.
Oh, it's not sharing. Okay.
Yes.
I was looking at slides before, but okay. There you go. Can you see that?
Yes, perfect.
Okay, great. And maybe let me just put this in play mode so we can present mode. I think it's this button here. Yeah, okay, great. Yeah, so anyway, without further ado, so we have a great day in front of us. It's a very long day with which is packed with you know, very, very good speakers. You can see here in one slide all the people that are going to speak today. These are the organizers of the workshop. Yeah, so again, this is a workshop about learning from unsupervised data that doesn't have labels, or which could mean no manual labels, but could also be no labels in terms of 3D information, like, for example, recording done with point clouds obtained from a LiDAR, but rather just raw images and videos. And the goal here would be to take this sort of data which is available, for example, on the internet in abundance, and extract from that a 3D-dimensional understanding of the world. Now, this gives you some very exciting experiment, colorful results. You can see here a composition slide where we show some of the cool stuff you're going to probably see today, results from recent papers from the speakers. And you know, it looks very nice. It's a fun area to work with, but it's also, in a certain sense, fundamental and important. So that's, I believe, or we believe, one of the important next step in computer vision to be able to finally break through these kind of problems. All right, so in terms of a program, these are times in the Eastern time. So presumably where ICCV is supposed to be located, except that it, of course, is running virtually. And so we're going to have 3 blocks of talks of 3 talks each. Sorry, 4 blocks of talks of 3 talks each. After each block, we're going to have either a short break or a longer break. We're also going to have panels at the end of at the end of pairs of blocks. During the long break, basically lunch break, there will be an opportunity to talk to each other using a platform that I'm going to discuss in the next slide. So here you can see on a glance the people that are going to speak in which order. But if you want to have more information about the details of the workshop, the talks, the times, and instructions on how to ask questions, you can connect to this URL on GitHub. This is Unsup3D. Again, so you're going to get information about today's schedule, as well as instruction how to watch this. Of course, there is a Zoom channel to which you're probably connected. There should also be a YouTube live stream, which were we able to start that?
Yes, it's live streaming.
Exactly, great. So the workshop will be recorded, so keep that in mind, please. So if you want to type questions for the speaker, you should be using the Zoom channel. All right, that's the primary way you can do that. Of course, you can use that only if you are registered to ICCV. So it is possible to enter questions in the YouTube live stream as well. We'll try to monitor that too, but we cannot guarantee that we'll be able to go through those questions in full. Again, talks will be recorded, so you'll be able to watch them later, particularly for the ones that are not inconvenient time zone for you. And again, so during the long break, we will be able to talk to each other using this platform, which is called Geiger. And maybe, Shangza, do you have some more details about that?
Not yet, unfortunately. The ICCV organizers haven't given us the details on this. We'll try to release it, the details, once we have it.
All right, that's great. So a little bit of last-minute excitement. We are going to update the information on the website, and of course, during the breaks, we're going to tell you if we have news on this. All right, now I think that's enough chit-chat. So going back to our list of talks, the first one to be speaking is Tali. So are you? Oh yeah, here you are. So please, the stage is yours.
Okay, I'll give a little bit short introduction for Tali. She's an amazing researcher, and she's currently a assistant professor in the Department of Math and Computer Science in the Weizmann Institute of Science. And he was a research scientist. He's also a research scientist at the moment at Google as well, I think. And she's done amazing work on image and video analysis and multi-view reconstruction, 3D structure from motion, etc. And including the best paper award at the ICCV21, the Singan, and the Mannequin Challenge, which won the best paper honorable mention award at CVPR 2019. So Tali, please take over and show us the latest work. I think you're muted.
Yes.
Oh. Okay.
Hi everyone. Very excited to be here, and thanks for the introduction. So I know this workshop focuses on kind of learning 3D in the wild, but this is such a challenging topic. So instead, I'm going to talk about a 2D method, and more specifically about layered neural representations for videos. So recently I've been very interested in how can we analyze and re-render casual everyday videos. So this is a sample of my own personal video collections. Most of these videos are of my children, and I take many of these videos and I care about them, but I hardly watch them because even for me, those videos are kind of boring. So I was looking for ways to make these videos much more engaging, artistic, creative, and more generally, looking for ways to enhance the way we can perceive our dynamic world through everyday videos. So just to give a few examples, Here is the video where we told the children to jump to the pool together, but of course, each child jumps at a different time, as you can see here. So what I'm going to show you next is a result produced computationally and automatically, in which we go into the video and retime the motions of the children such that they all jump to the pool together. So here is the result. And now notice how not only the children are retimed, but also all the scene elements that are related to them. The water splashes, the reflection in the water, all these complex scene elements are nicely following the children in the retimed result. So going into the video and changing the actions and the moments that actions occur in the video is one way that we can perceive the way we can enhance the way we perceive kind of like actions in a video. So here is another example. Oh, got stuck. Sorry. Slides get stuck. Here is another example where we take this ordinary video of a horse jump and we can produce this stroboscopic video where, again, you can see that not only the horse is being duplicated, but also the shadow is nicely casted on the ground. Another useful application is removing objects from video. So here we have a bunch of children jumping, causing deformation to the trampoline, and we can remove all the people except once. And again, we can remove those people along with the deformation effects that they generate in the scene. And finally, this is a final example where we take this video and we want to map objects or map texture onto object in this video. And we want everything to continue to move in a coherent way. And also you can see that the shadow here is casted on the bench, the colored bench, in a realistic manner. So all these video editing effects were produced by different methods from the past couple of years. At the heart of this method, there is a decomposition of the video into layers, but each kind of like work focuses on a different aspect of the decomposition. And today I'm going to tell you a bit about OmniMatch from last CVPR, and then I'm going to tell you about the new work, the layered neural atlases that will appear at SIGGRAPH Asia this year. Okay, so let's jump into it. And OmniMatch is a joint work with Erica Liu, Forrester Cole, Mickey Rubinstein, Andrew Zisserman, and Bill Freeman from Google. And let's think for a second what is required in order to produce all these effects that I showed you. Obviously, we need to segment out the objects, but it's not enough. We also must take into account all the scene elements that this object generates in the scene. And actually, computer vision became really good at segmenting objects. So what you can see here is a result of a state-of-the-art, segmenter, mascar CNN on this complex video. So it works fairly nicely. But if we take those masks and plug them into kind of like a state-of-the-art object removal method, this is the result we get. So we end up with all these kind of like visual artifacts because we didn't model, we didn't take into account the deformation of the trampoline in this example. So video editing and the applications that I just showed you give rise to these novel research questions of how can we associate objects in video with their scene effects. And that led us to define a new problem, the OmniMatch problem. So this is the setup. We have an ordinary video along with rough masks for each object of interest. You can compute those masks using off-the-shelf tools like mascar CNN. And the goal is to produce an RGBA layer for each object. And those layers not only contain the object, but also all the scene elements that are correlated with them in the video. So for example, shadows, reflections, smoke, etc. We also have one separate layer for the background. And of course, the task of decomposing a video into layers is not new. The pioneering work by Wang and Edelson inspired a great body of follow-up work. And modern approaches, of course, use the power of deep learning. So for example, in stereo magnification, you take a narrow baseline stereo pair, and they basically learn a layered representation that corresponds to physical depth layer. And then they can generate like wider baseline views of the scene from this layered representation. In our case, we are also using the power of deep learning, but our layers are not meant to be strictly accurate in terms of depth. Our layers meant to capture an object along with all the effects that they generate in the scene. And our model is trained on a single video without observing any additional examples in a self-supervised manner. And the main driving loss that drives this whole system is a reconstruction loss. We want the layers, when we put them back together, to allow us to reconstruct the original video frames, as you can see here. So let's dive more into the details. We're given a video, and for each frame of the video, we have these rough object masks that we computed. We also pre-compute optical flow between consecutive frames using, for example, Raft. And we have our OmniMat model. We take, so a mask and an optical flow form the input for a given layer, and we input those input layers into the OmniMat model in a separate forward pass, as you can see here. The OmniMat model produces outputs an RGBA layer and also a refined flow layer. So optical flow layer here is just an auxiliary task that allows us to inject kind of like motion information into the model. For the background, we also have a separate background layer, and we assume that the background is static, and the motion of the background can be well approximated using homographies. So that means we can register all the frames into a common coordinate system. And in practice, we just have a single background layer for the entire video. The input is just a fixed noise image, as you can see here. And the output is the unwrapped background canvas for the full video. So in order to get the background layer for a specific frame, we just need to sample this background layer using the pre-computed homographies. You can see the paper for more details, and even if you didn't get all the technical details here, it's not so important. What is important to get is that we model only a static background and the objects. And this model is required to faithfully reconstruct the entire video. And in order to do a good job, it must also reconstruct all these time-varying scene elements, like this shadow on the ground here. But these elements are not given to the model as input by any manner. So the model is required to infer reflections, shadows, and all these complex scene effects automatically. Okay, and now the key question is, how does this model manage to place the effect in the correct layer, right? How does it manage to associate the effects with the object causing them? So I'm gonna give like a very kind of like brief and intuitive explanation to make this point. Okay, so recall that this network is overfitted to this single video. So basically it has to memorize this shadow given the inputs that we provide. Recall also that we assumed that the background is static. So the network cannot place this shadow in the background layer. It must place it in the object layer. So it has the option of predicting this shadow from the person's input, the person's mask and flow, or it can predict it from the dog's input. And it has to do it consistently over the entire video. And if we take a look of this task over the entire video, what we can see is that obviously there is very high correlation between the person's input, the mask and optical flow, and the shadow. We can tell a lot about the shadow by knowing the mask of the persons and the optical flow. On the other hand, the dog doesn't tell us much about the person's shadow. So it's a much more difficult task for the network to predict the person's shadow from the dog's input. So in short, the shadow can be learned quicker and in fewer iterations from the person's input, and that's the solution that the network favors. So this is also, very much related to the observation made in the deep image prior work, if you're familiar with that, where they show that if you take a CNN model that is trained and you fit it from scratch to an image, it's a much easier task for the model to fit a natural image than a random noise. So for natural images, there is high correlation between image patches, and it takes fewer iterations for a CNN to learn to kind of like reconstruct a natural image. than random noise. In our case, the effects that are closely correlated with an object in space, in time, or in both are learned quicker and in fewer iterations than other effects that might be noise with respect to that input. Now, this is only kind of like a very intuitive and a brief explanation. We have a more in-depth analysis in our SIGGRAPH Asia 20 paper, so please check it out for more if you want to know more about how it works. So just to conclude kind of like the losses that we use. So as I mentioned, the main driving loss is a reconstruction loss. We want the layers when we put them back together to allow us to reconstruct the original video frame. We also have a regularization on our alpha mets. We want them to be sparse. And this is a combination of an L0 and L1 loss on the alpha mets. And it turns out that these two losses alone are not enough to make the optimization converge from a random initialization. So we also have an initialization loss in which we encourage the mask of each layer to match kind of like the rough segmentation mask that we use as input. We turn off this loss after several epochs and let the network refine this initial estimate. Finally, we have two additional losses that incorporate the flow. One is a temporal consistency loss, and the other is kind of like flow reconstruction loss, which is similar to the RGB losses. Okay, so let's see a few examples. Here you can see results from Davis. You can see on the left the original video, then the input mask that we use as input, our OmniMat prediction, the RGBA layers for both the foreground and the background. So you can see here how we manage in the Black Swan example to pick up all those complex reflections in the water and also very fine details of the swan. In the second example, we're able to pick up the dust that this elephant throws, and you can see kind of like the delta from the input mask. And here in the last example, you can see how we capture the shadows that does not appear in the input mask, the original input mask. So overall, you know, if you take a very close look, you can start to notice a few artifacts. Like for example, in the black swan, you can see a little piece of the swan in the background, because the model never observed the content behind that region, and so it doesn't have a good guess how to paint this. But overall, kind of like the results are, you know, we are able to apply this method on a really diverse set of objects and across categories and capture those semi-transparent complex effects. And now that if you have those layers in hand, you can do all sorts of kind of like, you know, video effects. So here, for example, we can do color pop. We can keep in color only the flamingo and its effects, and the rest is left in grayscale. So here is the result. Sorry for the lagging in the videos. This, I guess, Zoom challenging me. So please check out the videos also offline later. This is a real application where we were asked by a team to take this video and place a logo behind the car on the ground. So we used our OmniMat to separate the video into background and foreground layers, and we were able to separate out the smoke and place the logo right below it. And here you can see kind of like the RGBA layer for that video. And, you know, just imagine to do this in Photoshop. This is really, really challenging. Okay, so I guess OmniMats are great for associating objects and their effects in video, but one disadvantage of this representation is that it is a per frame representation, meaning we take the video and for each frame I have an RGBA layer. But you know, the editing is kind of like restricted to per frame manipulation. I don't have a good way of propagating information across time here. So in this work, like a new work, which in neural atlases, our goal was to tackle this challenge. Here, the idea is as follows. We want to take exactly the same input like the original video, just a casual video, but now we want to break it not into per frame RGB layers, but instead we want to have per video atlases, 2D atlases layers. And this provides us with a unified representation of the video that will allow us to easily and intuitively edit the video across time, as I'll show. This is a new work, a joint work with Yoni Kasten, Dolevo Free, and Oliver Wang, and it will be presented at SIGGRAPH Asia this year. So again, the idea is that we want to take an input video and break and decompose it and unwrap it into these 2D atlases. So you can think of these 2D atlases as texture map, only that we don't have a 3D model of these objects behind the scenes, right? Like you might have like in dense pose. Here, everything is 2D. And you know, imagine like what it would be very challenging to have like a very accurate 3D model of this swinging dress. So instead, what we do here is our method not only estimates these 2D atlases, it also directly estimates a mapping from each video position onto this set of 2D atlases. And what this allows us is to basically apply any editing that we want directly on these 2D atlases, like we can color the bench or add those flowers onto the dress. And then using the mapping, we can consistently map them back into the video, to the original video. So all that was required to produce these results is editing 2 images. That's it, 2 texture maps. And of course, this idea of unwrapping a video into kind of like a unified texture map is actually not new. Our work is inspired by the unwrap mosaic methods from 2008. But you know, this was before the deep learning area, and it was a very complex and very sensitive system, and that has several kind of like drawbacks that we actually try to tackle in our work. So one problem with the unwrap mosaic is that it assumes an input and accurate segmentation mask for the object. It doesn't refine the mask, it doesn't solve for decomposition, whereas our method solves for a layer decomposition. Like in OmniMat, we only use the segmentation mask as initialization, and then we refine them together with the rest of the unknowns that we estimate. Another problem with the unwrap mosaic is that it relies on very long point tracking in the video, which is super challenging. In our case, we only use pairwise optical flow and only use it as a soft constraint. Finally, they have kind of like a discrete atlas. They have to set the resolution in advance, and we leverage continuous atlases via coordinate-based MLPs. Okay, so in more details, given a video, each pixel position x, y, t is first mapped onto these 2D coordinates in the atlas space. So these are just like values between -1 and 1 that tells us, you know, for each position, where does it map to in the atlas. These estimated 2D points are then fed into another Atlas MLP network that predicts the corresponding RGB color at that Atlas location. So what you are seeing here is just kind of like a rendering or a visualization of this continuous atlas when we render it into a discrete image. Each atlas position also goes into an alpha MLP that produces an opacity value that tells, you know, at this pixel position, how much is observed from each atlas layer. And this allows us to basically reconstruct the color at video position P just using alpha blending. And this essentially allows us to reconstruct the original video and to train this whole thing end to end, mainly relying on a reconstruction loss as we did in OmniMat. Now recall that our goal here is, you know, to edit the video. So we want to produce atlases that will be interpretable and that will preserve the video content and that will have several properties. So reconstruction alone is not enough. We have several loss terms in our objective function, and I will briefly explain each one of them, okay? So as I mentioned, the main loss is a reconstruction loss. We just want, you know, this representation to allow us to get back the original video content. So this is just a simple L2 loss between the original colors of the video and the predicted ones. The second term is a rigidity loss. Our goal is, again, to get interpretable atlases. So we want the content in the atlases to preserve as much as possible the original structure in the videos. So we achieve this by encouraging the mapping between a video frame onto the atlas to be locally rigid. And without this loss, you can see that the atlases are kind of like all very much distorted, and they all collapse maybe into a very small region in this kind of like continuous atlas space. So the rigidity loss prevents this. We have an additional loss that is based on optical flow. So ideally, what we wanted to achieve is that, you know, each point in the atlas domain will correspond to a physical point in the world. And again, we don't have any 3D information. So our way to kind of like encourage that is through 2D optical flow. What we want 2 points when the 2 corresponding points to be mapped to the same point in the atlas space. So this loss encouraged that using a pre-computed optical flow. So here you can see the results when without this loss. So surprisingly, I was surprised to see that it's not like the model completely breaks. It still managed to do the composition nicely and still managed here to get a nice foreground atlas layer. But you can see, you know, some artifacts and objects that break in the background on the right here, and the optical flow prevents that. The problem is that we don't have optical flow for all the pixels in the video. Some pixels won't have kind of like valid optical flow. And in order to kind of like prevent duplication in the atlas domain and deal with those points where we don't have supervision for, we also have a sparsity loss that encourages a minimal alpha atlas. So without this loss, you can see that we might get kind of like duplication, like we get 2 motorbikes here in this example, and the sparsity loss will encourage kind of like a minimal atlas. Okay, so just to recap, our losses are kind of like, we want to reconstruct the original video. We want to preserve the original structure in the atlas. We want corresponding points to be mapped to the same atlas point. Finally, we also want the atlas to be minimal as possible. And with our full model, we are able to get the composition for that video. We also have an alpha initialization stage where we can get kind of like a very rough mask. So, you know, for some object category, mask RCNN might not work like here. So actually we experiment with that, and the model works well also with very rough user mask like you can see here, and it refines them during kind of like the optimization. So let's see some more results. Here is an input video. You know, there is quite a bit kind of like of motion in the background here. And here you can see the foreground and background atlases that our model produces. You can see some distortion in the car, but again, locally, everything remains rigid and allow us to apply all sorts of editing. So here you can see kind of like also the reconstructed video, the RGB foreground layer, which you can see that capture also the shadow and reflections. And you can see also an example where we map a texture onto this car on the top right. Is an even more challenging example that has like, you know, very severe parallax and complex non-rigid motions. And here is the composition for the foreground and background atlas. And again, you can see the reconstruction, the RGBA layer, and the texture mapped onto this object. And this is, again, a super challenging example. So as I mentioned, like with respect to the unwrapped mosaic, we are using a continuous representation of the atlases and mapping. And in order to show the advantage of that, we did a small ablation where we just replaced the continuous atlas with a discrete atlas. You have an image, and the pixel of that image is the unknown. And now we just want to solve the same objective function. Everything is the same, just replacing the MLP atlas with this discrete image. And this is the result you get for this dog video. And you can see that the composition really breaks. So actually you can get like, even with kind of like this really bad decomposition, you could get a pretty okay-ish reconstruction. but the decomposition is meaningless, and you won't be able to do much with these atlases, as you can see here. So the fact that we're working in a continuous domain allows the model to be much more flexible. You don't need to set the resolution in advance, and the model could give a different budget to different kind of like region in the atlas as it needs to. Okay, so let's see some cool stuff that we can do with that. So this is a video. Again, sorry, this is again my son. And this is the foreground and background atlases. And to do editing, what we do, we just render those atlases into images, and then we can just plug it into any editing tool that we want. So for example, we can just, apply existing image style transfer on this texture image, and then map this stylized background atlas back to the video domain using our mapping and get this result. And again, all we have to do is just kind of like edit a single image, and it automatically propagates continuously in time to the video. We can do this to this black swan example, this time for the foreground object, just by applying some Photoshop filter. And you can see how, because we are solving for the decomposition, we are able to also edit the reflection in the water, not just the swan itself. As I mentioned, we can map texture onto objects. So in this complex video, what I just did, I just kind of like laid out some stars and this pinkish line on this, the white region in the background atlas. And then we're able to basically map those stars. The stars will deform with the wave, and they will settle down once the waves is gone in the video. So regarding limitations of this approach, because we have these rigidity constraints that we apply to the video, it will be kind of like challenging to represent very complex geometry and self-occlusion and extreme deformation with a single foreground layers. Like in this example, this is a super challenging example, and you can see that our foreground atlas doesn't represent reliably the full body parts. And in this case, we need to break the object layer, the foreground layer, into multiple foreground layers to reliably kind of like represent this. But still, you can see that even in this example, the predicted alpha and the background atlas are quite of good quality. So in fact, we are still able to edit this video by, let's say we can just add this graffiti on the ground and this scribble on the wall, and get this as a result and map them back to the video. So though we didn't manage to fully kind of like represent the persons and we cannot edit the person here, the result is still useful. Okay, so I think with that, I'd like to end. I just want to acknowledge again all the wonderful people I got lucky to work with on all these different projects. And just to conclude, I guess each of those works kind of like reveal the different aspects of layered decompositions of videos. I think this is a really exciting topic that allowed me at least to be much more creative and fun with my own personal videos, and also kind of like, raises a fundamental question of, how to represent temporal content in everyday videos in a meaningful way. So with that, I'd like to end there. I can probably take a few questions. So thank you all.
Yeah, thank you very much. It's those are really, really cool results. I really love all those editing effects. I do have a question here. Of course, participants, feel free to type the questions in the chat, and we'll ask the speakers as well. So how much 3D do you think you can extract from these representations, like atlases, or from the Omnimat? I guess with the alpha maps, there might be some information about the 3D layout.
Yeah, so I think for Omnimat, it's less obvious to me that you would be able to easily extract 3D. I think the neural atlases it's 2.5D, right? It's a representation that has this kind of unified representation, like each point of the atlas is mapped back to the video, and you can start imagining that, you know, you can track a point throughout the video, and perhaps that could give you a lot of prior about, like, you know, how to extract its 3D information. Because or you can start thinking of really integrating kind of like a 3D model in the loop together with these 2D atlases, like making the whole thing a real 3D model. So an example is dense pose, right? Like you can imagine that you could solve for this UV mapping, but maybe you also want to solve for a mesh that will tell you that where each point is kind of like located in 3D. I think it will be a challenging, but I think it should be possible.
Awesome. Yeah. I think like all the results, like it might be really possible. Like if you have all these light atlases, it might be possible to visualize them like from another viewpoint somehow if you project them onto 3D.
Yeah.
Amazing.
Should I take some question from the chat then?
Yes. So there is a question that is what would happen to the layer decomposition if the camera movement is very large?
So in which work? So I guess in the OmniMat, we did assume a static background and we also assume that, you know, you can well approximate the camera motion using homography. So I guess in that case, the model will struggle if you cannot do that, because we won't be able to register all the frame into a single coordinate system. In our neural atlases, we don't have this assumption. So we can deal with arbitrary camera motion. And I think we've seen one, like in the Libby example, the camera motion is pretty fast and it has a lot of parallax. So I think, again, like to deal with really correctly, like parallax, you might want to break things into kind of like really depth layers and do this correctly. But for these types of videos, the model was able to handle them quite nicely.
Cool. There's also another question, which is like, could we use this atlas for advanced like video compression?
Yeah, so I think there is this classical work called video epitomes. I don't know if you guys you know, familiar or remember this work. So I think there it's quite similar. They have this mapping onto this kind of like a minimal map. But I guess our focus was to have atlases that are interpretable and that we can edit. I think that for compression, you can drop this assumption. Yeah, and this requirement, and you can think of like maybe you can compress a video in a way that, you know, that will collapse everything into a very small region in the continuous space. But I think it's an interesting direction. I think the requirement, the objective requirement, would be different in this case.
Cool. One last question, which is what is the computational cost of these models as it takes to like overfit on one single video?
Yeah, so I guess it changes. So for OmniMat, it changes, you know, according to the number of layers and the number of frames. Also for our neural rendering, and it depends on you know, your GPU power and so on. I think it took a couple of hours, several hours on a single video that had, I don't know, multiple, like standard Davis video, probably on 2P100. We have all these details in the paper. I can't recall the exact numbers right now, but it's not a super fast method yet. Hopefully it will get there at some point.
Awesome. I think that's all the questions. Thank you very much, Tali. Thanks for joining us.
Thank you so much for inviting me. It was great to be here. Thanks.
Great. So now next speaker is Andreas Geiger.
Hello.
Hey. You can start sharing your screen. So for a brief introduction for Andreas, he's a professor at the Autonomous Vision Group at the University of Tübingen and MPI for Intelligent Systems. He's done a really amazing work on 3D scene understanding, reconstruction, motion estimation, especially like including like generative models. One of the best paper awards for no, not the only one best paper award for CPR 2021, which is Giraffe, is really like outstanding work in this area. And he was also the recipient of the PAMI Young Researcher Award and many other awards at 3DV Best Paper Award, creator of the Kitty dataset. That's also like really large impact in the community. Okay, so Andreas, you can take over and start your talk.
Great, thanks a lot for the nice words and welcome everyone. Giraffe is what I'm going to talk about today, amongst others. I'm going to talk about generative neural scene representations for 3D aware image synthesis. So maybe what was already alluded to in the previous talk, we are trying to go here in this talk more towards unsupervised 3D representations. And in particular, I'd like to talk about these three works here that are in line and build upon each other. The first that we did was called Graph, Generative Radiance Fields. The second, Giraffe at the CVPR. And then very new, Campari, just accepted to 3DV. And these are my amazing collaborators. Michael Niemeyer, who did a lot of the work behind Giraffe. Katja Schwarz was the main author on Graph, and my former postdoc. Let's get started. As we all know, generative models are fantastic, no? So how do they work? In a nutshell, sample a latent code from the prior distribution. And then we have a nonlinear function, a generator G with some parameters theta, a neural network that takes that normally distributed latent code and then generates a more complex distribution, in this case an image distribution. This is an example from StyleGAN. It's really amazing what these models are able to do. This is a real example from StyleGAN 2. Here's another example from StyleGAN 2. And here is yet another example from StyleGAN 2. So we can sample more and more latent codes to get different generated images. But I want to pose this question here. Is generating photorealistic images all we need? Or do we desire something more? And I would argue that for many applications, we require control. In particular, we require control over many aspects of the image generation process. Think about animation movies. If you want to generate, if you want to synthesize scenes like this with little human effort, then you need to be able to generate individual assets, but then control them in the scene. Or video games. Video games is another great example where you want to have full control. You want to control the environment, the state, and as the game engine, but then also you want to hand over some of this control to the player. So you need to be able to modify the image content. And of course, also virtual reality is another example for this. So what we are looking for, what we were after in this line of research, is to build a generative model that is 3D aware and that can do 3D aware image synthesis. And in particular, this model should allow us to do the following. It should allow us to generate photorealistic images, control individual objects with respect to intrinsic properties, for example, their appearance, pose, and size in 3D. These are 3D properties, not 2D properties. And then also control, of course, the camera viewpoint in 3D. And what is making this problem really hard is, as we phrase it, is that we want to train this from unstructured and unposed image collections. So we want to use as little prior knowledge as possible, just a collection of images from a specific object category, for example. The first question that we have to answer here is, what representation should we use for 3D aware image synthesis? So in the past, different representations have been tried. For example, Platonic GAN uses a voxel-based 3D shape representation and a volume rendering step here. So latent code generates a 3D object in terms of a volumetric voxel-based representation that's then rendered into an image. The advantage of doing that is that it's multi-view consistent by design. You generate a 3D object and you render that 3D object. So whatever you generate, it will look consistent across the different viewpoints. But this approach, at least this early approach, doesn't lead to very high image fidelity. As you can see here, this is the image that has been generated from this approach and has relatively high memory consumption because voxels don't scale so well. Another approach called Hologun uses a voxel-based 3D latent feature representation with a learnable projection. The idea here is to sample the latent code and to generate a feature volume, and then to render that feature volume with a neural renderer into an RGB image. Now this allows for higher image fidelity, as you can see here, but the object shape and identity now vary with the viewpoint due to this learnable projection, because this learnable projection in a sense makes this 3D consistent representation 3D inconsistent again. So if you render from different viewpoints, the object identity or shape might change. And if you try to reconstruct then, for example, using CallMap, you don't get a very nice reconstruction from that. So what we proposed in, this was in NeRFs 2020, is graph, a model called graph, generative radiance fields. And the idea here is to build upon NeRF, the NeRF representation, the neural radiance field representation that takes a viewing direction and a location as input and maps that to color and a density value and uses a non-trainable volumetric rendering step to render an image, to use that representation for in a generative setting, in a GAN setting, where we sample a latent code, we condition on that latent code, and then we render an image based on this conditioning. And this is an example of our graph method. And you can see that because we have no parameters here in this rendering step, that we obtain a consistent 3D reconstruction if we take these images, a couple of images from different viewpoints rendered from this model and try to reconstruct that again. So we have a continuous representation that's multi-view consistent, leads to relatively high image fidelity, at least on these very simple data sets that we applied it to. It doesn't yet work on very complex scenes, but on this kind of data set it works. And has low memory consumption because we're using this very compact radiance, neural radiance representation where this mapping is represented through a neural network. So let's look at this model in a little bit more detail. What we do first is we sample the camera matrix. These are the camera intrinsics, the camera pose. These are the camera these are the camera intrinsics. These are the camera extrinsics, and a patch sampling pattern. A pattern along which we want to compute the appearance. We do this because it's intractable to render entire images with this NeRF representation, as this is very time and memory. It takes a lot of time and memory. So we just render a patch that we sample randomly from the virtual camera. And then we have a patch generator and a patch discriminator, similar to a patch GAN. So here's an example. This is from this virtual camera where we sample this, in this case, 5x5 patch pattern in a 5x5 pixel pattern. In reality, what we do is we have a 32x32 pattern. So then we pass these parameters to the generator, which samples the corresponding pixels and rays. And then for each of the pixels, or a pixel and a ray is the same thing here, right? So for each of these pixels or rays, we can sample 3D points along the ray, as in the neural radiance field approach, which we need for volumetric rendering the image. So we sample the space along these rays. And then we pass this through through a positional encoding, the view direction and the 3D point, and use it as an input to what we call the conditional radiance field. And this is a conditional radiance field because it's also conditioned on a latent shape and appearance code, illustrated here, that are sampled from latent low-dimensional Gaussian distributions. So we condition on the shape and appearance as well. And the output of this conditional radiance field is then the color and the density for each of these points along each of these rays in the pattern. And then we apply volume rendering, which is basically just doing alpha composition on these points in order to render the pixel colors for this particular patch that we have sampled. And this is what we call the predicted patch P dash. Now we want to compare this patch to real patches. So what we do is we take real images and we sample real patches using the same patch sampling procedure, that we get a patch of the same size. Also 5x5 or in practice 32x32. And because now we have a very standardized patch size, we can use a very shallow and standard 2D confident discriminator to compare these two with respect to each other. And of course, what we do in practice is we sample these patches randomly. So we sample the dilation factor here randomly. We sample also the location and the scale randomly, so that all areas of all regions in the 3D space and all areas of the image are eventually covered over time, stochastically. Okay, so yeah, the key idea to summarize is that we have a generator and a discriminator for image patches. The generator has a non-trainable deterministic volume rendering component, but a trainable conditional radiance field. And these patches are sampled at random locations and with random scales using random dilations. Let's have a brief look into the architecture. So this is this little orange block that we are looking inside now, this conditional radiance field. We have a fully connected MLP similar to NeRF, where we input first the 3D location and the shape code. So at the very beginning, we insert the shape code, but the appearance code CA and the view direction D influence only the output color. So here we're encoding this into a latent code H, and then we are branching out to a density head and then to a color head. And only the color head is influenced by the viewing direction and the appearance code. And this allows us, this inductive bias allows us basically to disentangle the shape and the appearance. So we have multiple inductive biases in the model. One inductive bias is this here. The other inductive bias is, of course, that we force the entire image generation process to go through 3D space. These are the main two biases that we are using here. So let's look at some results. These are some results of graph on the synthetic Kala generated cars data set. But again, this data is generated without providing to the method any information about the depth or the viewpoint. What the method sees is only a random collection of images, of rendered images. And as you can see, it can then synthesize novel cars with novel shapes and appearances decently well on this simple data set. We can modify also the shape and the appearance. And we also get automatically the geometry here rendered as a false color coded depth map, despite the input to this method is only RGB images. Here's another example, and this is on real data on the Celeb A dataset at also 256 times 256 pixel resolution. And again, here we get the corresponding depth map out of our learned model. The next thing we wondered as well, how can we scale this idea to more complex multi-object scenes? And this is where we started working on Giraffe, which is this CVPR21 paper. In Graph, we incorporate a 3D representation as an inductive bias into the generative model, as we have seen. What we do now in Giraffe is that we incorporate a compositional 3D scene representation into the generative model. The difference is that now we have a compositional model. And again, we want to train this in an unsupervised fashion from an unstructured, unposed image data set. So the data set doesn't change, only the model changes. And what we do in addition is we incorporate a neural renderer to yield fast and high quality inference, which means we are giving a little bit up on 3D consistency here now. We have a trainable rendering part, but the advantage is that we can train much, much faster this model and get better results, at least in terms of FID scores. So let's walk us through this model. The first thing we do is we sample N shape and appearance codes, where N means the number of objects in the scene and the background. So N is the number of objects plus the background. And also we sample this randomly. So depending on how many objects we expect, but over a random set. Then we, for each of these objects or the background here at the bottom, we obtain, we generate a so-called feature field. In contrast to graph, we don't directly generate with our multi-layer perceptron the color value, but we generate a higher dimensional feature representation continuously in 3D space. And the advantage of this is that when we render this, we can render this to smaller resolution. And the rendering is the slow part, so we can have faster rendering. And then we have a 2D, still a 2D convolutional rendering step that upscales this feature map then to a higher resolution image. As a note here, what we show is RGB colors. So this might be a bit confusing, but it's just easier to visualize the colors rather than the features. So what you see here is colors, but what you need to think is features. So these are the sampled feature fields. Then we sample also the size and the pose of each of these feature fields. So you can see this little bounding box. So we have a local coordinate system and we sample the pose and the size of each of those to stage them in the scene, indicated here by this little square at the bottom. So we have the background staged and we have all the objects in the scene staged now. And then we composite them together. We composite all feature fields into a single 3D scene representation and then sample a camera pose. Let's say this is our sampled camera pose. And then we perform volume rendering in order to get a low resolution feature image. And then we have this bespoken 2D decoder that upsamples this feature image. Here we are still in the feature space, not in the RGB space. But then we upsample this and output the final RGB color image. And at test time, we can then sample individual codes. So illustrated here, we can draw random samples from these distributions to control the shape, appearance, and pose of each of the object and the background. Just to highlight again, the key here is that we volume render the feature image at a smaller resolution and then upsample via the decoder to make this tractable and fast. Unlike graph, we can then directly train with an adversarial loss at full resolution. So we don't need a patch-based discriminator anymore, but we can directly train with the full resolution images. This is the architecture of Giraffe. It's of the conditional part. This is almost the same as graph. The only thing that has changed is the feature head, right? So before we had a color head, now we have a feature head. We're outputting not 3 values here, but a higher dimensional feature vector. That's everything that has changed inside this conditional radiance field. And then the scene composition is rather simple. Just to go back, so we need to composite these objects together, right? So how do we do that? Well, we have n feature fields that each produce a density and a value and a feature vector. And then we combine the densities simply by summation and the features by density weighted averaging. So we just compute a weighted average and sum the densities of the individual objects in order to obtain the final density. Okay, so this is everything about the method. Let's look at some results. The first result is a comparison in terms of object translation for a 2D-based GAN and our approach on the right. As you can see here on the left, the 2D GAN is not able to disentangle translation or position and appearance entirely. As you translate objects, for example here, the shape and the size and also the appearance of the object often changes. So it's just hard to do this without this inductive bias of going explicitly through 3D and disentangle the objects into different objects, disentangle the scene into different objects. On the right, however, you can see that we can individually now stage the scene because we have individual object representations available. And so they are consistent. We can also do more complex operations like circular translations, as shown here, which is impossible. So we can't get that level of control with a traditional GAN. We can also add more objects at test time than we had available during training time. This is an example where we trained on 2 object scenes, but then at test time we staged the scene with more objects in it. And we can also rotate the object. Here's an example on a car data set. You can see that it's a little bit overfitting to the canonical poses because the data set is very biased. It has a lot of observations from front and back and side, but less from intermediate angles. And we can translate the object. And we can change the object shape. So here on the left, the shape of the car. On the right, the shape of churches in this example. And we can change the object appearance. We can even generate out of distribution samples. So what you see here is samples where the car is translated more than it was translated in the original data set. Or we can add additional cars into the scene, that more cars than were present in the original data set. Here's a little comparison of the rendering time to illustrate, highlight the difference between this low resolution feature rendering and then upsampling compared to directly rendering the RGB image with a neural radiance field representation. You can see that it has a big impact. In particular, if you go to larger resolutions, you get a quite significant speed up with that. Now, finally, the last project I want to briefly show to you is how can we extend this to learning also the camera distribution. What I didn't tell you so far is that in Graph and Giraffe and all the works that appeared at the same time with a similar goal required very careful tuning of the camera pose distributions. So given the data set, you first looked at the data set and then you were trying to figure out what is a reasonable distance of the camera and focal length, and what is a reasonable elevation angle of the camera. And then you picked some distributions that capture that precisely, because if you don't do that, the generation will just break. It will not learn anything meaningful anymore. So what we tried to do in this project is to lift this restriction by learning a 3D aware image generator and a camera generator jointly. And it turns out that this actually works. So what we do now is we sample a prior camera from a very generic uniform prior distribution, where this camera is parameterized through its intrinsics. We use the focal length in X and Y direction and the extrinsics. We assume the camera is on a sphere at a certain distance to the center, is looking at the center, and at a certain elevation and azimuth angle. So we start with a uniform distribution over all of these. We sample this Xi prior from this uniform distribution. And then we have a camera generator. This is again a nonlinear function implemented as a neural network that maps this quite uniform distribution to a nonlinear multimodal distribution, Xi prediction. And then we feed this into the 3D aware image generator. In this case, we have a model that treats foreground and background separately, but we don't model more than one object, more than one foreground object in this case. And then we have a standard discriminator, a standard adversarial objective similar to Graph and Giraffe. So here I want to show you some results. What you see here is a histogram or distribution plot over the elevation angle on the x-axis. This is one of the camera parameters now, a one-dimensional space illustrated here. And we can see that starting from a relatively uniform prior here in blue, the model now, including this step of also learning the camera distributions, learns that in this particular data set, here in green, the distribution has actually 4 modes. So there's 4 elevation angles that are more likely than the others. Or here's another example where we start from a uniform distribution and then learn to approximate these 2 modes of this different data set. And this has quite some impact on the results if we compare these non-tuned generative models. And here are some samples drawn from trained but non-tuned standard generative models like Graph and Giraffe. You can see that it's not consistent, it's not leading even to very nice photorealistic results. And when you rotate, this is the rotation axis, when you rotate, sometimes rotation doesn't even happen, sometimes rotation changes the shape or the appearance. So it doesn't really work. But if we also learn jointly now the camera distribution, we can get nice results again, similar to the results obtained with hand-defined parameter sets. This concludes my talk. I want to briefly summarize. We proposed novel methods for 3D controllable image synthesis. We demonstrated training from raw unposed image collections and incorporated compositional 3D scene structure into the generative model as inductive biases. And this allowed us to gain explicit control over individual objects during synthesis. In future research, I think we should address scaling to larger and more complex multi-object scenes, and also to enhance photorealism to match 2D guns like Stylegun 2, for example, which we don't match quite yet. Also, disentangling lighting, materials, etc. is an interesting direction for future research, I believe. With that, I want to close. Thank you very much for your attention, and I'm looking forward to any questions that you might have.
Thank you very much. It's really exciting work that you have presented. I think Chris has a question.
Yes, while people are typing their questions in the chat, I can fill in a quick question that basically concerns the last part. Going from learning the camera pose distribution, you could also think about learning the object pose distribution, or where objects are in the scenes, how many they are, and so on. Have you thought about that? I guess the difficulty there could be that these models like to cheat and might collapse into a mode where it just reconstructs part of the data set.
Yes, indeed it becomes quite hard. I mean, you're right. In a sense, there is this duality, right? Well, focal length, you need the intrinsic. I guess you need to model really in terms of the camera parameters. But what effectively what we did here in this in the case of Giraffe, let me go back. Was to assume the background to be fixed and instead model the camera with respect to the background, because of course the pose distributions of the individual objects are modeled. Yeah, so I guess the question is in which parameter space do you want to model this? I think you could also model it in the backgrounds, like you could model the pose parameters completely here in the background, except for the intrinsics probably. It becomes harder because then you have to disentangle these. I mean, then you have all the compositionality of the backgrounds with respect to the objects, right? So that's why we choose this kind of spherical representation for the camera. But it's a good question. I don't have a very good answer to that. Yeah.
Great. We also have a few questions from the audience. So the first question is, like, if you need to interpret a given image or video, would these models be useful?
I think so. I hope so. We don't. I mean, we didn't tackle this, but of course you could run like GAN inversion techniques and try to or train an encoder jointly and try to infer the objects from a single image and then manipulate them. I think, for example, where this could be useful is if you can do it photorealistically, is to generate more training data by manipulating objects in a scene photorealistically. Or one thing that we are currently looking a bit into is differentiable and trainable differentiable and trainable simulators, where in the end you could even place a little sensory motor agent that does something in that environment and basically interacts with that environment. So I think it would be very useful to have that, but we are also not at the photorealism. We haven't achieved the photorealism that we'd like to achieve. So, but I think it's certainly possible to implement encoders or inversion techniques that figure out the latent codes for these scenes.
I think the next question connects like really nicely to the question, this question, which is what is the motivation behind adversarial training in these models? Besides like when we don't have these labels, when the data is unlabeled, is there any other like motivation for using GANs adversarial training?
Well, in our case, we couldn't use anything else. In comparison to a VAE, for example. I mean, in our case, we have unstructured image collection, so we don't have paired examples, right? So, but of course, we could try to do this with a VAE, and I think there's a paper from DeepMind that does something like this with a VAE. In the past, we have always struggled to get the same fidelity with VAEs as we could get with GANs. So I don't think it's a fundamental limitation, but it's definitely not easy to reach the same level of fidelity. And that's why we use, at least if you use VAE-like models, typically you have to combine them with adversaries to get photorealism. We haven't explored that more, but at least our initial attempts weren't very successful, I have to say.
Okay, and there was also another question, which is, can we replace the NeRF representation with more surface-based representations like occupancy fields or volumetric and like Uniserve?
Yeah, sure. Why not? I think the main problem or the main difference or the main reason why we choose these type of representations here is that they allow you to train from scratch. So if you look at like surface representations, they typically require some input masks to start from. Unless like recently we have tried to lift that a little bit, that's true with Uniserve. So we have kind of a hybrid between the two. But the reason is that without masks, these models will just break because they are like for the background, they can't reconstruct them very well. And so they also mess up the foreground because they can't capture the entire scene. Whereas in radiance field, like volumetric representations, you can represent all the fuzziness and start with a really fuzzy initialization, if you will, and then converge to, at least in the areas where you have enough information, converge to something reasonable. But I believe that they can be combined, right? So but it's hard to start directly with a surface representation, I would say, in particular for the background, because a surface representation always has to commit. It has to commit to a surface, right? If you don't know something very well, then it's bad to make a commitment in a sense, right? So I think you would need to bootstrap also or combine this somehow.
I also have a quick follow-up question on this. Like, is there any way to deploy some explicit controls over these like implicit representations? For example, if you want to like edit part of the scene using a NeRF, like how would you do that?
Well, I mean, here we try to do that by decomposition into individual objects. But if you ask, how would you manipulate individual elements of an object, like the front light or something, where you have modeled them already at the object level, I mean, that is not covered by our approach. So either you model more fine-grained, yeah, you have a deeper hierarchy in a sense, but then it becomes also harder to train. I think then you would need to start using some supervision probably. Or there is some nice works that recently have shown that actually there's nice semantic embeddings also encoded in unsupervised trained radiance field representations, and you can then build on these semantic embeddings. I think that would also work, right? So if we want to change the color of the car or something, or the color of a certain area of the car, I think something like this could work.
Great. Thank you very much. I think there are a few more questions on the chat. If you have time, you can look at them, and
Sure.
We'll probably move on to the next talk.
Thanks for having me. Yeah.
Thanks. So next speaker is Jingyi. I think he's here today, but because of some technical issue, we're going to play the pre-recorded video, and then he will be here answering the questions. So continue typing the questions in the chat. So Jingyi is a professor at the university, the Shanghai Tech University, and he's done a lot of interesting work in computer graphics, computer vision, especially on computational photography and non-conventional optics and camera designs. Today, I think he's gonna talk to us about some recent work on neural rendering of human bodies.
Thanks very much for inviting me. It's my great pleasure to give a talk on our latest work on digital human modeling using neural modeling and rendering approaches. So we all know that actually digital human have been broadly used in a wide range of applications, ranging from movies to gaming to latest AR and VR applications, as well as sports training. So as an example, actually, during my own quarantine, actually, I used digital human for personal fitness training a lot. So we actually captured a series of movements of a trainer, and along with our inferred muscle and the skeleton structures, and to actually put it into an AR setting. For example, we can actually see position the person on a desktop, and we can actually see the movement very clearly along with the muscle movement. So I'll very quickly jump into traditional approaches, then our neural approaches. So for traditional approaches, we all know probably the most widely used 3D reconstruction scheme, or passive 3D reconstruction scheme, is structure from motion. The seminal work by Angjoo et al. Used internet images and try to reconstruct high quality, large scale scenes. And they unanimously follow the same procedure. For example, conduct a camera pose estimation, which is very well studied these days. Then conduct a triangulation to form a point cloud, and later on do the triangulation of the point cloud and then texture mapping. So almost all widely used digital human reconstruction schemes use SFM type of structures. One example is a dome system we built at Shanghai Tech. Actually, starting from 2016, we started building this very large dome system composed of over 80 live cameras at 2K resolutions, and these days we upgrade the camera to 4K. These systems are expensive, no doubt, and complex. There are several tricks. First of all, for example, the camera's viewpoint or view volume is rather limited, so it's kind of tricky to determine whether each camera should view the whole body or just part of the body for better reconstruction. There are always design issues and tricks. As an example, we worked with the Juilliard school in New York City. Actually, we captured performers. Here we show a drummer, a violinist, a singer, and you can see actually the initial reconstruction actually look just okay, I would say, because you see all kinds of visual artifacts caused by lack of textures, caused by heavy occlusion, etc., etc. So this is actually very common in structure from motion type of solutions. For example, in order to conduct a reliable triangulation, you need to first establish robust correspondence matching, and then later on, optimization and triangulation can be tricky and time-consuming. And I'd like to point out one interesting phenomena, discussed by Takeo Kanade. He called more cameras can be worse. Basically, what it means is that if you use more cameras, conceptually, they're supposed to be better. But because of, misalignments of cameras or, errors in calibration, you will observe fine details such as fingers, hair, nose. All the fine details will be missed during reconstruction the more cameras you use. So it's very counterintuitive, but actually we do observe it in real life. So how do we do that? So my talk is composed of 4 components. First we talk about how to do high quality human body reconstruction, then switch to face, then to hands and finger, and essentially to hair. So let's talk about the 3D human body reconstruction first. So a few years ago, we started revisit the problem, and we observed that maybe we are on the wrong track of just merely improving the reconstruction quality. Because as mentioned, despite advances in cameras and algorithms, essentially robust 3D reconstruction remains still very challenging. In fact, we use the commercial software Capture Reality for comparison. We observe, whenever there are, textureless regions, heavy occlusions, they also fail very badly and requires tremendous artists' efforts to fix these. So how about we try to learn to fix the errors, in the reconstruction, which we call neurohuman rendering, which was published 2 years ago. So the main idea is as follows. If we are able to recover a low quality 3D point cloud, and we know the camera parameters, maybe we can, leverage neural rendering to fix specific views or, also, for example, masks. And then we can actually generate a better rendering and a better reconstruction. So to elaborate on this type of approaches, essentially, we use a PointNet++ to extract 3D features from our low-quality point cloud, and then we feed it into a neural renderer. Essentially, it produces 2 things, a feature map and a depth map. And then we use a UNet, to basically, we all know UNet are very good at kind of denoising super resolution type of tasks. So we use a UNet to patch the errors or holes, in the mask, as well as fixing reconstruction. So the idea is very simple. Essentially, you start from poor reconstruction, then you slowly move to better and better masks and images. And it turns out to work very well in the sense that if we are able to generate very dense masks at a very high quality, we can further conduct, for example, shape from silhouette or volume carving to actually patch the errors or holes or noise, in the initial reconstruction. So this is our first attempt. For example, the trainer actually wears a black short. So essentially the black shorts, they impose tremendous problems in traditional reconstruction. By using this kind of mask generation, and then we use a mask to fix the holes, they will produce much better results. So here I show you the comparisons. On the right, you see the initial reconstruction using, for example, CoMap or Capture Reality or any structure from motion algorithms. And on the left, we show the reconstruction using our techniques. I'd like to point out a few parts. For example, the nose, So as mentioned, the more cameras you use, due to errors in calibration, fine geometry will be lost. For example, the nose here. But using our approach, you can recover very high quality fine geometry. And the other part is the black shorts. So without using our technique, traditional methods will exhibit the holes, but in our case, we managed to fix these holes. So this is our initial approach. So along the line, we were thinking, okay, maybe we can, extend the work to mobile portrait scanning. So we started working on this project with the Oppo, the cell phone manufacturer, and they wanted us to use a cell phone to capture multi-view images of a person, and then using SFM type of structure to recover that. So here we show the initial reconstruction using our techniques, They also have a lot of other requirements, for example, real-time performance, things like that. So they're all very challenging. So our thoughts is that to exactly reuse this neural-human rendering pipeline to address these problems. Specifically, we reuse this NHR type of work. Then we use a UNet to simultaneously to fix both the appearance and the geometry. And the results actually looks pretty reasonable, even with a very sparse set of input RGB images. So here show you, some of the sample results, So you can see actually, to some extent, even exhibits, view-dependent features, which is actually common in, for example, latest NeRF settings, right? So this also shows because we use nearby views, to conduct a view interpolation. So it also preserves the view dependency effects. So so basically we have this setting using multiple cameras, structure from motion as raw input, fixing both the mask and the geometry using deep network type of solutions. So we want to extend it a little bit further. So the first trial we conducted is to use just 6 RGBD cameras, So people use that for example, dynamic fusion type of results. In our case, we basically use 6 RGBD cameras. And one thing I want to point out kind of different from other approaches is that we also have a texture branch. So we figured that, it'd be very interesting to combine, geometry fixing with neural texture blending, actually to simultaneously recover geometry and the texture. So this is using 6 RGBD cameras. And here we call that a few shot neural human rendering. And you see, on the left, it's a very sparse point cloud of the Spider-Man. On the right is the results, using our neural renderer. So again, the multi-view or FVV type of rendering produces a very high quality results, and partially fixes the geometry. And here I'll show you more results. Again, here we only use 6 cameras, and even we can handle, for example, very complex clothing, black textures, all these kind of tricky cases. We can partially handle all these problems. And so this basically gives a hope, maybe we can fix the geometry using neural rendering. So we further extended it to, for example, only using RGB cameras. So in this setting, we use 6 RGB cameras. Here we use the connective. The D is essentially used for verification and basically to verify whether our results are of reasonable quality. So you can see actually everything is rendered in real time. So you can actually use the neural rendering engine actually try to conduct multi-view shape reconstruction and FVV rendering in real time. Even can handle complex topology changes. For example, taking off clothes, etc., etc. Right. So this was published at the this year's CVPR. All right. So the main idea is once again is like follows. You want to use a sparse capture system, so mitigate the cost problem. And then you use learn the geometry because you don't have RGBD, right? You only have RGB, so you want to use the neural geometry. But we find what's more important is also neural texture blending. So you want to have a way to blend the textures so that it looks very good, when we change a viewpoint. Okay. So this is trying to show you, you can even handle complex, human-object interactions. In this case, the person. Geometry is recovered by the 6 RGB cameras, and you can even recover, for example, the bags, and the person, taking off the bags. All right, so we conducted one more step further. How can we actually only use 1 RGB cameras, right? So this is turns out to be very difficult. 1 RGB camera essentially falls into the category of, simple type of like a reconstruction, right? So we figured that the most challenging part is not the geometry, but actually pose. So to that end, we built our multi-view capture system that consists of both the mocap system Vicom and also the multi-view reconstruction solutions. And we use that to capture, very complex movements. These include people doing, very athletic movements or doing yoga type of things. Here we show some of the challenge motion data sets, some are really challenging, for example, doing push-ups, and doing, ab works. All these are very challenging movements. and use that as training data because we have both the 3D geometry and the ground truth, motion capture data. So we can actually train a network to actually tackle all these challenging problems. So basically, we captured the 60 by far. We probably already exceeded 100 challenging movements and also 10 performers. And I show you some of the interesting results. The first one I show you is for the person doing a push-up. This is challenging, because a lot of views are occluded. And you see our results are not perfect yet. For example, the left arm, still exhibited some, jittering and instability. But still, it shows that it can actually fit very well. So another challenge we faced is can we actually directly handle challenging movements in sports videos? This turns out to be very useful in sports analysis. For example, we managed to actually show you some of the results, doing badminton. I think the key here is essentially we managed to capture all these movements, ground truth movements, as well as multi-view movements, So this we helped a lot, including, for example, diving, we handle blurs, occlusions, complex poses, etc. We also introduced the semantic meanings of these movements, which turned out we find it very useful as well. Right? Yeah. So this is the first theme of work we've been doing on high quality 3D reconstruction, human body parts. I think one of the most interesting part of human is human faces. So we started looking at the human face reconstruction more than 5 years ago. So our goal is actually trying to use, for example, existing high quality 3D data to train a network that can actually predict fine geometric details from a single image. So this is showing our ICCV2019 work. Basically, we introduced a emotion-based proxy geometry estimation scheme, takes into account the emotion of the facial expression. And we also introduced a detail layer recovery network, trying to recover fine details. So here's a little bit more details about that. The essential idea is actually decompose the image into patches and use the patches to infer, fine geometry within each patch. And for training purpose, we introduced the two training schemes. One is supervised, the other is unsupervised. The supervised essentially is our own data plus the USC light stage data, which consists of very high quality 3D geometry of the human faces. The unsupervised training plays also a very important role because we only have very limited number of training data, So we have to use online images without geometry for training. So let me go a little bit into the details of our solution. So first of all, we build our own, photometric, high quality photometric system, which can capture very high resolution facial details, For example, the wrinkles, the pores, or all the facial structures can be captured very accurately. We also leverage, USC's ICT data structure. And for supervised training, as I mentioned, essentially, we decompose image into patches and basically try to use a PCA type of, scheme, try to predict whether, the basis of the patches for the fine geometry inference. So this is more interesting because all the previous ones I've shown you is actually are static, facial images. So it took us almost 4 full years, to build our own, dynamic light stage. So we call that light field stage, mainly because it's not only a multi-light source capture, but also a multi-view capture. So the system, composes of up to 1,000 light sources and about 40 cameras, trying to capture the dynamic facial expression. Here's how the system works in lifetime. So here we use the Flex 4K, ultra high-speed camera with a 4K resolution at the 4K frame per second. So this allows we can illuminate the subject at a very high frequency without, the subject experiencing bad feelings. And this is showing you, our camera resolution is so high, you can actually capture very, very fine facial details. So for example, you can capture, ultra fine details such as the pores of the face. And we can also do relighting type of application, which I will talk about in a second. Right? But what I'm saying is that essentially we managed to build our own, light stage data for conduct the supervised training. But we also conducted unsupervised training because we collected over 100K in wild images. The main idea here is actually to first estimate the lighting and albedo of these facial images, right? Then essentially we use our network to predict the fine geometry of the facial structure and re-render it. So it's a differentiable rendering, pipeline. Basically try to match the appearance loss. So turns out to boost the performance significantly with the unsupervised training. So let's look at some of the unsupervised training results. Essentially, we have the coarse mesh, normal map, shading map, albedo, all recovered, using the single image. Once we do that, we feed it into our differentiable renderer and then trying to recover the fine geometric details. So with the help of supervised and unsupervised training, we can conduct some very cool tasks. One task is, for example, this is the late actor Robin Williams, and using our technique, we can actually recover, for example, wrinkles on the forehead, essentially all the fine facial details. We also matched expression of the face and the mood of the face, which we find very important. And here is my favorite result. Neither subjects can be actually captured using our technique, right? Apparently. So on the left, President Donald Trump, on the right, Jack Ma from Alibaba. And we managed to use our technique to infer very high resolution and detailed facial geometry using this framework. All right, so once we conducted this task, we've started looking at, okay, maybe we can do one more step. All previous ones are using one single image, right? Can we actually using a single image, but at the same time change the style of the image? But in this case, not in the 2D style, but in the 3D style. So my student Ampei Chen, who will be doing a postdoc with Andreas, has been doing this work. So his idea is actually to introduce something called a 3D semantic volume or field. It's called SOF, semantic occupancy field. And the difference between this technique and traditional approaches is that this is really embedded in 3D. So if you revisited it from the NeRFs perspective, right, you can see actually it does fit the volumetric kind of reconstruction ideas. So the main idea is, using the SOF as primitives and combine it with our 3D scanner models, and then we can change styles and change viewpoints on the fly. So here's my favorite demo, and this is showing you generating from drawings. So in this specific case, let's say if someone wants to generate a face, looks like Harry Potter, Daniel Radcliffe, right? So what we can do is actually we can find a photograph of Daniel Radcliffe. Then an artist or user can actually paint on top of the images, draw eyebrows, draw hair, draw nose. As the artist started drawing different parts of the facial structures, on the right, it will automatically generate this kind of images. And of course, you can change viewpoints later because it does support the multi-view type of viewing experience. So as you can see, this is interesting because we're drawing along the, the binoculars, are round, but the generated ones are rectangular. So as we generate the mouse, the facial expression will appear accordingly. Right. So I'd like to point out one more thing on what we did on facial reconstruction. That is relighting. Because our fine geometry of the faces are generated using our light stage. So we naturally have our own dynamic light stage data. So we have this neural relighting framework. Basically, we can conduct image-based relighting because we have both geometry inference and environment map and the lighting latent code. So we implement this on the cell phone, which we are pretty proud because we checked, by far probably only like a Google Pixel 5, they have a equally high quality relighting schemes. So this is showing you that we can actually capture image on our cell phone. Then we can change environment lighting. We can even add more light sources to change the illumination effects. All right, this is showing you we can actually do live videos, not only on images, but live videos. This has been accepted to ICCV21. So this is showing you on the top is the original input image. On the bottom, we show two, relit sequences using different environment maps. So I'm showing you kind of like using this technique can actually boost the capability of relighting. I do want to show you this limitation because if you look very closely to the images we produce, you will see actually still it loses a high frequency components like facial details. So we're in the process of fixing these kind of facial details using, for example, something like along the total relighting work. So I talked about two parts already. One is on the human body. Hopefully I've shown you that, the DeepNet are pretty good at, fixing holes, fixing noise, and also generating new appearance, right? So the face is more like a generating fine details, generating, appearance models. In the human body case, it's more like fixing. So these are two very unique capabilities. So let's move on to the other part is very difficult. That's human hands. So there has been a lot of work, on, generating, human body movements. But in contrast, a very limited work on hand movement. Probably the most, famous work is the Mano framework, by Romero et al. And still, I think the fundamental reason behind the hands, why the hands are so difficult to recover is, first of all, we do observe hands every day, right? So we know, okay, this movement is fake, this movement is real. The second is we lack an anatomical understanding on how our hands move, on how our bones move. Can you even tell, which joints are moving under a specific pose? So we did a crazy task, which I view, which is pretty insane. That is, we generated the first MRI hand data structure. So our goal essentially is trying to understand the anatomical structure of hands, the bones, the ligaments, and the muscles. So we made some achievements on the bones, and we're in the process of understanding the muscles and ligaments. So let's talk about the goal here. The goal essentially is try to build a anatomically correct and simple to animate and differentiable hands. So essentially, we want to use MRI to do that. We are very lucky, actually. We at Shanghai Tech have a MRI machine that hasn't been used by anyone. It's just sitting there. So I said, fine, why don't we just use that MRI machine to capture? So there are existing MRI or CT data sets, but very limited. For example, the TOG 2019 paper, they have a 24 MRI scan with only 2 subjects, very small scale. So in contrast, we want to generate a much larger data set, okay? So essentially, what we managed to do is we actually captured the 200 MRI scans and of 35 subjects and 50 postures. And don't make me wrong, this task is extremely painful because each subject actually needs to stay still for 40 minutes per posture. So this is a very painful experience, but in the end, we managed to get this very valuable data. So in order to do that, because when you stay there for just even 5-10 minutes, your hands movement will start to change. So what we did is we use a molding solution, trying to build a mold of the hand, right? So your hand will stay fixed. And on the right, it shows that using the MRI data, we managed to capture the very accurate bone structures, on top of the appearance structure. This is showing you some of the results. This is showing you our MRI volume on the left, and on the right is the MRI slice. And we have the MRI volume. We managed to use a segmentation scheme to segment the very fine bone structures. To our knowledge, it's probably the first, comprehensive MRI hand structure produced ever, So we're in the process of releasing part of the data to the public, but probably not all yet. But at the same time, we are capturing, and annotating, for example, muscle structures. So in our results, we basically use around the 3,000 vertices, 6,000 faces, and 20 bones and 19 joints. And this turns out to work out very well. So I'm not going to talk about details, but basically we use LBS to consider both the shape parameters and the pose parameters together. And using that, our goal is actually trying to combine the appearance with the MRI bone structures. If we manage to capture a single view or multi-view of the hand, can we actually infer the bone rotation and the joint positions, from the images? So this is our pose estimator. So due to time limit, I'm not going to talk about details, but this is just showing you some cool results. Just using a single RGB or multiple RGB images, we can actually refer very accurate bone position and structures. This was published at the ICCV 2021. Right. So our next step is actually trying to use integrate it with muscle structures. So the last part, also I think is a very promising part, is human hair. It's actually hair. So the hair is very difficult to recover, but never underestimate, the realism of a hair. The hair is very important because if the realism of hair is lacking, then even though you can recover hands, face, body very accurately, everything would look fake with the hair. So we introduced something called the neural opacity point cloud. The main idea is, again, going towards the volumetric type of concepts. We want to introduce the opacity value on top of the RGB value. So we adopted the multi-view setting capture, just like the human body. But in this specific case, we want to infer not only the RGB color, but also the alpha value of it. So the pipeline goes pretty much like the NHR, neurohuman rendering, as I talked in the very first place. So you infer the point features from the feature map. You use separate branches to handle the RGB color and alpha branch to handle the alpha volume. And this fits very well into the traditional differentiable renderer, pipeline. And you can actually conduct, differentiable rendering back and forth to, optimize the volumetric alpha map. And it turns out, in our case, this works out very well. So I'd like to mention that we do use a separate, decoder to handle the alpha channel during rendering, because your training and rendering are done separately. So this is showing you, if we do a rendering without using a separate path, the rendered result will exhibit excessive blur. But if we do use a separate alpha encoder decoder, the volumetric alpha will exhibit a sharpness and much clearer. Okay, so I'm going to skip the training part due to time limits. Instead, I'm trying to show you this our capture system. Again, our capture system uses this multi-view capture, but in this specific case, we only use static cameras, SLR cameras. And using multi-view capture system, we can actually build this point cloud, and then we get the ground truth alpha maps for each captured views. and then use the capture views to conduct training and eventually, volumetric alpha rendering. So I want to show you the results. Details can be found in our pioneer paper. So on the left is showing, traditional image-based opacity, how you see the jumping of appearance. If you use neural rendering without considering, separating channels, you see this weird blending effects. But this is using our results, NLPC results. You can see the hair structure can be, alpha map can be very well preserved. This is showing you, a wolf scene, and with the geometry only, you see jumping with without separating the alpha channel and the RGB channel exhibits excessive blur. With NLPC, it shows you, stability, and you see the very nice structure of the fur. This is showing you a real result of human hair. You see the jumping in the traditional IBR, excessive blur, without separately considering the alpha channel. This is showing our results. So we're also motivated to see the possibility of integrating this with, for example, neural radiance field, the NeRF. And because NeRF naturally provides a volumetric reconstruction, so this will fit perfectly into the alpha channel. So I'm only going to show you the results, with the NeRF type of, volumetric alpha. You will see actually we can even achieve 1 order of magnitude more magnitude higher quality alpha reconstruction. So this is showing you the real hair, and you can see all the fine details are preserved using using the volumetric opacity we inferred from NeRF. Okay, so I think my time is up. I'd like to thank my team at Shanghai Tech, without whom, we wouldn't have accomplished all these tasks. So we have a slogan: to see is to believe is to see. And multiple members of my groups are graduating. Some will join, Tina's group. The other will join, actually, Andrea's group. So they're all looking for postdocs. I think they're doing very well. So if you have postdoc or even faculty positions, please do consider them. If you have students who want to send over to Shanghai Tech, to work with us, we have a light stage. Actually, we have 2 light stages, one smaller one, one bigger one. And then we have a dome system with 80 cameras. So we're very pleased to work with you all. I think that concludes my talk. Thank you all very much.
Thank you very much for Jingyi. I think Jingyi is here today with us.
Hi, yes.
Hi.
Right. I was hoping to give the talk in person, but it turns out, my network is unstable. But for Q&A, I think it's okay. But essentially, I think, everything is delivered in the pre-recorded video.
That's awesome. The video is like is amazing with tons of crazy interesting work. I have a quick question. We'll probably have a few more from the chat. So how do you see this approach for capturing 3D shapes? For example, the wolves. If we want to train a model for wolf, how much effort do we actually need to spend on capturing the 3D data?
This is a really good question. So I'll share with you my own experience, or the experience from my group. So we figured actually, NeRF, is a really, really good on rendering new views. If you want to render a new views, even with the opacity or volumetric opacity, NeRF works really, really well. The challenge though is actually how do you use a NeRF kind of settings, to actually do the reconstruction, because it's a slightly different problem, right? Because essentially you're targeting at, converting volumetric structures, right, to surfaces. There are several very magnificent recent works, right? For example, News, I think, which is really cool using sign distance field, we see very promising results as well. For the wolf thing per se, the challenge is not the shape. The challenge is the fur, is the volumetric one. So our focus currently is mainly on reproducing photorealistic alpha map, at different viewpoints, rather than just reconstructing them. But I see actually, I think the whole community is going towards a neural reconstruction route. So I think we'll see a lot of exciting work coming out. Yeah.
Awesome, great, thank you. So I think there is a question from the chat, which says NHR, I guess it's neural
human rendering.
Reconstruct. Yes, uses differentiable rendering to complete sparse geometry. Can it be extended to NeRF or news architectures?
This is a really interesting question, actually. So for the NHR, we use the point cloud from structure from motion, because at that time there was no NeRF, so we couldn't use NeRF, you know. But you're right. So we can definitely use geometry, you know, from NeRF as a starting point, and then conduct NHR. Having said that, I think there are alternative routes than using NHR, because like there are so many NeRF-related works, you know, coming out these days. One possibility is to combine with IBRNet. So for IBRNet, you know, it will accelerate the training significantly. You pre-train a network, and then you know, use you know, sparse images to refine the results. So basically, we actually have a paper at ACM Multimedia this year. Just you know, the conference will be in a few weeks, an oral paper using IBRNet for sparse multi-view human reconstruction. So I think, you know, definitely, yeah, NeRF can be used to combine with NHR, but alternative routes are, because you want to accelerate NeRF training. So you definitely, you know, IBRNet is a very positive route.
Great, thank you very much. I think we're running out of time. We'll probably have a very short break. Thank you, Jingyi, for joining us today.
Thank you, yeah. I'll see you at the panel though, okay.
Great.
Yeah, bye.
But we'll have a very short break, 2 minutes actually. Then we'll go into the next session, another 3 talks. So see you in 2 minutes. Okay, I hope everyone is excited to go to the next session. The next session will be hosted by Natalia. Take over.
Sure, thank you. Welcome everyone. I hope people are getting back from the break. Apologies, it was so short, but we have a lot to cover today. So I'll be your host for the next section, which will have 3 talks from David, Novotny, Iasonas, Kokkinos, and Niloy Mitra. A quick reminder for those who just joined that this workshop is being recorded and live streamed on YouTube. If you're watching the talks, we highly encourage you to ask all questions you may have. For that, if you're on Zoom, please do type them in the chat window during the talk, so we have time to capture them all before the speaker finishes. And if you're watching this on YouTube, you can also comment there on the live stream, and we'll try to capture those as well if we have time. Okay, with that, let me introduce our first speaker, David Novotny. David is a research scientist at Facebook AI Research in London. Before joining Facebook, David obtained his PhD from the University of Oxford, where he was a PhD student in the visual geometry group, jointly advised by Andrea Vedaldi and Diane Larlus from Naver Labs Europe. David's research focuses on discovering representations of semantic and geometric structure of objects from images and videos, and recently has done lots of awesome work in unsupervised 3D reconstruction and novel view synthesis. And today, David will give a talk entitled Common Objects in 3D, which is also a project which is being presented at this ICCV. David, please, the stage is yours.
Thank you very much. Can you see my slides, please?
Yes.
Great. Okay. Thank you very much for a very nice introduction. So yeah, as said before, my name is David, and this is essentially going to be a presentation about like culmination of a 2-year-long effort in dataset collection and very hefty experimentation on unsupervised UV synthesis. So, okay, so this work was essentially a work of a large team of people. So we were not only working with people in FAIR, but I'm also extremely happy for the collaboration with University College in London, and this is essentially credits for all the people who were involved in this very large project. So throughout this work, we will be interested in the problem of learning the 3D shape from 2D images. So imagine that we have 4 images of a teddy bear here on the left. And essentially our goal here would be to reconstruct the geometry and appearance of the teddy bear, which is the main object in the center of the scene, such that we can then render it from novel viewpoints, which you can see here on the right of the slide. And so essentially having this kind of capability opens a lot of interesting applications, ranging from augmented reality, where we can transport objects between different realities, automatic generation of models for 3D graphics, or maybe even virtual try-ons of clothes for any living beings which are around yourself. And so I would like to get slightly more specific about the actual machine learning task, which we would be tackling here. So we would assume the category-specific 3D reconstruction, where as a training set, we have a bunch of images of an object category, for instance, a bunch of hydrants here on the left. And our goal would be essentially to obtain a machine learning model, which is able to learn the generic structure of the object category in form of geometry and appearance, so that we can use these trained priors later in the few view reconstruction task, where we are given a small number of input views of a given object. And our goal is essentially to reconstruct the whole object only given this kind of partial observation. And so in this case, of course, the priors are needed in order to fill in the missing bits, which are not captured by the input views. And so, of course, this task has been tackled before. And what I'm doing here is that I'm plotting it on a graph where on the x-axis, we have the difficulty of the task of the prior work. And on the y-axis, we can see the amount of supervision which is needed in order to tackle the actual task. And so historically, the first approaches are appearing in the top left part of this slide, where we have been working on synthetic data, or the researchers have been working on synthetic data. Namely, this was the ShapeNet dataset, which provides us with the perfect 3D ground truth. It has been generated by expert graphic designers, but one of the biggest issues here is that, of course, this is a synthetic dataset, so whenever we deploy an algorithm trained on ShapeNet, we really don't know whether it's going to work in real life. Nevertheless, I think ShapeNet was a great contribution to the community, mostly because it gave us some kind of like a first proof of concept that this kind of unsupervised category-specific 3D learning can actually work. And some of these works are cited here on the slide, and what you can see is that many of the authors are actually speaking during this workshop. Later, the community basically moved to the right side of this graph, where we have been learning only from real isolated views of object categories, such as birds from from CUP dataset, or cars from Pascal VOC. And so in this case, the problem is extremely difficult because we cannot exploit any multi-view constraints between these individual isolated views. And so what the researchers essentially did is that they assumed manual annotations, either in form of semantic key points or a known category 3D template, or they assumed like a very strong constraints on the output of their reconstruction algorithms. So for instance, in case of the CUB birds, it is very common to assume that the bird is actually perfectly symmetric along that axis, which essentially goes through the center of the body of the bird. But probably the main message I want to deliver with this graph is the fact that this part in the middle of the whole graph is essentially quite unpopulated by methods. So we don't really have methods which would be working on real data. And at the same time, they would not be as difficult as just learning from the isolated views. And so this is essentially where we enter the field. So our main proposal throughout this presentation is going to be a novel data set called Common Objects in 3D, which is a data set of real views of object categories. But importantly, this data set contains multiple views, the same instance of a given object category. So this way, the whole problem becomes much less challenging because we can enforce the multi-view consistency constraints between the individual views of the instances of the object category. And hopefully this way we will obtain much better results during the category-centric new view synthesis. And so this is just an overview of the data set. You can see here on the left, the data set is composed of a lot of videos of these individual instances of the object categories. And together with the videos, we released a bunch of 3D reconstructions, which could be used in order to supervise your 3D reconstruction algorithms. And so since this is only an overview, I would like to give you a bit more details about this. And so the dataset is a crowdsourced collection of object-centric video tubes. What this means is that we essentially ask Amazon Mechanical Turkers to put an object in front of themselves on a solid ground, take out a smartphone, which is a commonly owned accessory these days, and essentially take like a 360 video, slowly rotating around the object such that we slowly scan the object from every single view. And later in the second stage, we would take those videos and we would automatically annotate them with a structure from motion algorithm, which would track the cameras. And it will also give us the 3D reconstruction, dense 3D reconstruction of the actual shape in the center of the scene. So this is the stage of the reconstruction right now. By March 17th, which is the ICCV deadline, we collected 22K videos from 51 Microsoft Coco categories. I will speak about the reason why we selected 51 Microsoft Coco categories later. And of course, after the submission deadline, we also continued the collection. And at this point, the dataset is doubled the original size. So we have 46K videos at this point. And at the bottom, what you can see is the number of videos collected for every single category in the dataset. So on this slide, you can see examples of the collected videos. So on the left, you can see some videos of teddy bears. On the right, videos of hydrants. Next slide contains cups and benches. At first glance, it is quite obvious that these randomly selected videos actually contain very decent captures, where it seems that the Mechanical Turkers were actually quite diligent in sort of following our advice in how to capture the videos. So this was about the actual data set collection effort, and now I will talk about the reconstruction and the automatic annotation of the data set. So the reconstruction pipeline was a standard two-stage structure from motion reconstruction pipeline, where in the first stage, we would track the cameras in the individual videos. So here what we would take is the video, we would chop it into 100 frames. We would pass this through Colmap, which is a very major structure from motion framework. And then essentially Colmap would track or annotate every single frame in the video with the camera extrinsics and intrinsics. Together with that, we would obtain a sparse point cloud of the scene. And so here are some statistics of this kind of reconstruction step. So we collected something like 100 frames for every single video, which in total gives us 1.5 million frames contained in the whole Common Objects in 3D dataset. The reconstruction time was roughly 30 minutes for a single video, which in total gives us 5 GPU years of reconstruction time. So you can see that indeed, it would be very hard to reconstruct the whole dataset or annotate the whole dataset with 3D ground truth if we didn't have at our disposal a lot of computational resources. So these are finally some nice examples of the camera tracking. So in the center of the scene or in the center of each group of videos, you can see the dense 3D reconstruction of the shape. I will speak a bit later about how we obtained that, but next to it, you can see the collected video. And orbiting around the actual 3D shape is this camera icon, which essentially follows the captured video, which is the camera tracking. And in those cases, you can see that the camera tracking was very successful. So these are a few more examples of the camera tracking for a few more instances per object categories. In this case, this is the bunch of reconstructed broccolis, hydrants, and motorcycles. You can see that we covered all possible object categories in terms of their size. In all those cases, you can see that the tracking is actually very successful. And yeah, so now I have been speaking about the sparse reconstruction. In the next part, I would like to speak about the reconstruction of the actual object in the center of the scene. So the dense reconstruction takes as input the sparse point cloud and a bunch of cameras extracted by Colmap, and this enters the multi-view stereo algorithm of Colmap, which essentially annotates every single frame with a depth map. And then after that, the depth map gets segmented with a pointer and segment. This is the reason why we selected the 51 Microsoft Cocoa categories, because we can essentially reuse the pre-trained content segmenter, which has been pre-trained on the categories from the Microsoft Cocoa. So without any additional pre-training, we can just use existing segmentation models in order to generate a nice dense reconstructions. More specifically, the dense reconstructions are then generated by unprojecting the individual segmented depth maps into the common word content frame. So these are some examples of the dense reconstructions for multiple instances of an object category. An interesting observation here is that if you, for instance, look at the plans in the bottom of the slide, you can see that they have been quite successful, even in the case of this kind of object, which is a very, very complex geometry. So this is a quick conclusion about just the dataset collection part of this talk. So we have publicly released the dataset roughly 2 or 3 months ago. The best place to visit at this point is the GitHub page here on the Facebook research site. And it contains all the possible hyperlinks that you essentially need in order to access the dataset, download it. But also it contains a lot of tooling such as data loaders or evaluation scripts. So in the future, we would like to release the next version of the dataset, which will roughly have 2 times more objects, as I said already in the previous slides. And hopefully the new version will also have cleaner annotations. Furthermore, we would like to release a proper public benchmark, which will allow researchers essentially to evaluate their methods on a hidden test set. And this way we can basically form a nice leaderboard of different research groups trying to outperform each other on the new view synthesis task. Okay, so this is the part about the collection on the dataset collection itself. In the next part, I would like to speak about how we actually use this dataset, large dataset, in order to learn category-specific 3D. Okay, so the first task, which we were essentially considering, was actually not doing any kind of category-specific learning. What we first wanted to check is whether the individual videos of the dataset are actually reconstructible just on their own without any kind of category-specific learning. So this is the standard overfitting task popularized by neuroradiance fields or neurovolumes, where we just have the single input video, and what we want to do is just reconstruct that single object. So a standard overfitting pipeline would work as follows. So we would have a bunch of training frames from the video here on the right. This is quite obviously a video of an apple. We would randomly sample an image during every training iteration. We would take the corresponding camera. We would shoot rays from the camera, which are sort of impaling the center of the scene, which contains the optimized 3D shape. And then we optimize the 3D shape such that if we render the whole shape into the camera, we end up with an image which actually matches the ground truth image, and we ensure this by minimizing the photometric loss between all the pixels. In this case, this is typically just a relative distance between the colors of the pixels. Together with that, we also have the ground truth opacity masks coming from the pointer and render segmenter. So in this case, you can match the predicted or rendered opacity mask to the actual segmenter mask. All the benchmark baselines essentially follow this kind of learning pipeline, but they mostly differ in the way how they represent the actual 3D shape, which is being optimized. And so in this case, we try to cover all the possible popular shape representations. We started from, of course, the famous opacity-based implicit functions such as NeRF, or sign distance field functions such as the IDR, or even like learned ray marchers implemented using SRM, which is a single representation of this. Furthermore, we also optimized voxel grid narrow volumes, some kind of mesh and point cloud-based reconstruct. So there was in total, I think, something around 13 baselines, which we actually tested on this task. Together with that, we endowed some of these baselines with the positional embedding trick, because the trick was actually not known when these baselines were released at first. So here we can see the quantitative performance on the new view synthesis task for the overfitting to the individual scenes. And quite unsurprisingly, it is obvious that NeRF actually wins over all the other baselines. What we also observed is that the positional embedding doesn't really help the previous baselines. What we found out is that the positional embedding, in fact, makes the baselines overfit to the training views, which was not great to see. And then finally, an obvious observation here is that the individual implicit methods quite decisively outperform the mesh or point cloud-based methods, which is probably, again, quite expected given the surge of implicit-based methods in the recent years. So this is an evaluation of the new view synthesis depth accuracy. So in this case, again, NeRF was winning absolutely over all the baselines, which shows that there seems to be a correlation between the performance of the reconstruction of the geometry and the reconstruction of the appearance. So this probably says that if we want to come up with a nice new view synthesis method, that method probably has to also understand the geometry of the scene very well. We also evaluated some kind of a trade-off between the accuracy of the generated colors and the speed of the rendering. In this case, narrow volumes were giving by far the best trade-off because they are roughly 2 orders of magnitude faster than NeRF. So these are qualitative results, finally. So we can see here that in the middle column, there are the narrow volumes, which give slightly more blurry results than NeRF. But again, what has to be seen here is, or noted here, is that the narrow volumes render essentially takes 30 seconds, while the NeRF render of this whole rotating teddy bear takes roughly 30 minutes. These are a few more qualitative examples. So you can see that the data set contains all possible levels of difficulty, starting from the apple here, where the shape is very simple, but the texture is actually quite hard to reconstruct. Then we have very hard examples corresponding to this kind of bonsai tree, which has a very complicated topology and texture at the same time. In all cases, it seems that NeRF indeed improves a lot, but of course, in case of the bonsai, there is still a lot to improve. Okay, so after we have verified that for the overfitting, the dataset is indeed suitable, in the next stage, we wanted to do the actual category-specific learning. And in this case, the idea was to take a bunch of videos of a given object category, and then we wanted to train a single model, which is able to reconstruct every single video in the training set without some kind of generalization to the actual tests. So in this case, we were just testing whether the individual implicit function-based methods actually have enough capacity to represent the whole family of instances of a given 3D, of a given object category. And so here we focused on the implicit shape framework again, because in case of the overfitting task, this was giving the best performance. So this is just a quick overview of how the implicit shape learning works. Given a camera, we just shoot a ray through the scene, sample points along the ray. For every single point, we would evaluate the opacity function called F in this case, and the coloring function C. And then what we are doing with this is that we ray march over this set of predictions such that we generate the final color of the pixel. What is important to note here is that this, of course, cannot be used for representing multiple objects of a given object category, because the opacity and coloring functions are only conditioned on the 3D point itself, and they are not conditioned on anything else, which will allow us to change the form of the opacity field. And so in order to extend this implicit shape framework to like a multi-scene setup, we propose to do the simple thing, which has been, for instance, already presented here in the graph paper. We just append a latent code to the input 3D locations, which are coming into the implicit function and the coloring functions. And this latent code is essentially broadcasted across every single 3D location, which comes into the functions. And by altering these latent codes, what happens is that we can actually alter the scene, which is being represented by the opacity and coloring fields. Now, how do we obtain these latent codes? We essentially do this through standard auto decoding, where we attach to every single scene a prescribed latent code, which is then optimized with all the other parameters of the network we optimize. So in this case, we are optimizing the weights of the coloring function and the opacity function. And together with that, we would treat the latent codes as 3 parameters of the learning, and we would optimize them with the individual weights. And this basically tests that the opacity and coloring functions indeed have enough capacity in order to represent the whole structure in terms of the geometry and appearance of the whole object category. So I will immediately jump into qualitative results because they look quite nice. On the very right, you can see that SRN, the scene representation networks, probably were giving the best performance, which was quite surprising because we would have probably expected NeRF to give us the best performance. But I feel like the issue with NeRF is that the implicit function itself is not a very smooth mapping, which doesn't allow the function to converge well to this kind of like a very complicated representation of all the possible instances of a given object category. Whereas, for instance, in SRN, there are layer normalization layers which tend to make the whole thing converge much faster. Again, the advantage of SRN in this case is that the rendering times are extremely quick. There are a few more examples, and you should bear in mind that although the reconstructions are quite blurry, we need to say that, for instance, the SRN is able to reconstruct not only this ball, but the same model is able to reconstruct 300 other balls in the training set. A few more examples. In this case, on the hydrant, it's quite obvious that the SRN indeed gives probably the best performance. And there are also very challenging examples, for instance, this teddy bear, where you can see that the SRN tries to do something, but it still washes out a lot of details. So indeed, the dataset is very hard, very challenging. So we are happy that there is definitely space for a lot of improvement. Okay, so this is just a quantitative evaluation, which somehow shows that indeed the SRN gives the best performance compared to all the other methods. What we also observed that all the sign distance fields based methods were not working as well as the implicit function based ones. Again, my intuition here is that it is much harder learning problem to regress the distance of a point from a surface for every single instance of the given object category in the whole training set. And in terms of the reconstruction of the depth, I feel that the conclusions are the same as in case of the reconstruction of the color. In the case of the depth reconstruction, the SRN again wins. Okay, so in the final part of the talk, I would like to speak about this most challenging problem, which is essentially the view reconstruction of the object categories. So as a training set, just recall that we have a bunch of videos of an object category, and our goal is to train a single machine learning model which learns the generic structure in terms of geometry and appearance of the object category such that we can later use it for view reconstruction and test set where we have a small number of input views of an object, for instance, the yellow hydrant here on the right. And what we want to do is to fill in the missing bits of information using the priors learned at the training stage. And so again, we will be using the multi-scene implicit shape framework where we are broadcasting this latent sequence-specific latent code to every single 3D point. But what I would like to describe here is what is the issue with a standard naive solution to this kind of prediction of the latent code. So for us, the naive solution here is essentially the fact that we can take this input image, which is the one which is known, and we can just pass it through CNN, which generates the latent code. And then we can put that latent code into an implicit function, which then generates the field of opacities and colors. Now, what I will describe next is why this is a naive solution and why it's actually quite likely to fail. And at the core of the problem are the coordinate frame ambiguities in the structure from motion annotations, where if we, for instance, where we are essentially not in the ShapeNet realm anymore. And this means that if you look at all the reconstructions obtained by structure from motion in the individual images, we will see that they're sort of floating around. They are not aligned both in terms of translation and also in terms of rotation. So in this case, we don't really have this additional supervision in form of semantic alignment of the 3D shapes. Now, why is this a problem? This is demonstrated on this simple example. So imagine that we have a bunch of images. We generate structure from motion reconstruction. Then we generate the same reconstruction, but with different random seeds. So we will end up with the same shape, but because of the innate ambiguities in structure from motion, we will end up with a reconstruction which is related by an arbitrary similarity transformation. Now, if you look at the embedding, at the latent embeddings generated by the convolutional network, imagine that we embed this kind of image using the CNN. This will generate latent codes at one, and then a second image, which is exactly the same one as the first one, again using the same CNN. Of course, because we have embedded the same image using the same CNN, we end up with two latent codes which are exactly the same. But the contradiction here is that these two embeddings, which are the same, they have to represent different geometries, which is of course impossible because everything in this pipeline is completely deterministic. So this is a problem, and our solution to this problem was essentially published at CVPR21, and it proposes a novel embedding called warp conditioned rate embedding, which works as follows. So imagine that we have a bunch of source views of a donut. Now, what we propose to do is essentially describe every single pixel in the source view with a hypercolumn descriptor, which is basically a dense, deep descriptor. And then, given a target view, we would just emit rays from this view. Along each of those rays, we would sample a bunch of 3D points, as it happens in classic NeRF pipeline. And then we would project those points into the individual source views. We would sample the features from the source views. This way, we'll end up with a bunch of features for every single 3D point. And then what we decide to do is essentially aggregate those source features for that given point using an angle-weighted average. So this will generate a point-specific feature, which is then passed through an MLP. If the video continues. Yes, which is then passed through an MLP, where the MLP essentially predicts for every single 3D point the color and the opacity, which is again ray-marched over using the emission absorption ray march. And so the reason why this works is the fact that this kind of projection transformation of the points along the ray into the individual source views is completely invariant to the ambiguities in the structure from motion reconstruction. So no matter how I rotate the whole set of cameras, I will always end up with the same projections, and this will give me essentially an opacity field and a coloring field, which is perfectly invariant to the ambiguities in the structure of motion. So this is just a quick quantitative comparison, which shows that if we endow NeRF with our warp condition embeddings, indeed we outperform the naive baseline, which is here on the right. And here we can see some qualitative results of the new synthesis using the warp conditioned ray embeddings. What you can see is that in many cases, the reconstruction is quite sharp from the top of the donut. Of course, the problem is that the donut touches the ground with the bottom part, so we don't really have enough information to reconstruct it. Okay, so this was for the warp conditioned ray embeddings. And in the last part of the presentation, I would like to mostly speak about our main technical contribution of the common objects in 3D paper, which is called NeRFormer, which is something like an efficient marriage between transformers and their radiance fields. And so the whole work has been essentially motivated by the limitations in the warp condition NeRF. which I've been describing on the previous slides. And the limitations are twofold. The first one is that the MLP, the NeRF MLP implicitly processes these individual points on the array completely independently. So it cannot really deal with any kind of noise in those sparse conditioned array embeddings, and for any kind of noisy input which it would produce noisy output. The second limitation is that the aggregation function from the individual source views is actually hand engineered. So again, if there is some kind of noise in the source views, this kind of aggregation function would be very sensitive to that. And so we essentially propose to deal with both of these issues using the NeRFormer architecture. So in order to deal with the first issue, which is the implicit MLP processing the individual points completely independently, we make the following observation. So if you look at the points along the array, indeed what you can see is that these points are just a sequence of features. And as such, they essentially admit processing using some kind of sequence-to-sequence model. In this case, the sequence-to-sequence model is, of course, a transformer, because this is the most popular architecture which has been proven very successful in the recent years. So what we essentially propose to do is process this list of features with a transformer to generate colors and opacities for every single point, and then we would march over this in order to generate the final render of the given pixel. The second issue of the hand-engineered aggregation function is dealt with in a similar fashion. So in this case, we make a similar observation where imagine that we have a point along array, and then we project it into all the source views, we sample the source features. What we will end up with is a sequence of features. Again, in this case, the sequence is unordered, which is of course not a problem because the transformers can deal with this even completely effortlessly. So again, what we propose to do here is to employ a transformer model, which would essentially learn to aggregate the features along the pooling dimension. And this way, the transformer can learn to become invariant to the noisy features which are input to the sampling process. And so the NeRFormer, as I said before, is essentially joint array marcher and aggregator, where the array marching and aggregating steps are executed using these transformer layers, which I have described on the previous slides. So imagine that we have a bunch of points on the array. We sample all the possible features from all the possible source views, and this will give us this nice two-dimensional image grid, which along one side has the dimensionality of the feature pooling dimension, and the other side is of the size of the array dimension. And then what we do is that we basically pass this two-dimensional feature grid first through the array marching transformer, which attends to the array dimension of the two-dimensional feature grid. After that, we swap the dimensionality of the attention, and then we only aggregate to we only attend to the aggregation dimension or the feature pooling dimension of the two-dimensional feature. And so we process the feature grid like this with the transformer layers until we are happy. And in the end, we end up with a bunch of predictions of colors and opacities for the points along the race. And in the end, what we do is that we basically march over those using additional absorption. So this is a quantitative evaluation which shows that indeed the NeRFormer performs the best out of the individual baselines which we compared. So this is just a small excerpt of the whole evaluation. Indeed, we evaluated against something like 14 baselines in total. And a small feature here is that it essentially took 8 GPU years of experimentation again. So we really made sure that we set the baselines correctly on the whole data. So these are some qualitative results on the new view synthesis evaluation, where you can see that indeed the NeRFormer gives probably the best color reproduction accuracy. Of course, it's not as good as in case of the overfitting to the individual scenes, because these reconstructions are generated only a small number of known views of the objects which have never been seen before. A few more examples. And yeah, so this concludes the presentation. So just to quickly recapitulate, we have released a novel dataset of object-centric videos for learning 3D object categories, which is called the Common Objects in 3D. The dataset is bigger than alternatives, both in terms of the number of videos and object categories. It has been publicly released on the following GitHub page. So make sure to visit it, because it contains all the possible links which you need in order to use the dataset, download it, and also evaluate on it. Together with that, we proposed NeRFormer, which is essentially a state-of-the-art method which is able to reconstruct the individual 3D object categories simply just by observing the videos from the dataset. And so with that, I would like to conclude the presentation. Thanks for listening to me, and I'm happy to answer any questions.
Thanks so much, David. Awesome talk. We're exactly at time. So there are quite a few questions about the Cos3D dataset on chat. They're technical about accessing data and processing. So I'm not going to read them, but please answer them offline. Maybe one thing I could cover is how are you thinking about future releases of Cos3D, if you think of any, beyond just the next thing, which will have like twice more objects, but more broadly? How are you thinking about that?
I think like a nice next release would be about deformable objects and trying to like somehow capture them or make workers capture them. We're sort of like working on this right now, and we would be very happy if this gets materialized into actual next release.
Got it. Okay, thanks. There's one more question on chat. Could you go into more details about how you model sequence to sequence for point features in NeRFormer?
Yeah, so basically the transformer is a standard, so these individual layers are standard transformer encoded layers. Yes, these are standard transformer encoded layers, which, you know, just you can import from PyTorch. What else can I say here? Yeah, basically the two-dimensional feature grid is just a bunch of sampled features from the individual source views. The features are again hypercolumn features, so there is again one more layer of learning before we actually sample the individual features. What is important to note here is that we couldn't actually use the standard transformer approach, which would basically take this 2D feature grid and just like flatten it into one list of features, which will be processed with the transformer. The main reason for that is that it would not just like fit in memory, so we had to split the attention into this remarching attention and the feature pooling dimension. There is one more detail which I omitted, which is basically that after we process the feature grid here in this part, we essentially have to somehow convert it into, let's say, one feature per point, and we do this by weighted average pooling. And then in the end, these average pooled features get converted into a bunch of colors and opacities, and then we use the standard NeRF emission absorption remark.
Makes sense. Okay, in the interest of time, we need to move on to the next talk, but there are more questions on chat. Please answer them in writing. Thanks again for the great talk.
Thank you.
Okay, our next guest is Iasonas Kokkinos. Iasonas is a research manager in SNAP, associate professor in the Department of Computer Science of University College London. Iasonas got his PhD from NTUA, did a postdoc at UCLA, and before joining UCL was a faculty at École Centrale in Paris. In industry, he started his journey in 2016 as a research scientist at Facebook AI Research, and then in 2018, he co-founded and served as CEO of Ariel AI, focusing on molecular human reconstruction for augmented reality. And in 2020, he joined SNAP following the acquisition of Ariel AI. So as we all know, Iasonas has lots of well-known research projects, including DeepLab, UberNet, DensePose. His current research interests are the intersection of computer vision, deep learning, augmented reality, and aiming at the development of real-time models that unify problems of 3D shape modeling and deep learning. So today, Iasonas will be talking about non-rigid 3D objects from Correspondence Self-Supervision. And Iasonas, please take it away. We can see your slides.
Thanks a lot for the intro, Natalia. Very happy to be presenting today in your workshop. Thanks for the invitation too. Today I will be presenting work aimed primarily on unsupervised 3D mesh reconstruction, as being aligned with the aims of the workshop. But I will look at it primarily from the perspective of what is required to make it ready for augmented reality. And this means practically that we're focused on techniques which are explicit, template-based, and we want also the resulting networks to be lightweight so that they can run on mobile. So this is, let's say, the particular point of view which can make the story. So I'll start by giving a bit the perspective from which I'm approaching the work. So we all know that augmented reality is here. So this is showing something that can already run on spectacles today. So this is showing how we can augment the world around us by overlaying computing on it on a rigid scene, which is already a compelling experience that you can see something beyond what is around you in the real world. And we were focused on doing this for the non-rigid world. And this was a few years ago, the whole grail. We were saying we want to be doing that on a phone. So this requires not just doing some structure for motion or slam, but also having some priors which would allow you to recover this non-rigid deforming body in real time. So this is something that back in 2018, which is when this particular journey started, was something that could only happen on high-end studios costing millions of dollars. And we wanted to make this happen on the phones and get all of the resulting use cases in AR unlocked. So this is how we started, saying that all of those things can be unlocked based on what was available in 2018. And we realized that we can have all of those sci-fi use cases actually happening on our phones in the very near future. So over 2 years with my co-founders in AI, we went full speed on making this happen. So this is showing where we were in 22. So you can see a real-time face, hand and body mesh reconstruction on a phone from a plain RGB stream. So there were a few CVPR, ICCV works around that, but the main thing was very solid engineering and careful development of the solutions. And now this is something that is already available to all of the hundreds of millions of Snapchatters out there. Okay, so you can see that this task of overlaying computing on the world is happening not just on rigid scenes now, but also on non-rigid scenes, and that means any user who has a smartphone. If you have Snapchat, you can try out these lenses, but now it's a commodity. So anyone who has Lens Studio and a decent mid or high-end phone can have this kind of augmented reality experiences happening for them. Okay, so you can see the kind of use cases, entertainment, overlaying or underlaying computing if you want to see this phone in particular, this lens in particular. All the kinds of animating your avatar in real time just on your phone are happening now. It's not somewhere on the future. And beyond, let's say, the entertainment use cases and all the cool stuff that you can do and get users excited now, there's also very clear practical use cases that allow you to stop trying to explain to your family and friends what computer vision is about. You can say, this is what is happening now. So you can do virtual try-on now. You can take assets from Farfetch or Prada and show them on yourselves. So we have all of the tools already available in Lens Studio for that. And this was a result of the work we did over 2 years on real-time human mesh reconstruction. I should say that if this is something that is getting you excited, practically having computer vision run on hundreds of millions of phones, please reach out to us because we're actively growing and hiring. Okay. So this is about humans. This is, I would say, the strongly supervised side of the problem. So the talk will be focused on what we can do for the less supervised. So, for humans, it's such an important use case that we can go all the way and gather detailed 3D supervision, learn sophisticated prior models. We can go all the way to make it happen. For a category like horses, it could be maybe not as important commercially, but the thing is that if you can do horses, you can do many other things in the weekly or unsupervised case. So there's another wealth of applications happening. And it's also very intriguing to see what is required to learn about the 3D structure of the world and have a machine learning models do it. So this is why I'm very excited about presenting today, because this is practically combining two cutting-edge problems, making things happen in augmented reality and doing it in the unsupervised way. So I should say that in connection with humans, the story so far has been that this is the case which is strongly supervised. The fact is that this is not entirely so. Even for humans, it's not easy to gather high detailed 3D scans. So to a very large extent, our work has been weakly supervised for that case as well. So the very first work in this direction was Correspondence, where we were using more easily accessible data like 2D key points, dense pose, or just 3D key points rather than 3D meshes in three ways: as auxiliary losses when training the mesh lifting networks, as weak supervision to provide mesh reprojection errors, and also an approach that we called refinement, which is taking all of the associated losses, let's say for 2D key point reprojection, dense pose reprojection, and so on, and optimizing over the parameters with respect to these losses. So this is effectively good old gradient descent, but through a deep learning module for a single example optimization. So this is, here you can see the difference of pre-optimization and post-optimization result. So this is very important because to a large extent what I'll be talking about is how we can optimize over 3D geometry in the weakly and the unsupervised case. Also for hands, again, we did a similar optimization to do training with weakly supervised data. So the idea is that you can easily get to the landmarks for hands with your favorite 2D hand skeleton system and use that to drive the fitting of a parametric model, and then use the results of fitting the parametric model to supervise your CNNs. Okay. So this is also the same story behind Spain, exemplar fine-tuning and many other works that are around today. So the main question is, how do you exploit optimization and all of those weak supervision losses in the case where you don't have this parametric prior to bailout? You don't have 3D scans used to pre-train your SNPL representation or your mana representation, and you just have 2D data. What can you do then? We know from classic computer vision that you can use SFM to recover 3D geometry without any 3D data, just from unstructured 2D photographs of the same rigid scene. And we also know that we can use non-rigid structural motion, again from classical geometry, to lift the video in 3D if you have dense point correspondence. So in both of these classical computer vision works, correspondence is the key to the 3D reconstruction task. So what I will be presenting today is how correspondence can be used in deep learning to improve the accuracy and also to facilitate the unsupervised learning of 3D meshes. So the agenda is what's shown here. You have an unstructured set of images, you feed that to some deep learning module, and then you have your parametric controllable model that allows you to express variability, account for camera, and so on. So there's three works that I will be touching upon. The one was presented in the previous ICCV 2 years ago, but it was the starting point for what I'll be presenting later. And then I will focus primarily on more recent work for unsupervised mesh reconstruction done in this lab. So the starting point for this work was my fascination with the deformable template paradigm and how to learn in the unsupervised way. So the idea is that you have all of those instances of a category, let's say your digit 3, and you want to somehow learn the underlying representation for it. How can you do that? What is the Platonic tree behind it? And then moving on a bit, you would want potentially to do the same thing for the whole category of faces. Okay, how can we learn what is a template for faces? So we started working in this direction with the deformable encoder work in 2018. So what we did was to have an image encoded through an appearance and the shape bottleneck. The appearance bottleneck synthesized the texture, hopefully in canonical coordinates, and the shape encoder synthesizes the deformation from the template to the image space. You warp the template to the image coordinates as detected by the shape decoder, and hopefully you reconstruct the image. I should say that there are many other works that were doing similar problems before, in particular, a line of works coming from Andrea Vedaldi's lab by James Tullis and many others. What was particular in here was that it was aimed at reconstructing the appearance. So it was in principle a full-blown generative modeling tool. So this ended up being possible by proper tuning of this architecture. And this is something which allowed us to learn our prototypical, our Platonic thread and its deformations, or our Platonic face and its deformations. Okay, so it was, if you want, dense pose or dense reg for free without any manual annotation. And so this is something that was already doing a surprisingly good job of face alignment in 2018. And what we set out to do afterwards was to turn this into a full-blown model for 3D face reconstruction. So this is something that we did by understanding that what the deforming autoencoder result delivers. So this showing the ISO contours of the UV of deforming autoencoder for this image. This showing the canonical template, and this showing the associated landmarks of the face on the original image coordinates. But we realized that we don't need to stick to just those 5 key points, which were used for evaluation. But instead, from this continuous UV map, we can get effectively a dense set of key points, as dense as we like, just by finding ISO contours in U and V for this UV map. So effectively, what our deforming autoencoders do is that they turn an image of a category into a representation that is abstracting the appearance information. So you just have a set of points across different instances of the same category, which are corresponding among themselves. Okay. So the exciting thing here is that you do not need a video of a single person to find correspondences. You have a whole category that is unstructured, so just individual 2D frames. You pass them through this process of disentangling appearance and shape. And then as a result, what you have is that this whole category, this whole data set of unstructured images comes with dense correspondence for it, which means that we can do the non-rigid structure for motion optimization as post-processing on top of this model. Okay. So this is what is shown here. You have your coordinates, your dense coordinates giving you a density projection loss. And you optimize that with respect to the cameras and with respect to the basis of your non-rigid SFM model. Okay, so if you do this alternating optimization over cameras and your non-rigid deformation space, what you get is a full-blown parametric model for the face category. That is disentangling camera pose, which is here, and expression and identity, which is represented in this space. Okay, so this could be how we would do lifting, just by post-processing the deforming autoencoder results. But we realize that we can have this as a single feed-forward architecture, where we have the image feeding into a network that is regressing the camera and the non-rigid branch, and then doing our standard deforming autoencoder job in here. So we have all of this pipeline as a single feed-forward line. Okay, so this is what we call a lifting autoencoder, as an extension of deforming autoencoders that is now able to do 3D lifting as well. Okay. And you can also latch a renderer on top of that, so you can see this as a full-blown generative models for image that is going through 3D without any proper 3D supervision, or 2D supervision for that matter. So this was, I think, happening simultaneously with the work of coming from coming from Paolo Favaro's lab back in 2019, and ever since there are many more works along the same lines. So this is showing what we can do with a model like that. So it's a full-blown model you can plug into a graphics pipeline. So you have the ability to re-illuminate because you have normals, so you can do spherical harmonics. You can manipulate expression because you have expression subspaces. You can manipulate pose because you have an explicit decoupling of camera and identity. So you can do all of those things you would be doing with a morphable model 25 years ago, but now without the need for any 3D scanning or any 3D supervision whatsoever, or 2D supervision as well. So it's all unsupervised. Now, the thing is that this was particular to faces, which are symmetric, which are a relatively easier category, and where we have tons of data. So the question that was really much more challenging and exciting is, can we extend this to work for all categories? And in particular, can we also do it for articulated categories? You don't have a linear, a simple linear space to bail you out, but you have non-rigid articulations where you may want to be doing something beyond just learning a linear shape basis. So these two works, I'll be talking about two works that have appeared in 21. So fast forward to today. Both of those works were with Philippos Kokkinos, who has been doing his PhD at UCL and is now graduating. So if you are searching for an excellent postdoc, you know, he's very soon on the job market. And what I'll be talking about is how we develop techniques which allowed us to capture articulation and increase the accuracy, while at the same time being with explicit template-based representations that would make it straightforward to deploy these models in augmented reality. So I should say that clearly this is a huge area of research today. The kind of works that have been making waves over the past few years are of the form shown here. You have an unstructured set of images, and then from those you want to learn a 3D, be able to perform 3D inference. So still, if you look at what these methods give, even the most sophisticated ones, and using, let's say, rigged models for articulated objects, they largely fail when the motion is highly articulated. So we want to have methods that really manage to deliver detailed articulated motion. So for this, we realized that video is an untapped source of supervision. And in particular, we realized that if you have an object that is moving in time, you can track its motion and use that to supervise your 3D lifting networks. So you do the same way we're doing offline optimization for 3D lifting of humans. Now we can do some offline optimization for 3D lifting of videos using optical flow and all the other tools. So this is the main story of this work, which I will be presenting now. So in particular, what we introduced in this work, which was published in CVPR21, is a very minimal deformable model. So all you need is a single scan of an object or a single 3D mesh of an object for the whole category, rather than a parametric model. So it's using a very simple energy-based prior that I will be detailing afterwards, which allows for a highly articulated deformation, as you're seeing here. So they're showing the result of the articulation. And then we also used source of weak supervision coming from mask video, which I will be detailing now. So starting with from the beginning, this is showing what would be mainly unsupervised mesh reconstruction work today. So you're saying, here's my input, I encoded, I estimate the camera, I estimate the texture, estimate the deformed mesh, and then reconstruct the image and use that to supervise my, to self-supervise my network. That's simple enough. So the very first thing I'll talk about is how to deform the mesh. So that's one of the contributions in this work. So for this, we realized that if we want to model articulated deformations, we may need to go a bit beyond the standard linear basis or morphable model, which is currently used in most works like UMR and many other works on unsupervised mesh reconstruction, and somehow use some prior knowledge that is coming from the template itself. Okay, so what we're using as prior knowledge is the curvature of the original template used as input. So what we have here is our single template provided to us. And what we're doing is that we're figuring out how to deform it. So this is what we call a control point or a handle at rest post. And this is where it is estimated to be by our network. And what is happening is that the mesh is deformed so that it follows our control points. So we're doing this only through a sparse set of control points, which are learned in an entirely unsupervised way. And the way we're doing this is by understanding that the standard Laplacian deformation problem from computational geometry, from geometry processing, can be seen as a structural layer for deep learning. So what we have here is a template mesh on which we know the Laplacian in advance. We have what we call a handle matrix, which is giving us the position of our control points as a function of a mesh, in particular here, the template mesh. And what our network is doing is that it is estimating a displacement of these handles. Okay, so what we're predicting is effectively n handles times 3 for their three-dimensional coordinates. So we're just regressing these positions. And then what we're doing is that we're solving an optimization problem that is saying, try to take and estimate a mesh V that will have a Laplacian that is not too far from the Laplacian of the template. And at the same time, we'll be able to regress the target handles if we take our estimate V and pass it through the handle matrix. Okay, and this is what we get as the result. Okay, the thing is that all of this process can be backpropagated through very efficiently. And this allows us to send gradient signals both to the CNN predictions and to also estimate the handle matrix. So these are to be interpreted as layer parameters. Okay. So we have a differentiable Laplacian deformation layer, which we use as a replacement for the standard linear basis model used to in other works. So one thing I should note, which is very interesting from a mathematical point of view, is that what we're doing is still a linear model, but our linear model is baking in some prior knowledge about the template. So this is shown here. We're showing that this is the Laplacian optimization problem I was talking about before. This is the condition at the minimum. And if you solve for V star, so if you invert this matrix, what you get is a constant matrix here. So you can see that this is the Laplacian of the template. This is the template. So all of this here is fixed. This quantity is estimated during training, but fixed at test time. And what we have here is a linear function of the handles. So at test time, we have effectively a linear model, if we want to see it like that. But in this matrix, we have lots of prior baked in from the template and the Laplacian. Okay, and here we're seeing what are the basis elements associated with each of the handles that were learned automatically. Okay, so we can see that we have effectively a process for rigging a mesh that does not require any manual supervision. So we learn these zones of influence over our template in an entirely unsupervised way. So this was a small parenthesis about our deformation model and how we can combine a sparse control point based representation with deep learning. And it is worth pointing out that this seems to be much more favorable in terms of accuracy when compared to all of the other techniques around, even if some manual rigging is involved. So you can see the kind of accuracy improvements we get in terms of intersection over union and PCK scores. So you can see even that with 8 control points, we have a substantial win over all the other techniques, and we can see that the more control points we put, the better this gets. Okay, and this just showing one case where we really recovered the twist of the bird with high accuracy. Now, the main part of the story for this paper is, however, the use of video supervision. And this is showing for a single video that we have in our training set, the kind of mask, optical flow, information we can extract with off-the-shelf networks, and the resulting 3D reconstruction we obtain. So we practically tap this very rich source of self-supervision and use it to improve our 3D reconstruction approach. The way we do this is by using flow and mask to obtain self-supervised losses. For the mask, it's kind of obvious. We're saying from this input, we can feed this into a semantic segmentation system. From our prediction, we have a mask loss. So we compare these two guys, and we have a self-supervised mask loss. So pretty straightforward. And combine this with appearance loss. For the optical flow-based signal, we need to somehow change how we're training our network. So what we're providing as input to the network is pairs of images. So these are consecutive frames. We pre-compute optical flow between them. So this gives us, for every pixel, an estimate of its displacement. And then we have our CNN give us one 3D reconstruction for this image and another 3D reconstruction for the consecutive image. And based on those two, we can estimate a mesh flow between these two meshes and compare it with the optical flow. So this is treated as ground truth because we can trust our optical flow networks to be doing a reasonably good job. And this is used to then supervise the camera and non-rigid deformation parts of our network. So this was really important for handling articulated objects because this gives you detailed information about how the limbs of the object should be moving, while also giving information about how the camera should be moving across the frame. So this was really disentangling you want the camera and the rigid from the non-rigid part of the motion, thanks to having a detailed per pixel supervision signal. So putting it all together, we have all of these losses to use during training. And now another thing that we're doing is that we do this optimization-based post-processing that we're doing also for the work within humans. Okay, so we're saying we have all of those losses. We train with these losses at training time, but at test time, we can also compute these losses because we have predictions for these individual components. So we can then go back and do an optimization with respect to the camera deformation and texture layers and further improve our reconstruction results. So this is test time optimization, which gives us one additional boost. So coming to how all of those things work together, we have an ablation showing the results of training with motion and also defining with motion at test time. So it's clear that each of those things gives an additional gain and they add up, so they're not doing the same thing. So these are complementary gains during training and test time. And then doing side-by-side comparison, we have very big improvement when comparing with other works, and in particular for the articulated categories. I should say that we are providing all of the video datasets because we think video is one really important source for supervision. So all of these code and datasets are publicly available through the project webpage. Okay, I think it's very interesting that we have accurate mesh reconstruction results, substantially better mesh reconstruction results, in particular when not having key point supervision. So this is the entirely unsupervised case, not human annotation is needed here. So this is just mask, effectively an off-the-shelf segmentation network, and motion coming from optical flow. So we're able to run this successfully on multiple categories and kind of articulate object. You can see that we're learning as our principal modes of deformation articulated motion. So you can say for a tiger that we get the motion of the leg, the front and the back legs disentangled, or the motion of these two legs disentangled from the motion of the back legs. So we have all of those things captured in the principal subspace of deformations computed from the training set. Okay, and now coming to some side-by-side results. Here we're seeing the results of ACSM, the articulation-aware canonical surface mapping, where some manual, not rigging, but some manual segmentation of the mesh was required. Still, we can see that this model hardly captures articulation, so it's very off when it comes to any challenging motion like this one. While we see that we're much better capturing this kind of drastic changes in the pose. Same kind of results here. You can see how accurately we capture the motion of the legs for a quickly moving object. So we can see that we're doing a much better job than other works aimed at articulated surface reconstruction. And some additional reconstruction results showing how agile the resulting model is and how easily it can capture large-scale articulated motion. Same kind of results here. Excuse me. And one last result of the same forum to show you the kind of articulated motion it can capture. So all of this is great. It means that we can really use minimal supervision, just a template and videos, and that's about it. Still, this is fairly challenging because firstly, it requires gathering videos, which come for free, but still figuring out what the right videos are, pre-processing, and all that comes with a pain. And the thing that is maybe the hidden secret of many of the existing works is that we rely on multiple cameras. So there are multiple camera hypotheses which are optimized over during training. So this is basically some redundancy in the optimization, which makes sure it doesn't go too wrong. But this is very far from something that would be used in augmented reality. We want one camera, one object, and making things simple for anyone who's using this model as a graphics object. Okay, so this is what we did in the follow-up work with Philippos. I think we've got 8 minutes. Is that right? Natalia, please correct me if I'm wrong.
No, we're actually a bit over time right now. So if you could wrap up in 3 minutes, it would be great. Thank you.
Really? So I'll be wrapping up very quickly. So it's 3 + 5 for questions or 3 period?
3 for the talk and 1 minute per question.
Okay, very quickly then, what we did with Philippos afterwards was to have a single camera, have a network that only predicts the positions of the projections of the mesh on the image. So effectively a 2D network that regresses 2D positions, and optimize over the camera and over the basis of a non-rigid SFM model during both training and testing. So effectively non-rigid SFM combined with deep learning. Again, same thing as 2 years ago, but now in a much more challenging case. So what we have here is one network that spits out UV, the positions of certain points on a mesh. And what we have here is a network that, an optimization process over the camera and the deformation based coefficients and the deformation base which is within the model. So this is a work we call to the point, because the point is to reproject back to these points in here. Okay, and this is in X21. So very briefly, what we're doing is alternating optimization over the camera and the deformation-based coefficients and the deformation basis itself, and then back propagating through the alternating optimization. And this is something that is substantially more accurate than competing approaches while using only one camera. While competing approaches use 5 cameras, or excuse me, 8 cameras, we only have 1 camera, no priors, and this can work across many different categories. And at the same time, do non-rigid deformations. Okay, so I would say these are the results that we're most excited about. I'll skip the ablations in the interest of time. Long story short is that you don't need too many iterations. 1 or 2 iterations are good enough, and these are super fast because they just optimize over camera and the low dimensional code. And in terms of quality comparisons, you can see that we have the ability to capture challenging twists for the neck. If you compare it with existing approaches, they see they entirely miss it, or the camera is just off. Okay, so you can see here the detail of the mesh that we were constructing, and comparing it to existing approaches, you can see that we're doing a much better job at recovering non-rigid deformations. And we also managed to make this work for many other categories, in particular for the Pascal 3D dataset. Where on the one hand, you can say this is maybe not as detailed as I would like it to be. It's not what an implicit network could give at its best, so we saw many exciting results coming out over the past few months. Still, this is explicit, requires no supervision, and can be directly plugged into an augmented reality application because it is template-based and creators understand how to use a representation like that. So this is really exciting in terms of where we can get with minimal or no supervision at all. So I should say that you're saying me, there is a big group of collaborators behind the works we did for humans and also for the unsupervised data reconstruction. In particular, Philippos did all of the work I was presenting in the last part of the talk and presenting CVPR 21 and NeRFs 21. And to conclude, I should say that these are very exciting times. We have work that was in CVPR 3 years ago, developing into some that is in the hands of hundreds of millions of users over 3 years. Things are moving very fast. This is the subliminal message of the horses and tigers running. So very soon we may expect to be having many more things in augmented reality on the phones of hundreds of millions or maybe billions of users one day. Okay, so if that excites you, keep a note that we're hiring and we're going very actively in this area. Thanks a lot for your attention.
Awesome. Thanks so much, Iasonas, for your talk. We really need to move to the next one. I'll just ask maybe one high-level question. So you said that you want to learn any articulated category from now on, but you're still using some priors on 3D geometries, at least at the category level. How are you thinking about doing like true generalization from here to any object?
To any object? You mean beyond the ones that can be expressed by an explicit template?
Yeah, I mean, I assume there are millions of object categories and probably you don't want to create 3D templates for each of them, right? So how do you think about scaling from here?
Yes, interesting. Lifting on the encoders had no prior, no template, no nothing. So we learned everything from scratch. So in principle, you can learn things just from data. And still, I would say if you want to handle categories, some do not lend themselves to the template, like tables or chairs. So I think the answer is somewhere in between explicit and implicit models. So there's work I'm doing with the PhD students at UCL now. Hopefully we'll have I'll have something more concrete to point to. But I think the answer is somewhere in between. Thanks.
Got it. Okay, thank you. Thank you once again. We need to move to our next talk, which will be from Niloy and Mitra. So Niloy is a professor at Niloy is a professor of geometry processing in the Department of Computer Science at UCL. He received his master's and PhD degrees in electrical engineering from Stanford University, advised by Leo Gabus and Mark Levoy, who was postdoctoral researcher with Helmut Pottmann at Technical University of Vienna. Niloy's current research focuses on shape analysis, data-driven geometry processing, computational fabrication. He is also especially interested in developing structure-aware representations and abstractions involved in 3D geometric data to help reason from raw images, videos, or scan data. And over the course of his career, Niloy received lots of best paper and career awards from Eurographics, BMBC, and SIGGRAPH. Today, Niloy will give a talk which is entitled Generative Models for Vector Graphics. We can see your slides. Please take it away. Thank you.
Thanks, Natalia. Can you hear me okay?
Yes.
Yeah, we start 10 minutes after. So how is it okay to go a bit over? Like I'm supposed to finish at 45.
Yeah, it's okay. Try to catch up, but we can go a bit over. Thank you.
Okay. Thanks everyone.
By the way, I think the slide is in presenter view. If you want to change it to.
Is it the way? How do I change this? Okay. Just check.
Yeah, there's a button up right, I think.
Yeah, I think I will switch the. Because it's sharing this window. Anyone knows it?
Hey, can you try to play the presentation again. I think there was maybe a button.
Okay. Yeah.
Yeah, that one more to the right where your mouse is. At the bottom, yeah.
Right. Yes. Yeah, okay, yeah. That was hidden for the Zoom. Yes. Okay. Thanks, Andrea. Okay. Good afternoon, everyone, or morning if you are in a different time zone, morning or evening. So today I'm going to once we can generate programs, as we'll see, we can also how artists typically create models. So in industrial design, they would start with sketching objects. And if we follow how the artists are taught to sketch, they start with drawing scaffolds and then shaping the objects by different sort of primitive operations. And many of the research in geometry processing where we try to extract abstraction is trying to find these types of primitives. If we look at the CAD modeling world, which is a computer-aided design, which is a method of choice for most designers, they're using a variety of operations. And if you have used Maya or if you've used Autodesk, it's calling through this various sequence of operations, calling a primitive, editing the primitive parameters, and in the end, we get a high-quality 3D geometry that is typically meshed out. That is a language that many of the fabrication models know how to use, so it can directly be sent to printers and others. This quickly gets quite crazy. So here's an example. You can look at it on YouTube, the actual video creation. So this is a 3D artist, an expert artist, really expert artist, creating this model. And this is a screenshot of he or she creating the model. And you can see it's extremely complex how they are modeling. In the end, we get this complex structure graph, which is a sequence of operations. So you are supposed to read these graphs from the left to right. So from the left, these are the operations, and the nodes denote how the operations sort of operate on the primitives they connect to. Right? So all this geometry can be seen as a program. So if we can recover the program, it would be really good because we can translate. So last year at SIGGRAPH Asia, we showed that it's possible to interpret sketch into these programs. So from the input on the column B, we can infer the programs as you see in the middle, and then we can read it out as the CAD model on the right. Now, but there's a huge restriction of our method because this is an interactive system, which means the user can model one of the red operations or the orange operations at the time. So this does not scale, and I'll explain why that's a problem. So this is an area that's getting a lot of attention now. So this year at SIGGRAPH 2021, Autodesk released this incredible Fusion 360 data set where each model comes as all the sequence of operations that generates these models. And now you can train your favorite sequence operator, whether it's RNN or a transformer, as David was talking about, to create these type of generative models that directly output instructions. And you can see some of our recent SIGGRAPH paper looking into this aspect. Now, to summarize, we would like to get programs from sketches or from 3D models, but in this talk, I will talk about 2D sketches because that's complicated enough. And we are not going to produce things on the left, but things as you see on the right. So essentially, we are going to output the program that would infer this. So this works to a good extent if we have training data. But what happens if we do not have enough training data? And that's the domain where we want to go, and that's the theme of this workshop. So the first thing is, where do we get our training data from, and in what form? Right. And here we would use our graphics knowledge because we know how the projection modules work, how the rendering modules work, how the procedural sort of functions work, and we'll try to differentiate through them. The second problem is more important, that even if we had outsource and manage to get a huge amount of training data in terms of procedures, the procedural models are not unique. By that, I mean different procedures can give rise to the same final shape. And that is a problem if we are trying to do a sequence to sequence model. It's possible to get around that problem, but it's better if we can do something differently. And then, as you will see, what is a good representation for these types of problems? Already in today's workshop, we saw sign distance field, we saw meshes, point clouds, and videos. So I've seen a variety of them, and not surprisingly, they would also come back here in this context. Okay. So the first one I will talk about is Im2Vec work that we presented at CVPR earlier this week. And the other one is a NeRFs 2021 paper that I will present. And both of them are done by Pradyumna, who's a PhD student in my group, along with collaborators from Adobe and UCL. Okay, so let's go into this problem. I really like patterns and at this fonts. So here's a sequence of like fonts, which are artwork on the left, icons, which are middle one, or even animation sequences, which is, I just unrolled it on the right. Right? So these are all vector fonts. Just to give a highlight of what we are expecting to do, we are expecting to output these type of results, which when seen through an interpreter of this language would produce a shape like this. Now to highlight how complex the problem can be, so for example, what would be the sequence or program for this? We would expect our method to output this language. Okay, so that's our goal. And already we see that the output that we expect to see is very sort of irregular in structure. Right? There's not a regular structure, so we have to get around that. Okay. I assume that we can solve the problem, and all the talk I will go through that, but let's see what we will expect to benefit. So if we want to interpolate in the latent space of programs, we would not get a result like this. So here, what we see here is a quality we would expect if we do an image-based representation, which is a pixel-based representation, and it is hard to have explicit control on the underlying structure. So we'll come back to these interpolation results later on using vectors or using programmatic approaches. Okay. So this is now, we are not the first to look into this problem. So there's a couple of very interesting relevant paper in this domain. One is this SVG VAE, another is this deep SVG that produces vectors or produces SVGs particularly, and which can support like arbitrary rescaling to a target resolution size. So all the nice advantages there. The problem is they require explicit training in terms of vector fonts. So all these fonts had their corresponding SVG operations available, and that's a problem we are trying to, or that's a requirement we are trying to avoid. Okay, so let's summarize what we expect our algorithm to achieve. We want it to perform well without having explicit vector supervision as input. But we do want the output to be vector or output to be programs, right? And what we also want is having an end-to-end trainable module so that we can supervise this, as we will see, with images. Right? And earlier, Andreas talked about the Platonic GAN, and when we worked on the Platonic GAN paper, that's when we realized that it's nice if we can supervise with different modality. In that case, we supervise with images, trying to recover 3D or voxel information. So we are continuing the theme here. So let's look at the architecture. I would focus on the most interesting parts of the architecture, but let me walk you from the left to right into the main modality. So the first one, and the main important part would come, which is the path decoder, but I'm jumping ahead of myself. So let's start with the main block. The first block is very standard, and each of you can come up with your own favorite way of doing it. We take an image, so this is a pixel image, and we want to encode and come up with the latent code, right? So you can have a convolutional approach to come up with the latent code or MLP even, so you can decide that. Because we have unknown number of segments explaining the final shape, so we don't know how many lines we will have in the SVG. For that, we would use a RNN-based approach. Okay, so this is a sequence. At that time, we used RNN. Now we might want to try the transformer approaches, but the relevance or the relations are quite local at this stage, so RNN might just be fine. And now let's go to the most interesting part, which is the key ingredient that makes it work, which is this path decoder module. Okay, so this would output vectors. Now, what this path decoder does is the following. So it takes a latent code, which is coming from the RNN, and this is, as you will see in the end, it's end-to-end supervised and end-to-end trainable, no supervision, sorry. So what we are trying to do is each of the curve segment, we assume it to be a deformation, unknown deformation of a circle. And the circle is, it's not like circle in the geometric sense, it's topologically a disk. That means it's connected back, it loops back into itself. And it can be filled, because we are talking about filled curves here. So in this, in the top one, you see the yellow blob. That's a closed sort of blob of a circle that has been deformed, the black one. And if you see a thin curve, that means it sort of loops back into itself. So it goes and comes back. Right? So that's how a circle can be deformed. So any of the closed curve can be deformed from a circle. And what the network is supposed to give is this deformation of these each point, right? So there are a couple of very interesting and important points happening here. One is the order of the points are going to be known, because that's how we sample the points. We would have some extra bits to denote if it's going to be looping back to itself. And the third point is, because it's a closed disk, we propose to use a circular convolution here, so that the neighborhood is kept aware of the ordering. And this output becomes the parameters of a Bezier path. I refer to the paper for the details of how we map the points into 4 points of the Bezier curve. Okay. Now, at this point, we have a vector output, but we have to compare with the image. Luckily, with the prior works we did, so we had a Segravation paper back in 2020, and at the same time, there was a paper by Lee and colleagues who produced a differential compositing block. Right? So all it does, it makes the composition differentiable. And the main ingredient there, it does a soft assignment there instead of an explicit raster one. So it blurs out that kernel, and that allows it to be end-to-end differentiable. Okay. And now this whole thing can be trained together. Right? So we can train on input raster images, and what it produces in the end is a latent code, which is this red or orange block here. That is the latent space where we can operate on. At the same time, it produces this individual segments, which are the vector output, as you will see here. The compositional block does not care about which line or which curve goes where. It only cares about the final one. So it's a bit like PointNet. It's oblivious to the ordering of the curves. Let's look at some of the results of this block of what we have here. So these were all trained of images with 128 by 128. And as you see on the lower one, the right ones, the blue and the green highlighted one, are our results. So you can see the reconstruction results. Because we output vectors, you can zoom in. And if you see the pixelated versions are if it's an image-based representation, or sorry, a zoom in of the original input image. But on the right is what we get because we have a vector output. So we can keep on going higher and higher in resolution, because we will just resample the output vector graphics. So that's good. So that's an even more zoomed up version of that. And let's look at how the interpolation starts to look here. And this gets quite interesting. So if we do an image VAE, that would be the top row, and ours will be the bottom row. Both are trained with images only. And if you see on the top, there are these pixelated or aliasing that gets carried through, and it looks quite reasonable though, but it doesn't look reasonable when you zoom in. You start to see the pixelation. With my graphics eye, it bothers me a lot. If you look at our output, so these 9, the way it is represented is by a big black sort of circle that has been deformed, and a blue, but actually it's white. I just show blue for clarity here, which is composited on top, right? So that's how it creates the hole in the middle. So it's a composition of 2 curves that you see here. Okay. Good. So this outputs 2 lines, and also along with which comes on top. That's given by the ordering of the composition block. Okay. Because it can be trained only with images, it can be used directly for MNIST. And Iasonas showed some results on MNIST datasets. So this is also trained on the MNIST dataset. And now you can see the advantage of having the vector, because you can zoom into this resolution. You know that MNIST dataset, the image sizes are particularly small. So the super resolution artifacts are a lot higher. Here are a few more examples for different fonts, as you will see here, and some of the artifacts you see with the jagged lines, we'll come back to that soon. Now, there are 2 nice sort of fallouts of our method. One is, because it's RNN-based, we can increase the complexity of the method by giving it more number of RNN blocks when we do the loop unrolling. Here, by going from 6 curves to 7 curves to 8 to maximum of 12 curves across the whole data set, and you can see that the network learns to add more and more details at the parts where it needs to, in this case, the horizontal line on the 7. The next one is particularly nice because we have a correspondence, because we have an order on the circle points, we get a correspondence for free across the data set. So it's unsupervised correspondence finding, and the color or the gradient of the color denotes correspondence as you go along the row, each of the row, whether it's fonts or emojis and others. There's a couple of limitations. One is because it's supervised with pixel information, we can sometimes miss small parts. Here, the inside of the 4 is particularly important semantically, but it's missed in the output. Or if we have very complex topology, here the 6 doesn't quite touch in the input. So we can't represent this anymore as a composition of 2 closed curves. Here, it could not find and the right reconstruction and causes some problems. And this topology problem is what inspired us to go to this next paper, which got accepted now for NeRFs, which is this multi-implicit neural representation. And it has a couple of really nice insights that I want to talk about today in the remaining time. Okay, so if we look at fonts, so now we are not looking at emojis, we're just looking at fonts. Right? If you look at font families, there are a lot of font artists whose whole life's work is coming up with fonts. And they have a couple of interesting criteria, and we have all used fonts in our daily life. So one is we have these fonts which have a lot of character, as you see here. But then if we look across the fonts, there's a lot of style variation. So if we look at the highlighted A here, if you look between the first and the last one, I think the French and the third one is a Gothic one, there's an incredible stylistic variation in how A is represented, but also how many curves are there, what are the type of corners, what are the type of things. And in our vision world, this would be what would be a right template that would represent all these fonts here. Just to slow down here, please recall that our goal is to come up with these programs, and we want to come up with these methods that would eventually translate to 3D. And that's why we want to pick a problem domain which we expect the methods will translate to 3D when we go there. And in terms of programs, this is our vision that that's what will happen. The other thing is, although there is a lot of variation across the different styles, inside the same sort of characters, the fonts are consistent. So if you look at the French style, the highlighted green one, they all have the same style, the same with Italian, and the same with Gothic. And that's our notion of font families, right? And our goal is, can we identify these sort of decoupling of the type, which is which character it is, A, B, or C, versus the style, which is the name of the font family, right? Can we learn this directly in a network? So that's our goal. Okay. And like before, this would allow us to go in increasing resolution without having aliasing artifact. That should be understood quite easily by now. The output would again be a collection of splines. And we would not go into how this would compare to raster-based methods, which was the image VAE that I presented early on. We saw the artifacts. Let's just quickly recap the vector weights alternatives. So the resolution independence we already achieved before, and also the SVG VAE and the SVG had it. However, as we saw in Im2Vec, we could not handle very complicated fonts. So we could not handle the Gothic font, we could not handle the 6 and other things, right? So that's what we want to address in this work. Right? So what is this multi-implicit? So let me talk about that multi-implicit. The goal is threefold, that we want a method that allows to generate programs for complex shapes or complex fonts in this case. So you can zoom in arbitrarily. It allows to capture sharp features. So let's quickly go over the type of sharp features so that we are all on the same page of the complexity of the problem. So one of the sharp features where it transitions from black and white, that's fairly clear. But another one is the type of these corners. And these are quite diverse, as we saw when we go across font families. We can have very different corners. And what is a good representation that would allow us to have corners? Okay, and then we want to work with minimal supervision, and I'll talk about what this minimal supervision would be. Okay. So what we start with is the following, that this is architecture, but I will break it down into the most important part that we want to look at. So this is the part which is the key module, and the key sub-module of that is the corner template. But let's first talk about the multi-SDF and the corner template. These are related. So what is a SDF? SDF would be a sign distance field, but in the context of fonts, and I'll talk about that. And the other modules are the standard sort of gradient loss we will have on the L2 regularization and the shape loss. So these are quite standard. You can have a VAE, then you would have a normal or a KL divergence on the Z term also. That's a standard detail here. Okay. So here, what we are going to work on are sign distance field of the font. So instead of a mesh here, we have a font boundary, which is denoted by this white line. And then we have a SDF around that white, both inside and outside. Okay. And this can be resampled at arbitrary resolution. Again, that's an advantage we had before. So this is fine. But when we pass the gradient, what we observed is that it doesn't get, like for point samples close to the 0 level set or close to the white iso surface or iso curve on the left, the gradients get very hard to propagate. So what we did in this case is, instead of working on these SDF fields, we worked on these anti-aliased SDF fields. And the interesting part here is we used a known anti-aliasing kernel or a filter kernel. So it's very similar if you make the connection that when we looked at the Platonic GAN or we look at the block GAN or holoGAN, there was a known camera module that was fixed through which we backpropagate. In this case, this rendering module or the camera module becomes the anti-aliasing module, and that's known and fixed because that's the imaging module we are used. And when we pass the gradient, it sort of collectively gets information from quite a few neighboring pixels at the same time without us having to consider SDF values very far from the zero level set. So this really speeds up the convergence. For the exact kernel choice, we looked up some old literature from graphics to find standard modules there. But that's a fixed module. That's not optimized for. And then we are fine to only do importance sampling or get more samples from near the zero level set. So we don't have to sample from the black regions, right? So it really speeds up convergence. And if you look at deep SDF and other works, there's the same idea of sampling near the zero level sets, because that's what we care about. But with this additional anti-aliasing term, the gradients gets a nice, better behaved. There is another problem. So that's the SDF aspect of the problem, but now we go to the multi-SDF. But first, let me talk about the problem. The problem is if we work with these SDF images, when we get to the corners, then the aliasing effect starts to dominate. And that means that the learned vector graphics would have a lot of wiggly lines that would represent the images, but not actually the programs that we are trying to output. So here's quite a clever trick that I really like. So what we do is, instead of outputting a final SDF, we output simple SDF. That means we are saying complex SDF can be expressed as a combination of simple SDFs. And what is simple SDF? SDF coming from simple curves. So in the left, there's two simple curves, the two black curves, curve 1 and curve 2. And then the quadrant 4 or Q4 on the right can be expressed as a composition of these two SDF with the right sort of sign choice, what's plus and minus. And this type of sharp corners can be supervised, or can be, the loss function only needs to look at it locally, which is a huge advantage, as we will see soon. So to summarize this part, we can represent corners, which are complex SDF, as superposition of simple SDF. Again, the SDFs are not supervised in the sense that the user doesn't have to provide the SDFs, the algorithm will infer, or the network will infer these SDFs. Okay, I think this would make it clear. So here's on the left is a font F, on the right is a reconstruction F, as you will see here. I'm just trying to calculate the time, how much extra I have. I think I should be done in 5 minutes. So if you look at input and reconstruction, this looks pretty sharp, and it continues to look sharp as you go up in resolution. Now, the real question is, what did the network find in terms of this individual SDF? And let's look at that, right? Or I'll give you a few seconds to imagine how you would represent these Fs as composition of simple SDFs, or simple curves. It shouldn't be quite obvious, because I'll be disappointed if it is. So these are the individual curves, or these are the, after we take out the isosurface, this is what the network finds. And because we have the composition with the right signs, this is what it gets. So now you see, although the individual curves look quite chaotic, when you look at the combined one, we start to see what's really happening. Around the corners, it does its crazy things, but it has the right sort of mix of plus and minus to get the corner sharply, right? And this was not, so now try to imagine that if we had to get this individual curves as supervision signal, I would not know how to even collect such a data set, right? But this we can do directly with direct only corner level supervision. Corner level means we have a corner detector that tells to zoom in the corner part, and then the network finds out what are the individual curves and what is the combination modules of the correct plus and minus to get the right shape. Right? And this is a very, very clever sort of way of setting up the problem that Pradyumna came up with, that I really like, and it works quite well, as you will see here. Okay. In terms of the other things, these are quite standard. I would not go too much into that details, except for the gradient loss, because the individual SDFs are, or these are SDFs, so you can have an iconal loss on the gradient that it is indeed a distance field, but that's a technical detail. Okay, let's see the result. Does it really do what it promises to do? So the second column is image VAE. Deep SVG result is there. Im2vec is what I presented in the first half of the talk, hours as you see here. And this continues to be nice as we go forward. So the pink zoom is the multi-SDF method, or the multi-implicit method I just presented. Okay. Let's look at some interpolation results. So now it gets really crazy, and these are quite crazy fonts we found. So if you do Im2vec, which is the method I described in the first one, then the latent space for these crazy signals, it's really difficult for it to find something reasonable. And this is why we went to the multi-implicit form. Here it gets a reasonable output. And if you look at the zooms of the endpoints, again, the bottom row, the pink are the outputs of this multi-implicit one. It does reconstruct the corners quite nicely. With the supervision that we discussed. Right. Now we can do our standard tricks we do with GANs, so or a generative setup. So we have a generative setup. Now, given an input glyph, which is one font, can we find the rest of it? And I think to this audience, I don't have to explain this much. So what we need to find is we freeze the network and optimize for the latent code that will match this. So we need to know that this is the letter A. So we look for a latent code Z, fixing the network that minimizes the loss. And if we do one step or a few gradient steps, this becomes nice. And now we have a particular Z, which is a Z star, and that then I can take and read out the output for the other fonts like B, C, D, etc. So this allows to take a single one and reconstruct the font, right, for this one, which is particularly advantageous, and something we at Adobe also quite like, because part of our business is to work with fonts. They keep vector output. These are snaps from the paper, so they are pixelated, but actually the output is vector, so it's not pixelated if you had looked at the program. You can also do with a partial one. So it's a partial input. It's the same problem with mask. So there's nothing surprising. It still continues to work quite nicely. And we get the sharp corners. The sharp corners are coming from the underlying latent space and the multi-implicit formulation we have. Because it's only works with this local supervision around corners, it can have some spikes if we go to ridiculous zoom. So this is after you zoom at very high amount of zoom, you would start to see some spikes. And on the right, you see the overlay of the multi-implicits. At a similar failing, we can have these slightly wobbly one, again, if we go at very high resolution. Okay, so that brings to the end of the talk here. I try to make up for some of the time. So the main agenda here is to work with a data set where we have a lot of access, in this case, images, and to output programs, which is what we see in the middle. And in the process, we had to design the network, but in the end, as a reward, we get nicer interpolation behavior, because now we are restricted to the interpolations in this language space, which means all these interpolations, say, removes cubic splines or removes like operations that are available in the SVG library. So in a strange way, that the whole approach is regularized by the choice of languages or the choice of operations we have. In the modeling scenario, this would be the choice of CAD operations we have, and that's something we are working on. And hopefully we'll be able to present results in the 3D context later this year. So with all the code available, both for the first work, the Im2vec, and also this multi-implicits is available on the GitHub page. And the papers are available on our geometry website at UCL, and I'll be happy to take any questions at this stage. Thank you.
Thank you, Niloy. Great talk. I also love how it's a little bit different from the mainstream line of research we've ever heard about so far. We need to go to the panel, but before we do that, maybe just to reconnect back to the topic of our workshop, could you reiterate on your longer term vision, how you think about extending this methodology to, I don't know, modeling, like full 3D modeling, maybe even articulated objects, rigs, blend shapes? Like, do you even think that that's the right way to do it?
So we have the results, but I can't show you because it's not out here. So this is how the change would be. So in the CAD sequence, so whether the input is an image sketch or a 3D sort of scan, the inferred one, the third column would be the output, which is the program again, right? And so the part that needs to be changed is a compositional model. So it's not going to be 2D rasterized anymore. It has to be like in 3D. We are not working through a camera module. So the eventual longer term goal would be that we don't even have 3D models to work with, but we work with like images of that, but that even links to linking with the Platonic GAN work we have done earlier on. I think that's too far in the future. For now, I'll be really happy if we can work with 3D models without part supervision to come up with corresponding CAD sequences that can produce these ones. So, without having supervision on the CAD instructions. Right. So I think that without the supervision of CAD instruction is the critical part.
Got it. Okay, thank you so much. Thank you for the great talk. Let's now move to the panel. We have about 25 minutes left. Andrea will host the next bit. So Andrea, please take it away.
Yes, indeed. So I suggest maybe also take some more general questions from the audience, if anyone has any, that the speakers might be able to answer. So please type them in Zoom as you've done so far. Right, now let's see. So to get this one started, as people gather their thoughts, then so just inspired by your presentation that I thought was very interesting. So at the moment we are focusing a lot, at least in the vision side of things, in reconstructing 3D shapes, meaning we want to get something like 3D mesh, basically an idea of the surface of the object, maybe also the appearance, that would be the BRDF. But there's much more that we can understand. We should be understanding about objects. There is like the concept of part. There is the concept of category. So, how these things connect through many different object instances. Then there is a notion of dynamics, which we didn't discuss almost at all. I mean, there were some papers that show that at the level of deforming a mesh, but that wasn't explained in terms of, I don't know, skeletal structures, for example, or, muscle control or anything like that. So there isn't really a very deep understanding of these dynamics either. But what you showed here was some work that was trying to parse an image or into a set of primitives in a way, right? But those primitives, they do not appear to be very semantic yet, not very meaningful to a human necessarily. So how do you guys feel about moving to the next level beyond just understanding 3D shape in a shallow manner? Maybe going to understand also the 3D structure and the physicality of the objects in terms of parts and some sensible decomposition of the object in something that actually makes sense.
I think this is a really interesting question, and one that we have in our long-term agenda. So if we think of the sequence of operations, right, and if we start taking snapshots when users are modeling it, so we don't have the final shape, we have the progression of the models as people are creating the models. I think that gives a sort of a semantic association of how the parts are growing or how the parts are attached to previous ones. So there is also a temporal aspect of this, of how, not the dynamic of the parts, but how the parts are attached. And most of the semantic justification would be the core parts are introduced first, and then the details are formed, and how and capturing the correlation of the parts would be a nice aspect to have.
So correlation between, so you mean statistical correlation?
Statistical correlation, yeah. right? How the parts are connected. Like if taking, say, Iasonas' example that he was saying, like if you have animals, the body size is certain size and proportion, then the legs or the limbs that are getting attached to that has a certain relation with respect to the primary body and where they're located in terms of both the number of the limbs as well as the proportion and size of it. I think we're quite far from that. First step would be the dynamics of it before we talk about the evolving of the parts.
Okay, anyone else wants to say something about parts and structure in the objects? Not really. Okay. All right. I don't. By the way, so I still don't see any question in Zoom. So if the audience would like to type some questions, that's now would be the time to do that. Right. So moving on then. So one issue is that well, a lot of the work that we're doing, not all of it, but especially when it comes to deformable objects like animals, horses, and complex things like that, where you can have a complex set of deformations, they still seem to require some form of initializations, which is manually guided at least at some level. Now, Iasonas, you were saying before that you can do your modeling without having a manual input, I guess. But my understanding is that at the moment, you're still at least basing your work on some sort of initial template. Is that right?
It's right. Still, I think that there was a very interesting work in CVPR21 and now in NeRFs21 coming from CMU, from Deva Ramanan's group and Jengsan, I think, which was about taking a video and lifting it in terms of an articulated
laser.
Laser, yes, laser, and now it's visor. So
yes.
This is prior free just starting from a Gaussian, but then branches off into more Gaussian, so it's like effectively learning it all from scratch and handling articulations and challenging motions. So I think this is very exciting in the sense that we can say this could be used to learn categories too. So and also from classical non-rigid SFM, you can very well do it without any template.
Excuse me, what can you?
I mean, from classical non-rigid SFM, as soon as you have dense correspondence, you can learn it without a template.
Yes.
It's in principle, it's very well doable.
But in that case, you will need a dense post for initialization. So how much can you get unsupervised, and how important do you feel that is? So we tend to use a little bit of supervision, for example, at the very least in terms of getting a segmentation of the object in the image. Again, not all the works do that, but most of them do, right? There is a baseline level of supervision, maybe 2D supervision, not 3D supervision we're injecting into the reconstruction process. How do you think we can get rid of that? How do you think that's very challenging? Is that important to do, or it's just wasting time trying to do that?
I think practically what we're all doing is taking what we know from computer vision, using it as self-supervision. So if we know how to do video processing, or we know how to do classic geometry, and we're saying let's use it as a DOS. So in that sense, the more we can exploit from vision, the better. So let's say these techniques effectively use supervision in the form of asking you to have a video, which is something beyond the minimal thing of just throwing images at it.
Right.
So the more we can put in without, I think the balance is how much effort is required on the computer vision side to do it versus what is the improvement you get in your models. So if you go out of your way to get some computer vision thing to get a marginal improvement, it's maybe not worth it.
Okay, that's a very practical way of looking at it, but in principle, so as scientists, do you think that removing supervision is an interesting problem?
Maybe it's just maybe it's just me, but Iasonas, I'm having a hard time following your audio. Maybe you can speak closer to the microphone. It's been also like
maybe better now.
Your talk.
Yeah.
Sorry about this.
It's better now.
Yes, it is better.
So I'd actually want to add on top of that. So for example, when you talk about the template, I think the traditional notion of template has changed to some extent. For example, if you view NeRF, right, as a representation, And to some extent, IVRNet will serve as a template to some extent, because if you pre-train a network, right, that adapts to different models, then for new models that resemble similarity, it actually serves as a de facto template. So our recent experience is that we have some very interesting experiments. For example, if we pre-train an IVRNet for different, human performing different, actions, then you pre-train that, and then use that as the IVRNet, and then you have a new set of performers, and you will find that actually you can benefit tremendously from your pre-trained IVRNet for both reconstruction and the view interpolation. So this is one thing I think, potentially in the future can benefit from quote unquote templates. There are other interesting things. For example, pose itself can serve as a template, meaning that if you have some kind of like a quote unquote pose net, you've seen different poses before, then you can actually use that to very quickly determine the pose of in the, for example, SFM settings. So in other words, my feeling is that, especially with respect to, human, 3D reconstruction, is that actually the notion of template is, migrating towards a neural template than the traditional sense. Actually, on the contrary, I find it increasingly challenging to incorporate traditional, physical-based or stereo-based constraints into the network versus an implicit way of doing that.
Okay, that's very interesting. So, do you guys agree that we are losing the semanticity, or if you like, the interpretability of these templates or priors we inject into these models? And is that a good thing or a bad thing? Yeah, please.
I think for some things it's we should. My belief is it's not good to give the network extra freedom that we need to. Like for something like the camera model, if we know it, we should have that as a base model, and at best give it a residue on top of that. But something like was mentioned, like there's a lot of ambiguity in the image formation model, because going from 3D to 2D. So we definitely lose certain things. If we are doing a single image reconstruction, for example, then there has to be a supervision in some form. Right? So I think we might want to distinguish between, is it the supervision in terms of annotation data, or is it supervision in terms of maybe some object detection level, or someone has grouped the objects like these are all objects of humans or an alien creature, etc. But it seems hard for a network or any method for that matter to generalize from human to a completely different organism that has like an entirely different structure. What does even generalization mean there? Yeah.
So how are we going to understand every animal in the world in 3D? Or as a matter of fact, any object in 3D? Like David has this data set of 50 categories, which is great, but 50 is less than many millions of categories that are out there probably, or at least hundreds of thousands, right? So how do we scale this up to understanding?
I think just to say that, because something David very specifically made a point, that even the choice of 50, which 50 would determine, because Kokkinos segmentation was pre-trained on that and available, that's how we picked this 50, right? So it's not like 50 random objects. So there are things that, as you said, the bootstrapping would become a challenge. And we need one more loop to go out of that.
I see.
Yes, also. Yes,
it's true that to some extent we have to challenge the notion of the object category by itself, right? What is actually object category? Is it just something which we can reconstruct? Is it something which is grouped somehow based on semanticity, things like this, right? So I don't know. My intuition is that we can learn like very high level priors on the reconstruction, but I wouldn't really necessarily make them completely like tied to categories themselves, because I think with time we will basically run out of the reconstructible categories, although you would still be able to reconstruct other things. So it seems like quite restrictive to, in my opinion. Yeah.
Okay, that's an interesting point. So we could just get rid of the concept of categories, and then we will be done. That's actually.
Well, no, I'm not saying completely. No, like I mean,
sure, you can use it to like initialize the reconstruction pipelines and stuff like that, right? But like with time, you will find out. Or actually, what I found out from the experiments is that these things always learn very like, generic reconstruction like priors. They don't really learn anything about the category very well. For instance, the IBR net is a good example. We have been speaking about this here. It's literally like a multi-view stereo machine. It doesn't really learn anything about like a object category, even if you deploy it on a category-specific data set. It's very low-level thing. I feel like most of these like category-centric constructors actually latch on very low-level like cues. So yeah, but I agree that the notion of the object category, for instance, helps you to, let's say, focus on one object in the scene, and then like it gives you these like nice constraints, so like a multi-view, like a reconstruction, signal, which is very hard to achieve in like unconstrained scenes.
Okay, thank you. Anyone else wants to interject on this question?
Yeah, I just want to say that, understand this maybe general, like it depends on what we want to do afterwards, right? So one thing is reconstructing 3D, but let's say for anything like humans in particular, or anything you would want to insert in a downstream task like augmented reality, you need to have things which are interpretable so they can be used. So if it doesn't come with a template, you cannot have creators or anyone who's coming from the graphics background try to wrap their head around an implicit model or anything like that. So it's already hard enough with articulated objects, with templates for articulated objects.
So you're saying that just the application itself means and implies that you're going to have some sort of template at some level. It's just because the reason why you're doing this, the performing reconstruction already has embedded a notion of template, like for example, the need for manipulation.
Yes, I think it's the same kind of questions you have for segmentation. Like, can we do segmentation? So it's largely task specific. So the kind of 3D understanding we want to do may be largely determined by the domain in which we want to do it.
Okay, the same. All right, anyone else on the question of scalability? Okay, if not, I can move to maybe another question. So Andreas, there's something you said before that struck me actually. So you said that you are very focused in improving the quality of the rendering now, as opposed to, I don't know, understanding, developing an autoencoder architecture so you can parse an image instead. So there is this sort of, well, I wouldn't say a trade-off, but maybe a different focus. One could be just, let's improve the rendering quality so we get really, really nice images, which almost feels like a computer graphics task. And then there is a computer vision task, which is understanding the images means performing good 3D reconstruction, maybe understanding the structure, the semantics, etc. So how do you guys feel these things are connected? Is it really important to get pixel perfect reconstructions to be able to get solid semantic reconstruction, or can we develop these two things somewhat independently?
Well, that's a good question. I think what is striking to me is that like taking independently 2D generative models are pretty capable of fooling humans. And also, if you have the right scene, it doesn't work for all the scenes, but if you have the right scene, then novel view synthesis methods also work quite well. In some scenarios, they don't work well. So we tried, for example, we tried NeRF on Kitty, and it doesn't work very well. But if you have the right scene, it gives you photorealistic results. And so it's a little bit striking to us why bridging this gap is so hard. And so that's, I think, in theory, it should be possible. The question is, do you need it? I think this was behind your question. I think it also depends on the application, right? So you like we are. So I'm personally interested in building simulators, and the question is also for simulators, does it need to be photorealistic? I think simulators can operate at all kinds of levels of abstractions, but one level of abstraction that you also, I think, will need in the end is a photorealistic level of abstraction, and for this I think you need to have this. And my experience with things like novel view synthesis is that if you can't get the geometry exactly right and the scene is non-trivial, then the novel view synthesis will also not work. So basically, the reconstruction loss, the RGB reconstruction loss, is quite a decent proxy actually to how good your reconstruction is and vice versa. So I mean, for non-trivial scenes, if you have a trivial scene like something planar or something very simple, then of course this doesn't hold. But as soon as the scene becomes like very complicated, where you have like, look at a fence or something with very intricate structure and occlusion relationships, then things really start to matter. And but I agree. I mean, it depends on what you want to do with it in the end, right? So maybe one comment to the previous discussion. I mean, most of what I would have said has been said already, but I also feel like we need to, of course, get away from this object-centric reconstruction. I mean, for example, for single image depth prediction, this is happening, right? You can, if you look at scenes, general scenes, you can't even identify all the objects. Sometimes an object is not clearly defined. It's not clearly defined if something is belonging to the stuff category or is belonging to the object category. We had a lot of trouble actually annotating our data sets because there can be buildings with vegetation on it, and there can be vegetation that's standalone, that's more like an instance, and there can be all kinds of intermediate things. And so it feels a little bit artificial to actually define this. And the question is, do we actually need to define all of this? I'm wondering.
So we are abolishing categories and objects today. So a good 20 minutes, I think, of research, right?
Well, I mean, maybe we don't need to abolish it, but ideally it would come automatically, right? Ideally, we don't have to define it ourselves, but it would be defined based on a downstream task in an unsupervised way from the method side, right? Not from us as engineers, I would feel.
Yes.
I actually echo Andre's comments actually. So our group has also tried very hard to apply NeRF to outdoor scenes, but not that successful. So we actually observed the exact phenomena as you just discussed. And my speculation to some extent is that the NeRF tends to overfit, to the images. And as a result, the sampled views actually do look pretty reasonable. But especially in the sparse settings, we figured that actually the geometry reconstruction or view interpolation, can be a disaster if you only have a sparse settings. So my students, have this interesting speculation that saying, it's always a balance between geometry reconstruction and view synthesis or rendering. So in other words, if your emphasis too much on the rendering part, actually, there's a possibility your geometry will degrade, as you improve appearance, if you use just appearance loss, So this is a phenomenon we observed, even beyond outdoor things. We actually tried that on something called a PROW-ET image. It's a bio image, and we observed the exact same phenomena. The better rendering you get or meeting fitting, on the sampled views, it turns out because under sparse settings, then we observe the geometry reconstruction gets even worse. So I don't know how to, mitigate the problem. Maybe Andreas knows better about it, but I echo your point, on what's going on. Another interesting thing is that I think, semantic meanings is really useful in generation tasks, but in the reconstruction task, as you mentioned, it's kind of tricky because how do you define semantics? In the generation task, it's very clear, right? Because you are given a semantic map, then you synthesize, multi-view images, blah, blah, blah. But in the reconstruction setup, it's getting much more vague. So, and more challenging speaking, when you have a dynamic objects, then how do you actually maintain the same semantic meanings across deformations, which it seems to be very, very difficult, especially in the NeRF-based reconstruction tasks. So these are just my 2 cents.
Okay, no, that's great. Thank you. Thank you very much. So we only have maybe 1 minute left, I think, indeed, exactly 1 minute. So is there anyone else that wants to, that's your last chance for a comment, I guess. So
I think I think it's okay if we run over a few minutes, but in case if anyone wants to leave, I think it's fine, but we can extend this for a few minutes.
Okay. So, well, I
think maybe before jumping to conclusion too fast, like about photorealism and the geometry trade-off, that I think I also agree there is a trade-off there. Sometimes we should also revisit the model we are using. So in the amazing work Andreas showed on giraffe and also graph, there are object-to-object interactions. So when we stand, there is a shadow on the ground, right? And that this is a very simple one. If you do outdoor, I would imagine like someone taking the picture would cast a shadow. I think in the example that David showed of this yellow hydrant, there was a shadow of the person on top of the hydrant as he or she was capturing. And this is not captured in the model, but it's there in the photo, what we have observed. So even if the model, either we have to improve the model or we need another step in the algorithm, in the inductive bias to model this as outlier. So there's a trade-off of increasing the set of assumptions on the scene versus how much we can handle at optimization time.
I think I also want to add a point. I think there's a missing bridge between geometry and appearance. Like if we have if we can complete the bridge, like all the appearance results from the geometry, right? All the shading effects, like specularity, like if we can actually model all these appearance effects, I think ultimately this should also benefit for the geometry reconstruction. It's just all these effects, they're like extremely hard to model unless we're using like Lambertian assumptions, which are probably like it's the best model we can use at the moment, or foam models. I think this is like something that's missing to bridge the gap between geometry and appearance.
You mean better illumination model, better reflectance models?
It's hard to model all these like shading effects, but if we can like model it better, it should be like all these appearance should give us much more information about the geometry itself as well.
So I think you're right. You know, I will add on top of that. You know, again with our own experience. You know, I think whenever we talk about shading and materials, right? It's very closely related to normals. So then this is actually when you talk about the gap, right? Then I think I call it a normal gap, meaning that under the, for example, the NeRF setting, it's essentially a density field, right? It's a volumetric reconstruction. So you can use, for example, SDF, which is one way of kind of extracting the normals. But essentially, it's if you view it as a level set, right? So how do you extract different level sets and its corresponding normals? There still remains an open problem. So when you say you want to make this gap, you want to bridge a gap, essentially, I think we need to first bridge a gap between density field and the normal field. I think this is the first urgent task to accomplish. These are just my very biased views.
My intuition behind like better material models is that you are giving actually the model a lot of chances to cheat by producing all these like different peculiarities and reflections and stuff like this, right? So I would agree that definitely like a good material decomposition is extremely important. At the same time, regularizing material decomposition so that the model doesn't present like specularity with some kind of a change of color, local or something like that. That's extremely hard, right? So people have to be very careful in that case. Yeah? And adding on top of that point between like a correlation between the appearance and geometric performance, I would definitely say that the correlation was pretty obvious in our experiments on the Kokkinos dataset. Really across all the baselines, we found out that the depth reproduction accuracy was perfectly correlated with the accuracy of the generated color. So it really seems that the models really have to understand geometry perfectly.
Okay, great. Now we have, we can stick it for a while, but we're probably a bit out of time now. So we should probably take this to a close. There will be a second panel later. So if you guys want to stick around, you can come back in 6 hours or so and say some comment a little bit more. But otherwise, thank you very much for participating in the workshop. So far, it has been fantastic, I think. And thank you for your contribution. And I hope to see you at least among the audience in the next few sessions. We're gonna start again in what's that? 3 hours, I believe. Is that right, Shangze?
Yes. In less than 3 hours, I think, or a little bit more.
Anyway, you can see the schedule on the website, and in the meantime, we're gonna put a slide here in Zoom giving you the pointer, so you can refresh your memory. All right, thank you very much. Goodbye.
Thank you, everyone. We have 2.5 hours break, and during the break, you can go to the ICCV platform and join the gallery social link. I haven't tried it myself, but I guess you can find it on the ICCV platform, conference platform. So see you guys in 2.5 hours. Have a nice break. Bye.
about now?
Okay, I think we're back. All right, Paulo will be hosting this session. Paulo, you can take over.
Thanks, Shanse, and it's my pleasure to introduce our first speaker, Jitendra Malik. And before, I would like to remind all that the talk is live streamed on YouTube and recorded. And also, I would like to remind all the presenters that in the interest of time, we should keep the talk within the 30 minutes so that we have some 5 minutes for questions. First of all, I would like to wish Jitendra a happy birthday. I heard that today is your birthday. I hope it's correct.
Thank you. Thank you.
And I should also mention that Jitendra is technically my academic grandfather. Since I graduated with Stefano Soato, and he came from graduation from Pietro Perona, and so that's my link. He is a professor in EECE at the University of California, Berkeley, and in 2018 and 19 he served as a research director and site lead of Facebook AI research in Menlo Park. His work has strongly influenced the computer vision and machine learning community and has been awarded several prizes, which I would take the whole 30 minutes to list. I'll just mention the IEEE Computer Society Computer Pioneer Award in 2019, and many, many others. And his work provides a constant source of inspiration, and I'm looking really forward to his talk today.
Thank you, Paolo. So can I share my screen? Do I have permission to share screen?
Yes, you should be able to share your screen.
Okay, let me try. Okay, can people see something which says differentiable stereopsis?
Yes, we can see that.
Okay, and now is it in full screen view?
Perfect, yes.
Excellent. Okay, let's get started. Thank you, Paolo, for a very kind introduction, and thank you to the organizers for inviting me. The topic of this workshop is very dear to me because I believe in this enterprise and I have worked on it for some time. So, but I'm going to start by situating it in the context of some high-level philosophy, if you don't mind my doing that. So I want to start with this slide, which actually captures how I want to pursue computer vision now. I don't think this is the way we could have pursued computer vision 30 years ago, but today we can, thanks to all the development of technology we have. So this idea really goes back to Turing. So Turing in 1950, his famous paper, he had this idea that the way we can build intelligent machines is by trying to start with a child and then give it the experiences that a growing child has, and then you will have this fully developed adult intelligence. Now, this was 1950, which is quite far-reaching. Now, the difference is that between 1950 and 2020, we are 70 years later. So in these 70 years, we have had major developments in the techniques for machine learning, which we can draw on, major development in fields like computer vision, robotics, and so on. There's also been major development in psychology and neuroscience, and in particular, the understanding of how children develop. So we can actually draw on all those insights in order to embark on this program of educating Turing's baby. Okay. So the goal is, instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? Okay, so here is a paper that I have picked from the child development literature, which is very appropriate to our topic. And this is from like 1985. So this is, and this is representative of a lot of work that has been done. This is about the development of sensitivity to depth information in human infants. And 3 Qs are considered: kinetic, which is what in our community we would call structure from motion or optical flow; binocular, which is basically from your 2 eyes in stereopsis; and pictorial, meaning the cues which are available even in a single image. So we can see depth even in a single image, and that refers to pictorial cues. Now here is the observation. The observation is that, I mean, they do it on experiments with babies, that some sensitivity to kinetic information may be present at birth or soon after. So motion perception comes early and drives our early even grouping and depth and so forth. Next comes sensitivity to binocular information, which appears between 3 and 5 months. So between 3 and 5 months, you use your 2 eyes, you're able to fixate, make use of the disparity signal for depth. And then sensitivity to static monocular information appears between 5 and 7 months of age. So after that, we can see depth even in a single picture. These findings may direct research on the development of neural mechanisms. But these findings may also direct research on sort of some of our computer vision ideas on this, and computer vision combined with machine learning ideas. So the pictorial depth part, which is where you can see depth in a single image, it requires some supervision. So currently, a lot of the research in the computer vision community has been based on supervision from ShapeNet and so forth, and now there are better data sets available, but ShapeNet played a pioneering role. Now, I'm arguing that for the human child, there is no access to CAD models like ShapeNet, right? What the human child has access to is kinetic and binocular information. And that provides the 3D models, which then are used for supervising the training of shape from even a single image. So I believe that enterprise is useful for us in computer vision as well. So here's my statement of this philosophical goal now in computer vision terms. And this is a goal I believed in now for at least a decade. My research goal is to develop the ability to 3Dify any image, so even a single image. And I want to 3Dify it so I can imagine replacing each one of these objects by some kind of a 3D model, so that you can move around and see what that scene would look like from different viewpoints. But the initial training has to occur, if you want to make it natural, just from acquiring multiple views of an object. Now we can start solving that problem. So again, this is an area where we have worked on for some time. And in fact, two of the people who are going to be presenting after me, Angjoo Kanazawa and Shubham Tulsiani. So those have been at Berkeley, and we have worked together on various problems in this space. And I'm just going to show you the result of the last paper in that series. This is from Shubham Goel, different Shubham than Shubham Tulsiani, Angjoo and myself. And here what we were looking at were photographs of birds. So lots of photographs of different birds. And from that, we are trying to build some kind of a generic 3D model of a bird, as well as a texture map. And then we develop the ability that even from a single image of a bird, we can 3Dify it. And in this work, we showed that we didn't even need key point knowledge to be able to do this. So this is not your traditional setup for structure from motion or stereopsis, where you have one instance and you look at it from different viewpoints. So this was a harder version of the problem in a certain sense, because the different views are of different instances. Okay, next, what I'm going to talk about today, my work today is primarily, it's unpublished work, and it's all on the theme of the more classic version of the problem, the classic version of what's sometimes called SFM, sometimes called stereopsis, which is where you have multiple views of the same instance, the same object. And what we are going to do is we call this differentiable stereopsis. So stereopsis is a very classic term. I mean, in computer vision, it's been there. People have studied it for 60 years. And differentiable refers to how we combine it with the latest ideas on differentiable rendering. So let me get into this problem statement. So the problem statement is very simple. All you're given are a bunch of views. So here are 8 different images of some 3D object. Okay. And we also, let's say, have access to their masks. So maybe you run sort of mask RCNN on this and you get segmented out from the background. And that's what this is. And we might have some noisy camera guesses. Okay, you might, for example, you might have a few points that you can match on these views. And then you can run like some standard call map or something like that to find the cameras. So that's this setup. So that's the input. And that's the input, and this is the output. The output is a dense shape. Okay, and what do I mean by dense shape? In our case, this means a mesh reconstruction. So in my group, we believe in meshes. Okay, so we've been doing this now for several years now. We regard this is like the standard representation in graphics, and the computer vision community has, of course, moved on to more newfangled things, but I'm an old-fashioned guy. I'm going to stick with meshes. If you can produce results in meshes, and you have meshes and texture, you can do. You can use the standard machinery of the computer graphics community. So we have shape as a mesh, and then we have a texture map. And then we also maybe can correct the cameras, I mean, as part of this process. So now you can do anything you like, because meshes and texture is the representation that graphics people love. So that's a problem we're trying to solve, very straightforward. Okay, and here are some results. Okay, so here are, let's say, 8 views. And we had maybe the cameras were given with some noise. So they're not ground truth cameras, but maybe they could be off by like plus minus 20 degrees. But here's the reconstruction of the 3D shape, and here's a reconstruction of the texture map. Here's another result, and this is from like a typical product images that you might get from an Amazon catalog. And what you will see here is, you get the masks from just white background kind of stuff. And sorry, I apologize. And this is the 3D reconstruction, and this is the mesh. Okay, here is a pretty classic data set for people in multi-view stereopsis. It's called tanks and temples. And here you have 15 views of this horse, and the cameras we can get from using call map as a generic SFM technique. And then this is the 3D reconstruction that we can get. So I'm starting by showing you results so that before I go into all the theory and the algorithms, you have some faith that yes, it's worth listening to this talk because they actually have some results in there. Okay, so now let's get going on. Now you know what the problem we are trying to solve is. And this is, of course, a very old problem in computer vision, right? The problem of structure from motion, multi-view. And I have picked some like papers from like in the last 20 years, but in fact, the work goes back like 50 years, okay. When I started my PhD in 1980, there were already stereo algorithms which people were developing at Stanford. Okay, now this learning from ground truth 3D is what has been very common in the last 5 years in the neural network era. So you start from something like a ShapeNet kind of model, you have some views, and you try to learn the ability to 3D-fy from a single image. But the problem with this is too much supervision, and this is unnatural supervision. A child doesn't have access to CAD models. Okay, sorry. Okay, and then there is the work from our group, which has been without ground truth 3D from just multiple views, and then we like birds, and we did this work for birds, but I won't talk about it. I mean, this is work from Angjoo, Kanazawa, and Shubham, Tulsiani. And I should, of course, acknowledge the big new thing on the block everybody is talking about for the last year or two. It's NeRF. And I really like that work. It's from colleagues at Berkeley and Google, and it's been, the pictures are beautiful and very impactful work. Okay, what am I going to talk about? So this is the problem that setting we had. We have images, we have masks, we have noisy cameras, and we want to get at the shape and texture. So if I want to pose this in the classic computer vision terminology from 20 years ago, this would be called the problem of wide baseline stereo. because the cameras can be quite far apart. Okay, normally when you do stereo, the two cameras are very close to each other, which makes the problem much easier. But if you have views which are very far apart from different angles, it's much harder. So that's what was called the wide baseline stereo. So so that's the problem. And what is challenging about it? You have one image, two images, and we have the classic idea of stereopsis. Once you have correspondence, you can compute disparity, you do triangulation, you get depth. But it's the correspondence problem which is hard, right? So, so what do we do? Okay, so when the views are close enough, that standard techniques work, right? So like there's photosynth and so forth, they are all based on ideas like that. So what we did here was something old and something new. The old idea here is an idea called model-based stereopsis. This is from a paper we wrote like 25 years ago. Okay, so this is presented at SIGGRAPH, Debevec, Taylor, and Malik, 1996. We had a section of that paper talks about something called model-based stereopsis. And the idea is something like this, that we are going to do this iteratively, and basically given your current guess of the shape, you will try to solve an easier correspondence problem. I mean, I'm going to go into it in a bit more detail. So that was an idea we had back then. And then, of course, what we have now are the whole machinery of differentiable rendering. Okay, so what's the idea of differentiable rendering? Well, we are going to have some loss function. Maybe it's in the rendering, in the image plane. And from that, you back propagate to changing some aspect of the shape or the texture map or whatever. And again, this is now a technology. And I mean, there's this work of a soft rasterizer from Hardy, but we can look at packages like PyTorch 3D, and they give everybody this capability. So you don't have to write your own differentiable renderer. Okay, so let me first explain the idea from like that 25 years ago. So this is like from this paper from SIGGRAPH 96. So what we are trying to do is to match what we call this key image and this offset image. Okay, and these two images are very different because the camera angles are very different. And trying your stereo algorithms at the time, which used to be taking blocks and matching them, the views would look very different, and then the disparity would get all messed up because your correspondence would be messed up. Now, our idea was that what if you have an approximate idea of the shape? So in this case, the approximate shape is a plane. So if you have an idea of that approximate idea of the shape, then with that, you can take that and sort of predict the view from the new location using your current guess of the shape. So that's what we do by taking this offset image and warping it with the help of your current model. And now we have to solve the correspondence problem and estimation of disparity between these two guys. And this is an easier problem because the two are much more similar. So therefore, your usual correlation-based stereo and so forth will work much better. So at that time, our idea was just that it makes for an easier correspondence problem because wide baseline is hard. Use your current guess of shape to get to making it a problem more or less similar to narrow baseline. Okay, now what we are going to do is, so now this is 25 years later, what are we going to do? We're not going to do that kind of warping business. Essentially translates to estimating shape and cameras, right? But now we are going to do this using the tools of differentiable rendering. So let's get into that. So it's our algorithm is like super simple. I really love this approach because often when we develop new ideas, they get more and more complicated over time. This idea is actually much simpler than the kinds of approaches we used to write papers on 20, 30 years ago. I can basically explain it in like 10 minutes and this is it. I mean, what you hear in the talk, you will never need to go read the paper. This is so easy, you've got it after this talk. Okay, so there's a simple differentiable stereopsis, blah, blah, blah. Okay, essentially all you do is you have got your shape S, pi stands for the cameras, pi for projection. So I'm going to correct them using some gradient descent step. And there's something is basically some differentiable rendering mumbo jumbo, where we are going to look at the images, and from that we'll try to figure out how to correct the shape and how to correct the cameras, and just repeat. That's it. Nothing more. It's super simple. Okay. There's very easy to explain because that's all there is to it. So let me get into a bit more. So here is some object for which I have different views, and this is my current shape. Okay. So what I can do is, if I have a shape, then I never estimate the texture. I merely transfer the texture. So I can transfer the texture from this source view or from this source view. Now, which view should I transfer from? So note that in different views, only a part of the object is visible, right? Because if you think about this object, in one view, I might see the front side, another view, I might see the other side. So to see the entire, so that the entire texture map is not going to be visible in any one view. You might see like half of it or even less. So when we are texturing this shape, we should do it from the appropriate view. Okay. So and the appropriate view is the one where there is no occlusion and where it's most foreshortened. Okay. So that's the texture transfer that we can do. Okay. Next, we've got a target view. And with these, I can render. So now I'm going to render. Recall I have an approximate camera, right? So I am going to render from these views and given my current guess of the shape and my current guesses of the cameras, I can render what this object should look like from the view 3, right? That's what I've predicted it should look like. And this is my actual view 3. Now, these are the two between which I can have a loss, right? I can have a loss because this should be the same. So in my old days, if you remember what I was talking about, this 25-year-old paper, at that time, we would try to warp and then try to find this correlation between Windows or SSD or something. So here we have the moral equivalent of that. So there's some loss on the texture, some loss on the mask. So I get this texture loss. And now, okay, now the magic of differentiable rendering. So your backprop. So you're now getting all these losses going back. So these the effect of losses is to compute some gradients, which then go back. So I'm correcting the camera pi3, correcting the camera pi2, correcting the camera pi1, and I'm correcting the shape as well. And the shape is represented for us by a mesh of vertices. And then I perturb each of the vertex of the mesh as a result of this gradient flow. So hopefully the shape gets a little bit better and the cameras get a little bit better. And that's it. You're done. You've learned the whole algorithm. You don't have to read the paper. Okay, I'll just show you some pictures and try to convince you that this actually works. So here are some 8 views, and this is the 3D reconstruction. Okay, here is another object with 8 views, and these are the 3D reconstructions. So note that these are dense reconstructions. Okay, note that the topology can be quite tricky. And in our case, we always start from this initial guess of a sphere. Okay. And if you thought we could only do 2 objects, here are lots more objects. Okay. And even more objects. And basically, we've done this on, hundreds of objects. Okay. And and we can do this from 4 views, 6 views, 8 views, 12 views, and so on. Okay. So now let's get quantitative and compare with other techniques. So what are the other techniques we can have? Okay. So call map is your generic structure from motion technique. But the basic issue with call map is that, so nice thing is that it doesn't need anything else in advance. You just run it. It'll find some sparse correspondences, and then it'll give you the cameras. And the cameras will be rough. But most importantly, the shape recovery is very sparse because you need to find corresponding points. And on smooth areas, you have no points. So call map will give you a reconstruction, but it will be a sparse point cloud. Okay. Now with NeRF, we can get dense reconstruction, and with differential stereopsis, which is our technique, both of those will give us reconstructions. The basic difference is that, and we'll back this up with numbers, is that the NeRF approach, with enough views and good enough cameras, it works really well. So in the regime when you have lots of views, good cameras, NeRF and our approach work equally well. Okay. In the regime where you have very few views or your cameras are noisy, that's when I think NeRF starts to sort of break apart. NeRF really likes multiple views, whereas our approach still holds up. So that's the basic claim, that in the regime of what used to be called wide baseline stereo, I have maybe just 4 views or 6 views. Okay. And you might even have noisy cameras. Our approach sort of keeps on holding up. Okay, so let's see some more results. So call map, the main point is call map is great. I mean, structure for motion is great. It gives you cameras, but it gives you sort of sparse reconstructions, not dense point clouds. And that depends on the luck of the draw, in the sense some objects have lots of smooth surfaces, some objects have lots of texture, and depending on that, you will do well or bad, poorly. Okay, so here are some quantitative comparisons, and basically we're comparing with NeRF here. So what you see here are sort of curves corresponding to the chamfer distance. So the chamfer distance smaller is better. So we have these curves, and on the x-axis is the number of views. So 4 views, 6 views, 8 views, 12 views. So all the approaches should get better as you have more views, right? When you have 4 views, they all will do less well. Okay, so that's point 1. Then we have DS, which is our approach, and then we have NeRF. And this is a variation of NeRF called NeRF opt, where in addition to doing the usual NeRF thing, you're also trying to optimize for the camera. And we have three curves here, which is R10, R20, R30. These refer to the amount of noise there is in camera. So in the camera pose. So we think of that 10 means that it's perturbed only a little bit. 20 means there is much greater noise. So it's like plus minus 20 degrees, plus minus 30 degrees. So what do you expect? So the DS curves are solid lines and the NeRF curves are dashed lines. So you should compare in the same color. So this dashed line blue curve and this dashed line solid curve. So these are the comparison between NeRF and DS. So these correspond to the noisiest case, which is this 30-degree noise in the cameras. So you see that basically both approaches like to have more views. So as we get to more views, we do better. But the NeRF curve is higher, which means that it has got higher error. Okay. Now, so this was with 30-degree noise. So suppose I had 20-degree noise. So then you get these other curves, and these again, these are better. Both approaches do better with less camera noise, but again, NeRF is slightly worse. But the difference doesn't matter once you get to enough views. Okay, and then if you have only 10-degree noise, then they are basically can't be distinguished from 6 views on. So if you have relatively little camera noise and lots of views, no reason to pick one or the other. They are the same. It's only in our approach is, I believe, more robust. And okay, here's another measure, which is normal consistency. So that was for shape. So this was in terms of sort of surface normals. And so the measure is with taking dot product. So higher is better. And again, you see the same characteristics. So the solid lines are our technique. Dashed lines is NeRF. Everybody does better with more views. See, they are all getting there. So with more views and the green curve is always is the better one, right? This is when you have less noise, and obviously your results are better. Okay, and then we can do so this approach uses both the mask, which is which makes you think of sort of space carving and stuff like that. And it's using that signal for sure. But it is also making use of the signal of the texture, because just to do an ablation where if you were not using the texture signal, then this would be the kind of reconstruction you would get. You would kind of get the outline of the shape, but you would not get the concavities and things like that, for which you really do need to be looking at the texture. And this is the ground truth. And here are some, I think I've already shown this picture before, more results. And yeah, with these product images, they are interesting because basically the underlying assumption in all this texture transfer is that you have Lambertian surfaces. Because when you have specularities, then that assumption is not true. And that is what is responsible for some of the errors in these product images. But it is something which can be fixed in this paradigm, because we could, of course, do differentiable rendering with more sophisticated BRDF models, but to be sure. And here are some more results on the tanks and temples data set. And again, CallMap, I'm not trying to say CallMap is bad. CallMap does what it does. It finds the cameras and it finds sparse reconstructions. For dense reconstructions, you need to go to NeRF or our technique. So more reconstructions. And I'll conclude here, and there'll be a little bit of time for questions, which is that it is a very simple paper. It's taking a pretty classical idea, implementing a differential rendering, but basically this is now a way to do reconstruction of 3D from multiple views. SFM techniques, which people have used for the last 50 years, they'll do a reasonable job on finding cameras, but not on dense point clouds. You usually have to do something on top, whereas this the approach we have will give you dense from the beginning because it's recovering meshes. The two techniques you can use for recovering dense shape are our technique, differentiable stereopsis, as well as NeRF. The differences are they both have differentiable rendering in them. So what's the key difference? First order difference is one is surface based, one is volume based. I mean, there are other differences like using some like this implicit this function thing, but to me the more fundamental one is surface versus volume. And for many views they'll both do well, but for few views and noisy cameras, not nosy camera but noisy camera estimates, DS is more robust. And I believe that this is a solution to the classic weight baseline stereo problem. And the paper will be on archive, and I'll end here, and I'm happy to take questions so long as we have time. And
thank you so much, Jitendra, for the presentation and also the great timing. So I see already a couple of questions. One is from Andrea Vedaldi. He's asking, what are the limitations of meshes and when do we need to switch to something else?
So this is a philosophical debate. So I think there are no limitations of meshes. They are a pain to deal with, but there are no limitations. I mean, so that's a extreme statement. And the limitations are, I mean, the problem, what makes them difficult to work with is this problem of topology, right? So in our scheme, we start from a sphere, and these objects eventually are not just of the sphere topology. So what we have to do is we keep reconstructing, and at some stage we go to a point cloud, we remesh. We go to a point cloud again and remesh, and those stages, and then you use marching cubes from the point cloud to mesh. So once the point cloud is sufficiently good, then the meshing will give you the right topology. So this aspect is a bit painful. I think that this is where the approaches of using an implicit function, I think, are nice. They are elegant. They don't have this mess. So I can appreciate that. I think that the nice part about meshes is it's standard infrastructure in graphics. So I mean, we don't have to reinvent any new wheels. We just plug into their pipeline. And I mean, we can do this for maybe I'm just sounding like a conservative old guy. I'm saying I want to just adopt the legacy stuff there is, and I like meshes, and that's it.
Actually, I had something connected to that because I was wondering how you handled the change of topology, but you indeed answered to that. Maybe I can, before pointing some other to some other questions, I wanted to ask something connected to this. So, of course, going back in the old days, then there were also the other methods that had a different approach to deal with the change of the topologies, like level set methods, where basically they have this implicit volumetric representations. And what do you think? Is that maybe too heavy at this point to use for the resolutions we want, or?
No, that's a good point, but I think the level set methods are essentially what are. I mean, I always, when I talk to the people using NeRF and so forth, and the implicit function methods, I tell them, hey, have you gone and read those 1990s papers? Because the implicit function, the level sets are exactly that, right? That's exactly the same idea.
Yes.
I mean, that was the same insight which was there in 1990s in the work of people like Jamie Sethian and so forth, right? Which
yes, and Osher,
Stan Osher, yeah. So the answer is it's exactly it's the same insight. It's a good insight. Okay, it's just implemented in a different way in the neural network formalism. So I feel that yes, people are onto this. So yeah, I think that since we went down this mesh path, we have to deal with this problem in a more messy and inelegant way.
Okay, and maybe one last question, although we're at the limit, maybe what are the limitations of call map, and whether we need to switch to something else?
The call map is the result of a lot of the work on it. I mean, it is your classic SFM, and call map it is an optimized result of 50 years of computer vision and maybe photogrammetry for 200 years. So call map is great. I think call map doesn't give you dense reconstructions. And I want dense reconstructions. I just don't want a sparse point cloud. So that's so call map does what it's supposed to do. I think I want more than what your classic SFM does, because classic SFM gives you a point cloud and the points are determined by where you have texture. On a smooth flat wall, that's not where classic SFM is supposed to work. Its formulation is different. So I'm not blaming that. I'm going to answer just one question, which is from, I think, Friedrich Karl, which is it fair to compare to NeRF, which is optimized to produce photorealistic images, not 3D shape? Yeah, I mean, that's the one I have to compare to somebody. I mean, so what we did was we said NeRF agreed. Their original goal was images, but implicitly they do compute shape. And I think that there's a whole industry around NeRF now, and there are lots of papers which focus on the shape that is extracted out from NeRF. So that's why we thought that it's a fair technique to compare to, because over the next year, you will see NeRF for everything, right? So I think that's why we are just getting ahead of the curve. And we actually considered a version of NeRF which is optimized in terms of cameras as well. So yeah, so that's the answer. Then someone else is asking about details. Yeah, I think that part has to do with having fancier losses. Maybe we can tweak that a bit and do better. Yeah, I think I answered all the. Have you tried the algorithm training without mask supervision? Answer is it doesn't work well without mask supervision. So I think that the question is whether how well will it work with noisy masks, as you might get from a just a regular mask RCN. And in we have some results which show we can do it, but I would not claim that, okay, we have solved that problem fully. In the first paper in any approach, it is good to keep the approach as simple and unadorned as possible. And that's what we have done. I've explained the entire algorithm to you, and it takes 2 lines. So we can always add engineering improvements, but I prefer not to do that in any of my first papers. People need to appreciate the idea before all the engineering gets thrown on top.
Okay, thanks a lot, Jitendra, for the presentation, all the answering the questions. I think now we swap with the presentation of Angjoo.
And
So
I
thanks
should
again.
stop share, yes.
Yes.
All right, can you see my screen?
Yes, perfect. So first, a brief introduction from Angjoo. She's a professor in ECE at the University of California at Berkeley. She's also a research scientist at Google Research and serves on the advisory board of Wonder Dynamics. She obtained her PhD at the University of Maryland and then had a postdoc at the Max Planck Institute in Tübingen and then at UC Berkeley. She received the Best Paper Award at Eurographics 2016. She's interested in general in building a system that can capture, perceive, and understand embodied agents in the 3D world from everyday photographs and videos. I'm looking forward to see her latest ideas.
All right, thank you so much for the introduction. I'm happy to be here. It's very nice to see everyone's faces, although I hope this is our last virtual conference. Okay, so let's dive in. I'm talking about NeRF, which is perfect because Jitendra also covered this, talked about this. And in particular, I'm talking about making it real time. And the point that I'm really excited about is that this really enables us to do visual debugging, which is very important whenever you're doing any of these things. Okay, so let's just dive in. There's such thing called NeRF that you may have heard, which can reconstruct these synthetic scenes or real scenes with very photorealistic content. I'm sure people in this audience have an idea, but let me just go over it in a minute. Which is that NeRF is a coordinate-based neural networks that takes in X, Y, Z and the view directions, phi and theta, which is supposed to be 2. It takes in 5 things and outputs color, RGB, and the density. And how you train this is that you have many pictures of the scene. So in each of these cameras have a picture associated to it. From each of these pictures, you shoot a pixel, you shoot a ray in the scene, and then ask these coordinate neural networks, like what is the density and the color at that particular point, which you can actually just integrate using this volumetric integration function, using this transmittance in alpha, which is a function of the density. You do this for many different views and you fit this network to a single scene. Because of this, you actually have to have all of these images with the known cameras, and then optimize the NeRF, which allows you to visualize the scene from many different viewpoints. And as you know, there's been a lot of work in this domain with lots and lots of follow-up works. Okay, and it's partly because it's really gives you really beautiful scenes, and also, but then also there is a lot of limitations. So this is a slide credit to my student Matt. There's a never-ending list of NeRF limitations. It's slow, it's so to train and to render, and all of these things, which, you know, a lot of the groups have been working on. And in my work, in my group, we looked at how can we make NeRF generalized to few shot scenarios with pixel NeRF. And today I'm going to talk about how to make it real time. But before I talk about this, I kind of want to address, like, why am I doing this? Why are we doing this to begin with? Like, why is this line of work really exciting to us in my group? And I think that is one, is that volumetric rendering is a very, very effective differentiable render. So here I will show you the visualization of the NeRF fitting to memorize this scene with this chair. Of course, you have like hundreds of images, right? But this is the initialization. And when I play the video, did you see how quickly this is how quickly the network basically got to the rough shape? Right? This is the depth and it's being visualized. But let me redo this video again, okay? It really converges very quickly to the rough shape. And then it takes like, has a very, very, very long tail to get the high frequency details. Okay, but this fast convergence is a very nice thing when you want to learn from images. And compared to other differentiable renders that I've worked with, like meshes, for example, it has a lot wider basin of abstraction. And I think this is really nice. And this is also very key for 3D learning from images without 3D supervision, which I've been looking at a lot. And this is the theme of this workshop. Okay, so number one is this. And the second thing, which is that is a really compact way to model the plenoptic function And I really like this viewpoint in thinking about what NeRF is what, okay? So let's remind ourselves, what is the plenoptic function? Okay, so plenoptic function is a conceptual, psychological experiment to think about what is the set of all things we can ever see at any point in time. Okay, and this was the answer to this question was the plenoptic function by Adelson and Bergen in 1991. But let me give you an example. Okay, so let's start with a simpler case where it's a stationary person like this in the world, and we want to parameterize everything that they can see. Okay, so what is this function? This function is a function that takes in phi and theta and phi for the viewpoint, and wavelength, lambda for the wavelength. It models the intensity of light seen from a single viewpoint at a single time at this specific point as a function of wavelength. So it can basically describe every single thing this person would see at this particular moment. Okay, now you can generalize this to wider stuff. So let's start adding time and location. Then you're going to get this 7-dimensional function where you have the viewpoint, which is a direction, the wavelength, which for the color or the actual wavelength is a physics-based model everything, time, and then also 3D location. So this is now why you see these like many different spheres at every single point. Okay, and this function can reconstruct every possible view at every moment from every position at every wavelength that anyone has ever seen it. It's the entirety of our visual reality. It has every photograph, every movie, anything that people can ever see, which is crazy. This is a crazy thing. Teaching is really good because I've heard about this multiple times. It didn't really click until I started really teaching what this was. This really is like a model of everything that we can ever see for the virtual reality. Of course, we don't know how to parameterize this function. This is a very, very expensive, large function, right? Like you can think of the street view as an example because they've captured, like a 360 image at every single point, which is like a sample of this space, right? So you could think of this function as like a very big lookup table with the street view. But what am I talking about? Why am I talking about this? I'm talking about this because let's just kind of like remove some of the stuff in here. Okay, so let's just not worry about time for the moment. Let's get rid of the wavelength because we can output color. Okay, so then you're actually going to get something like this, which takes in viewpoint, phi and theta and phi, and then the location, vx, voi, vz of this little sphere. And does this look familiar to everyone? And I think it should look like NeRF is what I hope everybody's thinking about. Okay, and so basically NeRF is modeling this plenoptic function. And in a very compact way with MLP. Okay, obviously it's not for every single moment because it's we can only currently optimize for this a specific scene. But I really think this picture is very important to have it in mind of what is NeRF actually doing because you have these points and you're modeling the viewpoint at every single point. Okay, and I think this is really okay. Well, we're gonna come back to this. And of course, when we talk about plenoptic function. We can't talk about light fields or lumigraphs, which are also SIGGRAPH 1996 paper. So SIGGRAPH 1996 is a very good year because that's when Paul Dubovic's the differentiable stereopsis or the stereopsis paper came out also. And also that's when the light field and the lumigraph papers are also there. But the light fields are essentially a 2D slice of this plenoptic function, as opposed to NeRF actually can, in theory, can model the entirety of it. You can actually model stereo occlusion inside. So that's kind of a difference. But anyway, I just want you to keep this picture in mind, and we're going to come back to this. Okay, so with this in mind, let's talk about how to make this fast. So first, I am going to start with the demo. So here is a screen capture of us rendering these synthetic scenes in NeRF in real time. You can see these view-dependent effects. And one thing I want to say now is that you can convert your existing NeRF to this format, which allows you to do these visualizations. for visual debugging, which I think is the most exciting part. This visualizer also has these kind of, you can insert objects in this, you can change the viewpoints. Actually, I'm going to try this we have a browser demo. So the first author, Alex, built this really nice demo. So let's go try it out. All right, so I'm going to try it with the hot dog. Can you see my screen? I hope you can see my screen. Yeah. Okay, good. Okay, so here is the hot dog. And so you can look at the hot dog. Right now I have to do zoom and this. So it might be a little bit slower than normal, but like you can do this and you can slice the scene. Like, if you're ever curious about what the hot dog looks like from inside, you can take a look. You can also visualize the kind of to fix the viewpoint, but change the viewpoints of this to figure out what kind of like view dependence effects that this network is learning, or this final result is learning. And this is like the data structure in which we fit this, and we can add all these things, so you can play around with this. And later I will show that you can also convert your model to this format, so you can actually do visual debugging on your own NeRF that you're developing. All right, so let's think about, before I talk about how to make it fast, let's think about why is NeRF slow to begin with. Okay, so NeRF is super slow to render, and rendering this 800 by 800 image takes about half a minute, even on a very high-end GPU, because it requires, you need to sample this whole space and then query your neural network every single time. And this is, you have like 122 million calls, and this is what makes it really slow. Okay, so the number one reason that it's slow is because of this sampling necessary. So for every single image that you want to render, for every single pixel, you have to shoot array in the world, and for every single sample, for every single viewpoint, you have to actually ask this network what the color and the density is. Okay, and so you have to sample densely in this R5, or more like R3 first, which is the expensive part. Okay, but for the figuring out where the density is, you can think that how do you actually make things fast? Well, fast rendering usually relies on caching. Okay, so you can just think that for the density, you could just cache where the high density areas are. So you don't actually have to, you can pre-compute this, and you don't have to ask empty points, empty locations, what the network is, because that is empty from the pre-computation. Now, that idea of caching is a rather tricky to apply because of this view dependence, right? If it's just the density, you can cache your voxels, sparse voxels. But R5 is a lot to cache, okay, quickly goes up. So that's really the view dependence is kind of like making it very difficult to just caching it, okay? But this is where I want to think about the plenoptic functions, okay? So let's recall this picture. This is what what we're trying to model anyway. So from this picture, you can already see that you can factorize the location of where these spheres are placed, and the view direction, which is what does that scene look like from all different viewpoints? What is the light that is being delivered to the center of the sphere from very different locations? And so you can actually factorize this. So this is really the kind of insight into how, a lot of the, how we make this NeRF real time. So the high level idea is that we're going to take the original NeRF network that is small, and we're going to apply some magic that factorizes the location and the viewpoint, view dependent effects and the location of these densities. If we do that, we can actually pre-compute, pack this in a pre-computed representation that we call PlenOctree, because we're inspired by the plenoptic function. But it really is that picture that we just saw, which is that we're going to store these spherical functions sparsely in this grid, which is kind of what plenoptic function is kind of modeling. Okay, so that's really the big picture. All right. Okay, so our approach is realized on 2 steps. The first step is to factor out the view dependency. And this can be done in 2 ways. And this is why you can actually convert an existing NeRF to that, or you can train a NeRF from scratch. Okay, so the point is that we don't want this second network call. It's annoying to do and makes it hard to cache. Well, there's a nice thing called spherical functions. Spherical functions is just a function defined on a sphere so that you can query any viewpoint and get a color out of it. A representative function like this is that of spherical harmonics, which allows you to compute these things. But that's not the only spherical function. You can use any spherical function. But the idea here is that we're going to replace the NeRF to, instead of outputting the color after given direction, we're going to make it output k coefficients of the spherical harmonic basis. Okay, so spherical harmonics models the spherical function like a Fourier basis. So basically, these are different bases. Oops. So these are different bases, like these pyramidal things that you're going to see are different bases, and you're going to output the coefficients, which get multiplied to these bases, and then you take linear combination of this, which gives you the spherical function that you can actually update. Okay, so the moment you have these 9 coefficients, at this time, what you do is you get the view direction. This gives you the analytical basis. You can compute this, and then you just take linear combination of this to get the color that you want. You could have used other spherical functions like spherical Gaussians or anisotropic spherical Gaussians. We actually played around with the spherical Gaussian and found similar performance with spherical harmonics. Other works, you could also learn a basis function on your own. This is what the fast NeRF does. But once you, which is a concurrent work, but once you start learning basis functions, that basis function is very specific to that scene because you're always overfitting to the scene. The nice thing about spherical harmonics or the spherical Gaussian is that you're having a central global basis for all possible scenes. So you don't even have to, cache these bases either. Anyway, these are just numbers showing that spherical harmonics, spherical Gaussians gave pretty similar results. And so the rest of this talk, we're just going to go with spherical harmonics. Okay, so you can train that spherical harmonics NeRF from scratch. But sometimes, you just want to, for visual debugging, you might have your own NeRF and you want to you want to change that. So in order to do that, what you can do is you just take your NeRF, just sample at every single point, many different view directions, and try to estimate the coefficients of the spherical functions, spherical harmonics, by just solving least squares. So you can also do Monte Carlo integration, but we have this implemented, and so you can just take your network and then do this. And obviously, the quality depends on the number of samples that you take. But even in like a minute or so, you can get reasonable one if you just want to do visual debugging. So you can always project your normal NeRF into this space using spherical harmonics. Okay. So now that you do this, then the question is how to convert it to PlenOctrees, which is a view-dependent octree. So what is it? Again, it's a sparse voxels, which means the voxel cell only exists at places where the density is high because we don't want to query empty spaces or store them. And that every single cell, it stores these coefficients. So, so if there's like 9 bases for every single color channel, then you have 9 coefficients, right? So the number of bases also changes the expressivity or the size of this. So here is, I guess, 9, yeah. Okay, and how you do this? You just take your NeRF SH and then you just sample your grid on the resolution of 2n to get the density. You threshold and keep only parts that have high density, and then store your spherical coefficients in the octree leaves. Then when you render, you can shoot your ray, but now you don't have to render out. You don't have to sample when there's, the cell actually reflects only where things are relevant. So you get to skip a lot of things. So this is really number one, it gets fast, okay? Second, we don't need to query another neural network to get the direction, so it's also fast. And then you just kind of render this like in normal NeRF. Okay, so where's the trade-off, right? Because there's always a trade-off. So the trade-off is usually the quality. So on this left axis, you see the PSNR. Let me see if whatever. And on the right side is the frames per second. So you want to be as high on this corner as possible because that means you are fast, but then the quality is also high. And later we're going to show how we actually don't need to compromise on the quality because you can directly fine tune your PlenOctree again to get a nice color. But so basically this. And then we achieve like 100 FPS, which is 3,000 times faster than NeRF. Another point is that because we are relying on a caching-based strategy, right? The other trade-off is going to be the file size, because the more complex the scene, the more complex you gotta store, and so that really also directly determines the PSNR, the quality. And we are showing these different trade-offs with the storage. For example, like the one that I showed in the demo is like a pretty lightweight one because we want to be able to load very quickly. Okay. All right, so here are some results of the PlenOctree. These are two different variants. They both render quickly, and you can change the, you can have these different various parameters to make it even faster depending on your application. Okay, so a couple of details. Because we actually have to cache this in a sparse voxel or octree, we don't really want your NeRF to have a lot of like junk in the places it doesn't matter. So for the hot dog scene, for example, all the cameras are on the upper hemisphere. Okay, so if you don't do anything, naively train your NeRF actually prepares like a plate for your table for your hot dog to put things in, because if it's all white, it doesn't really care how it models the white solidness. But then if you had all of this chunky white stuff at the bottom, you got to put this in your PlenOctree, and you don't want to really spend your memory storing that. And so we actually additionally train your NeRF with this sparsity loss, which nicely gets rid of these unnecessary stuff. Which is important for smaller file size. So that's one. The second thing is you can actually fine tune the octree values to the training data. There's nothing different once you convert it to the PlenOctree. You just, oops, oh, there's a line from here. So you can see that like this is right after, this is the ground truth. This is right after you convert your NeRF to, after training a while, to PlenOctree. And now you can directly optimize just the values of the coefficients. Okay, the structure is already set to you, so you don't change that. But you can do this, and then you can see like a marginal improvement in the PSNR. You can things get sharper. So this kind of gives you this idea. You can actually stop training NeRF early and then switch over to PlenOctree, which kind of allows you to train NeRF in a slightly faster way. So in this, we are showing the plot of the total time training required and the quality of PSNR. And so you can see how NeRF has this really long, takes a long time to get to high quality results. And the thing you can do is actually you can train NeRF for like 3 hours and then switch over to PlenOctree and do fine tuning, and you can quickly get to these values, higher PSNR. The thing is, you still need to do the training right now. So this really begs the question of like, can you actually just bypass the MLP altogether and directly optimize this? Which is an interesting question that we're asking. But right now, you still need the first, 3 hours of NeRF training to get the octree structure, because that's quite difficult to differentiate against. Anyway, but because of this, here are some results. On tanks and temples. You can see that because we can actually fine tune on PlenOctree after getting the NeRF, we actually get a nicer PSNR on these scenes. And here are some more results on the real tanks from tanks and temples. Okay. All right. Okay. All right. So, so that's kind of that's basically the method and the results. So there are a lot of concurrent works that tries to make NeRF real time. Next is a similar approach, but using MPI as the representation instead of NeRF, and it has it also uses spherical harmonics to model view dependency, so you can see it from one direction. And then these are 3 other variants that are concurrent in this ICCV. They all kind of basically use similar intuition, but there's a different implementation, so it might be interesting. It's interesting to check them out, and I highly encourage you to do so. But I think ours is the only one where you can take your existing NeRF and use it for debugging, if I understand correctly. Okay, so what's the limitation in future work? So the trade-off really is that you're going to have a large file size depending on the complexity of your scene. And to carry this around for faster, we do a demo on the web. So and then for that, we actually do extra quantization to make it fast to render, to load these parameters. And then as the scene gets large and large, the rendering speed can still get slow. And one of the reasons is this kind of junk that like NeRF kind of likes to put the cloudy things, it doesn't see, it's a planoptic function. It models what it looks like. And so it can put a lot of junk that doesn't correspond to any geometry to get the nice color, which increases the size of your, scene and everything. So one idea is to maybe convert it to surface light field like representation, which is also a 2D surface slice of the planoptic function. Another thing is that the higher degree spherical harmonics are very pointy. So once you start using some coefficient for certain viewpoints, when you look at it from unseen directions, you might get these like really bright colors, but other basis functions could help on this. And of course, you're going to see these like artifacts when you zoom in a lot. And you could fix this with trilinear interpolation, but then it also gets a little bit slow. Okay, but in summary, basically, we provide this kind of intuitive ideas of how to think about NeRF, where we factorize the geometry and view-dependent effects. This allows us to do sparse voxel caching with explicit spherical functions, and you can get 3000 speed up over OG NeRF. And you can directly optimize the PlenOctree, which is an exciting part of maybe training pointing to the possibility of making NeRF training faster. And the thing that I'm most excited about is that you can convert your existing NeRFs, which is great for visual debugging. And Alex made this tool, which is amazing, I think. So you can do pip install NeRF viz, and you can install this thing. You can visualize your NeRF that you're training on your browser. You can show these cameras and all of these things. Here, and then we actually use this in our lab where, we're trying to reconstruct a scene, but it's nice because you get to like, cut these things out, figure out what the bounds are, which is kind of important when you're doing all of these things. And visual debugging is so important, right? Like, and if it takes like such a long time to render every single view, your development in research gets really slow. So I'm really excited about this library. Of course, all of the code on PlenOctrees is also available. So I hope this is useful to everyone. I want to end with a thank you note to my team and first author Alex Yu in particular. When he worked on this, he was only an undergrad. And yeah, he built a lot of tools for this. We're going to be in poster session this week, Tuesday to 1 to 2 p.m. and Thursday at 3 p.m. early in the morning for us. So please come say hi and ask any questions. All right.
Thanks a lot, Angjoo. I mean, these are really cool results. Indeed, I think there was a question that I think you answered almost throughout the last parts of the presentation. So Andrea Vedaldi is asking, how would you also speed up the training? And you mentioned you can also optimize the PlenOctree. Maybe I can add a bit on top of that. So can you actually start to optimize directly with some generic PlenOctree and then refine it as you go? And have you tried to go beyond this that you have shown here in this slide?
Yeah, we're trying this, but it's, we'll see how it goes. Maybe we will have some good things, but I think the issue is that the PlenOctree, the space discretization is quite difficult to gradient backprop over. So basically, once you make a mistake, it's kind of difficult to, recover from it, right? Like once you say that the part doesn't exist. So the initialization is quite important. Another thing though is that the number of parameters in NeRF is much less than the actual space in which it's modeling. So it is doing a lot of compression, right? And so if you directly start doing this in the voxel space, it is also, as you increase your, resolution, you're gonna hit a point where it's like completely underdetermined. And like this thing can be like really, really good at overfitting on your existing views and don't really naturalize to the unseen views. And so I think it's a matter of what kind of regularization can you add in order to, make this a little bit more smooth like this, maybe like a coarsify. I don't know, we're kind of trying to look into this question because we would all like our NeRF to train faster. We will see.
Okay, I have another question. So you are converting the NeRF to this PlenOctree. How fast is the conversion?
Yeah, conversion is quite fast. Like, I mean, like if you want to use it for debugging purposes, like you can do it in a minute. I mean, like the longer you sample, the higher quality your spherical harmonics are going to be, obviously. But like with 20 minutes, I think you can take enough samples. And so it's really, you know, you can do it like a minute is fine.
Okay, so it will give you enough resolution to work with. In a minute, you will get enough resolution to work with the renderings.
Yeah, like you mean like to do your visualization. Yeah, I think all of these visualization that we do is like, you know, you don't like it's really I mean, especially I think whenever you're doing visual debugging, I think a lot of it is about like the structure. Then you really don't need it to do it too much. If you really want to know about the view directions, I think you might want to render a lot, but it's quite fast.
Okay, and what do you think is the next thing after, say, addressing the speed issue? Where do you think is the next problem to solve in NeRF?
I think the next problem to learn is to really, how do you like learn a reusable, like you want NeRF to be reusable, or like reusable pieces in 3D. Or something like this, basically training across multiple scenes. And I know there are other couple of directions in this direction, and like, you know, but I think if you actually want to train on multiple scenes, I think it's actually quite important that you can actually train fast. And so hopefully this is why it's not just making it real time for the, you know, rendering purposes, but it will also actually help us do a lot more if you can train more scenes faster, do more learning-based approaches.
Right. And there's a question from Alexander Trevitic. Have you considered some extension which creates a PlenOctree in a single forward pass given some images?
Yeah, I guess, you know, so all of this, you have to actually, you know, go back to 2017. It's not even that old. 2000. A lot of work in voxels from 2017 to 2018, or to 2016 to 2019, actually is doing this, right? People used to directly predict voxels. I have to mention that Shubham Tulsiani, who I think is talking next, has this work called DRC in CVPR 2017. And it really essentially does the volumetric integration on voxels. But back then we were like, oh, voxels, you have to store them directly. It's too much. And so we didn't really look into it. But basically what NeRF is doing is just like a continuous version of this. And so there's a lot of papers like that from back then that does this. I mean, which is what our pixel NeRF was kind of inspired on. Actually, Shubham, and also there's a paper from Andreas Geiger's lab that actually predict the Sparse-view representation from images. And so those things can be, I think, directly applied, actually. Would be interesting to see. Okay. And I want to answer a quick question, which is one of the persons asking, have you tried the training without the mask supervision? But this is NeRF, so there's no mask supervision used anywhere.
No, that was, I think, for the previous
that's the previous. I see. Okay, good.
And then I don't see any other questions. Well, thanks a lot then, Angjoo. And again, great presentation, good work. And now I'd like Shubham to try and share the screen.
Yeah, thanks. Let's see. Can you see the screen?
Works.
Okay.
Yeah,
great.
That's perfect. And in the meantime, I will briefly introduce Shubham Tulsiani. So he's a professor of computer science at CMU. He was a research scientist at FAIR in Pittsburgh and obtained his PhD at UC Berkeley. He has a long history of work in 3D reconstruction from images, and more recently has worked also in robotics and interaction. He won the Best Paper Award in CVPR 2015, and he's interested in general in building perception systems that can infer the spatial and physical structure of the world they observe. I'm looking forward to his presentation.
Great, yeah. Thank you for the introduction and thanks for having me here. So yeah, today I'm going to talk about Sparse-view 3D reconstruction. And I'm really glad Jitendra gave a talk before me on essentially the same problem that allowed me to cut a few intro slides and make the talk a bit more focused on some more results, etc. But really the problem that I want to talk about today is, given a very small number of images of an arbitrary object, such as this fire hydrant or this monitor, we want to get a 3D model out for this. And in particular on this problem, I'm going to talk about one specific work that is based on an upcoming NeRFs paper of ours titled Neural Reflectance Surfaces for Sparse-view 3D reconstruction. And really sort of Jason and Genshing did all the hard work. So if you ever run into them in ICCV virtually, just let them know. Actually, I see something in chat. Okay, sorry. So the long-term goal that a lot of us working in 3D vision are really motivated by is this, right? That given just a single image or a very small number of images of a scene, we want to predict a 3D representation of the underlying world. For example, for this living room, we really want to infer all the furniture items, place the sort of cup on the table, and really reconstruct a lot of detail of this particular 3D scene. And while that's a very challenging goal, sort of an intermediate problem that a lot of us have identified as being an important one is instead of trying to reconstruct sort of entire scenes, first we should at least develop capabilities of being able to reconstruct all the objects in them. So here are just some different objects reconstructed in 3D from some of my recent works. And the hope that we have in the community is really that we'll be able to scale this sort of an approach to really the tens of thousands of object categories in the world. And so with this in mind, that we really want to build approaches that eventually work on these tens of thousands of object categories, I want to very briefly paint the landscape of the 3D reconstruction approaches that we have developed over the decades. And to sort of borrow Jitendra's term of this landscape of approaches that aim to sort of 3D-fy objects from images. And so the axis that I was talking about was this generality, which is how many categories of these objects can a particular approach reconstruct? So for example, if I were to just go and download the code that the authors have provided, how many among the tens of thousands of object categories, let's say from ImageNet 10K, will I be able to reconstruct? And sort of the other axis, which is kind of complementary to this, which is how much effort do I need to put in to get the 3D model of a new object that I'm interested in? And in this, on one extreme lies a lot of single view 3D reconstruction that we're pursuing. For example, I just want to be able to take one image of an arbitrary object and out should come a 3D model. And sort of on the other extreme is this very dedicated scanning setup. For example, here is a scanning setup that I think Paul Debevec had to get a 3D model of President Obama, which really has many calibrated cameras with very sophisticated lighting to get an accurate 3D model. And so we really ideally want an approach that's somewhere to the top right of this chart. And in fact, the very first computer vision thesis was also tackling this problem of 3D object reconstruction from a single image, and kind of falls in the bottom right corner of this chart, where it could infer 3D from a single image, but was really limited in terms of the class of objects it could handle, just typically limited to these pyramids or cuboids, for example. And over the next decade or so, we improved the generalization by using, let's say, model-based detection systems, which could make it work on a far broader set of categories. And sort of in parallel, in computer vision, there was this amazing stream of work on multi-view stereo and structure from motion-based approaches, which gave a very different perspective to the problem of 3D-fying scenes and objects. And so they tackled a different space of this chart where they were really general approaches that could in principle reconstruct any scene or an object, but required many images and often calibrated cameras to be able to do this sort of an inference. And sort of more recently, with the advent of some learning-based approaches, I think we made a lot of strides on being able to do this in a more general setting. For example, this work from Angjoo could let us reconstruct meshes of more generic categories from images, again, from, let's say, just a single image. And maybe sort of a very brief self-advertisement of a recent paper that we had in ICCV21, which maybe pushed the number of categories that we could handle from maybe tens of categories to, let's say, 50 or so categories by using some more unsupervised techniques that did not rely on key point annotation. And so, we've been pushing on this towards getting to maybe from 2 categories like faces and cards a few decades back to maybe 50-ish categories at this point, and we can really reconstruct. And sort of the hope is that we'll be able to push this further. But sort of on the other hand, a lot of these NeRF-based approaches have improved the quality of what we can reconstruct, and still allow us to reconstruct these very general scenes of arbitrary objects such as this microphone or hot dog, but again require a a more painful capturing process where we have maybe 100 or 50 images of a specific scene, with, in this case, very precise cameras as well. And more recently, I think over the last year or so, for example, some approaches have actually looked at relaxing the capture setup. For example, this IDR paper or the BAF paper from Yari Van Lin relaxed the camera assumption from saying, okay, we don't require very precise cameras, but only approximate cameras that, let's say, have Gaussian noise, which we can sort of argue whether it's a realistic assumption or not. But they have allowed us sort of simplified the capture setup a bit to saying, okay, we still need many images, but perhaps the cameras need not be that precise. So still often requiring something like 50 images to be reconstruct a scene, but relaxing the camera assumption. But we still see that there's this wide gap between some approaches on the left, which really work in settings where Colmap can give us rather precise cameras, and some of these single view reconstruction approaches on the right, which don't really require cameras and require just a single image. And I think in the middle is this problem of sort of sparse view reconstruction in the wild, which is what our approach tackles, where we don't really have a lot of images. So something like just 6 to 8 images of an arbitrary object with very coarse and approximate cameras. And so someone can just go around and click some photos of an object they want to sell. And we want to be able to reconstruct objects in this setting. So just to be maybe more concrete, one use case that our approach was really motivated by was this marketplace setting, where let's say someone who wants to sell their car on eBay can just naturally take, let's say, 8 images of the car that they want to sell. And given this, we want to be able to predict a 3D model out. And just to convince you that this is a really hard setting, here's sort of a typical result of Colmap on some of these marketplace settings. So I think actually this is not a result on this specific sequence. It's a result on a sequence with even more cameras, maybe something like 12, but still a sort of typical sequence. And Colmap, because these are views with very little overlap, doesn't do very well in registering them or getting even a sparse 3D output. And here's actually maybe the best result that the first author Jason got by trying Colmap on maybe 20 or 30 different image sets, where given on average 8 images of different cars, we could register some correspondence and get some plain output, but the car doesn't really look very well, look very good from the top because a lot of these correspondences are false. So really this setting of sparse view 3D, where there's very little direct overlap, or there's a sort of a wide baseline setup across different views, is really challenging for some of these classical settings to come up with very precise cameras. And it is in this setting that we want to be able to reconstruct 3D. And in our work, what we do is, in addition to these images, just use a very coarse initial shape. So in this case, something like a typical sedan-like car, and using initial cameras from learning-based systems that don't give us something like a Gaussian noise, but give us maybe okay cameras for certain views and cameras that could be very off for some other views. So using just 8 or so images and a very coarse template mesh and cameras from off-the-shelf systems, what our work does is tries to get the 3D model of the underlying object while also modeling some view-dependent appearance. So this is really an image that has been taken out in sort of outdoor scenes where there's a lot of lighting, cars have specular surfaces, and we want to be able to model this sort of a view-dependent appearance effect from just these small set of images. And here's maybe just another example with a different object captured in the lab, where again, for this monitor, we just took 8 images, used only a cuboid-like mesh with very coarse initial cameras. And again, we can get a pretty detailed 3D model output using our approach. So before I go into the specific details of our approach, I just want to, actually, here's just some more results to convince you that this is really something that works across a lot of objects. And again, using the very same initial shape, we're showing reconstructions of about 200 different cars from Craigslist, again, using just about 8 images on average for each of these instances. So sort of before going into the details of our approach, of course, this is really inspired by a lot of recent progress in neural rendering work, for example, NeRF, which, as I said, lets us very accurately model a very wide class of scenes and sort of get results like these, where we can get accurate 3D reconstructions of very complex shapes with very complex appearance. And so, what is it that makes these neural rendering field approaches work really well? And Angjoo gave us a very nice review of the math, so I'll probably skip that. But the high level idea is that NeRF gives us a very powerful model of geometry and appearance. And in fact, it allows us to model arbitrary geometry and appearance. It is, the per point density model is something that can let us model something like cloud. And the per point radiance field is something that lets us model very different appearances for the same point in different directions. And this really rich and powerful representation of geometry and appearance, given hundreds of images, lets us reconstruct very accurate shapes as well as get very accurate novel view renderings. Now, unfortunately, it is this exact same thing that makes NeRF not work very well in sparse-view settings. And so to paraphrase from a famous American movie, if we have a very high representation capacity, then there's a very high risk that we'll overfit and go into some local optima. And just to illustrate the point, this is just vanilla NeRF, which we'll actually improve upon as our baselines. But given just 8 images of a generic car with very approximate and not precise cameras, the novel views that just vanilla NeRF from off-the-shelf generates are not at all very realistic. Because if we look at any of the training views, we actually find that it can reconstruct them rather well. But because the space of solutions is so large, it has really overfitted to the training views and doesn't really generalize to any novel view. And so the novel view renderings with a different elevation and azimuths don't really look realistic at all. And so our solution that really builds on these neural reflectance surfaces actually combines 2 very simple ideas and really combats the arbitrary nature of the geometry and representation that NeRF allows. And the 2 ideas are, one, that almost all objects that we are considering have well-defined surfaces. And the second is that the view-dependent appearance, while it's important to model that, for example, specularities in outdoor scenes, this cannot really be arbitrary. We have a lot of well-known view-dependent appearance models in graphics that are far more constrained and represent more closely what happens in the real world. And we should incorporate these kind of knowledges. And it's just really a combination of these very simple and basic ideas that we build upon for our approach that allows us to learn 3D inference from in the sparse view setting. So just to very quickly go over the shape representation, because I more want to talk on the appearance representation. We model shape as a surface that is diffeomorphic to a sphere. So given any point on the surface of a sphere, we have a neural network that predicts a deformation for it. So given a UV point in the sphere, you map it to a 3D coordinate XYZ. And because you can do this for every point in a sphere, it induces a deformed 3D shape through this neural network. And this gives us some very nice properties that it just guarantees a watertight surface by construction. And similar to what we do in neural radiance fieldworks, using some positional encodings to encode points in a sphere lets us still capture reasonably high frequency shapes, such as the monitor that we saw earlier, which had some of these thin structures. And so the shape representation at a high level is just extremely simple. It's a neural network that maps a point in a sphere to a 3D coordinate and thus induces a deformed mesh. In terms of modeling view-dependent effects, just to maybe give you a bit of a background and notation, what we are really interested in modeling is if we are considering a particular point X and viewing it from a particular point V, how much light will we see emanating from that particular point X? So just to give an illustration, suppose we are rendering this surface and there's this point X that we are viewing from the camera that is in the direction V. How much light will this particular point throw in the direction of the camera? And there's this very old and classical surface rendering equation, which tells us the math behind this. And while this looks slightly scary, it's the equation is just very simple. All it says is that when we are considering the point X, let's consider all incident light directions, omega. And for each of those directions, let's consider how much light is incoming to that point. So that's the last 2 terms. And what fraction of that light will go back towards the direction V. So essentially, all it's saying is that let's integrate all the light coming into the point X and calculate how much of it will go back towards the direction V. And so this is some very, very classical and well understood thing in computer graphics, which can allow us to model view-dependent effects. And the radiance field solution, or the neural radiance field solution that, let's say, NeRF adopts, is to say that, let's just forget about all this. And what we can do is just model this outgoing light from a particular point X in direction V through just a neural network. And we can just learn this neural network. And instead, what we, and sort of just to go back, while this is a very powerful idea, it really fails in the face of limited amount of training data. And so our idea is that we can constrain this particular solution, that we really understand from graphics what are some possible models of VRDF, what are some possible models of incoming light. And so we can constrain both lighting and VRDF models to sort of get solutions that still look realistic and can be trained with little data. And so to be more concrete, what we do is adopt sort of an environment lighting model. So what this says is that the incoming light to a particular point is independent of the particular point and only depends on the environment. So this is something like a car in an outdoor scene, which has no lights nearby, but only sort of the sky that is lighting the particular car. And the second assumption, I'm going to skip some technical details. And the second assumption is that instead of modeling a full BRDF, we can just decompose the view-dependent effect using a Phong reflection model. And this just breaks down the appearance at a particular point into diffuse and specular components. And I think in the interest of going to results, I'll skip a lot of the details. But essentially, we can compute the net incoming light at a particular point and multiply that by the sort of inherent texture at that particular point, which can again be modeled as a neural network, and some specular effects, which model the incoming light and the outgoing direction. And based on some specularity coefficients that we'll also learn, predict how much specular effects we'll see in a particular viewing direction V when we are seeing a particular point X. And maybe just to give you some illustration of what these typical terms look like, if we are trying to render the particular car that we are learning from this reference camera viewpoint that corresponds to this image I, here are the surface normals of the geometry that we can render. Here's maybe just a final texture that is unwrapped that we are learning. And this is kind of an environment map that we typically end up learning, which in this case is saying there's more light coming from the top than from the bottom, let's say. And using these, sort of using the environment map and the surface normals, we can compute the diffuse lighting at any particular point. And that can let us render the view-independent diffuse texture. And using all of the sort of the normals and the environment map and the material properties, we can also compute the specular effects at that particular point. And here's just an illustration of how some of the specular parameters control appearance. But by just a combination of these two, the specular lighting and the diffuse image, we can get this output, which has both view-dependent and view sort of agnostic effects. That can really let us model sort of the shininess on the surface of the car, for example. And so once we have this way of rendering, we can just train our system to match the training images that we have using just simple reconstruction losses. So again, we assume we have at least coarse foreground mask given by mask RCNN, and we just say that our renderings should match both the appearance of the pixels as well as the mask when we render this through the rendering model that I just described earlier. And to be more concrete, what we learn are the shape, the per pixel texture, and the environment map lighting. So all of these are neural networks that model the respective properties. And also we optimize the cameras associated with each of these views and alpha and K, which control how much specular the surface will be. And to do this, as I said earlier, we assume some initialization in the form of a very coarse category level template shape. And sort of in this case, we construct a spherical mapping to this so we can initialize a neural network. And we assume very coarse cameras that are given by some off-the-shelf system, in particular this particular system, which takes actually a CAD template and can give us some approximate cameras given an image. But yeah, just sort of given these two and a very small number of input images, we're able to reconstruct these kind of objects given just images from Marketplace. And just to highlight some results, so given these 8 images that we are showing as sort of the nearest neighbor to the current view in the rotating 3D shape, we can get pretty accurate 3D models of the car. And on the right, we are also showing just some visualizations that highlight the view independent and view agnostic rendering effects. And what I kind of want to highlight here is that using just the same initial shape, so just this sedan-like initial shape, we can model all of these three cars, which have pretty different geometries from each other. For example, there's a truck at the bottom, or this CRV at the bottom, and the Jeep at the top. And all of these are actually very different from the shape that we initialized with. And again, sort of going back to this image, we are able to reconstruct about 200 different cars using, on average, 8 to 9 images with just off-the-shelf pose estimations and off-the-shelf camera estimations. Sorry, off-the-shelf mask estimations. And so one thing that I do want to very briefly touch upon is how we can evaluate this, because we are really interested in making this work in the wild, where we don't really have ground truth 3D shape for the objects that we're interested in. Well, what we can do is hold out certain images and ask whether our learned models can generate those held out novel views. So what this looks like is we have a few input images. So for example, we have 7 input images because we held one out. And given these input images, our approach and any other approach that we consider as a baseline can learn some sort of a 3D representation. And then given a held out target view, we can just query whether this 3D representation can synthesize this particular image or not. And this is the typical way that almost all view synthesis papers, for example, NeRF, evaluate how well they're performing. And one thing that sort of is swept under the rug is that the assumption for view synthesis is really that we have ground truth cameras during training and aligned query cameras at testing. So when we say that we want to generate this particular view, we know what precise camera we are talking about. And that, unfortunately, we don't quite have in the real world. Like if I'm taking these 8 images from Craigslist, we don't have precise cameras during training or testing. And so we need to be able to account for this when evaluating the 3D inference that we can make. And so to work around this, in our paper, we actually proposed 2 different evaluation setups. One where sort of the first author, Jason, manually sat and optimized cameras and tuned them so that they're as accurate as possible on a small set of images. So that really represents the classic way of evaluation, except in this case, it's sort of manually defined pseudo ground truth cameras. And second is that we can allow camera optimization during training and evaluation. So when we say that we want to generate this held out image, we should also be able to optimize the camera that we are viewing it from, because the camera that we have from the off-the-shelf system is not always precise. It may be off by 10 or 20 or 30 degrees. So a method should be able to optimize the camera to generate any target view. And I might sort of skip some of the details. And we, again, evaluate this in a data set that is built off of Craigslist, where we chose sort of 20 different image sets, and we compare against NeRF and IDR and some other variants as well. And I'll actually just skip to the second kind of an evaluation result, where we do allow fine-tuning the cameras during both training and evaluation. So once you've learned the model, you're allowed to change your camera to best match the target image that you're trying to generate. And we think this is really critical for being able to evaluate by view synthesis in the wild, this ability to optimize cameras during training and evaluation. And sort of in this particular case, our approach is really better than some of the other baselines. And here I'm saying NeRF star because we improved NeRF a bit by giving it additional foreground mask supervision and sort of regularizing it to only reconstruct within a canonical volume, etc. And all of those tricks made the results sort of comparable. So it's not sort of quite vanilla enough. And here is maybe just some visualization of these different methods of what kind of results you can reconstruct. And you really see that not constraining the appearance model gives very different or sort of jarring view dependent effects, where we see sort of these ghosting artifacts from views that are maybe not seen in training. And so far I've just been showing results on cars because that was the setting that we were typically evaluating on. But nothing in the approach that I described was really restricted to cars. Really, we can take, because we're in Pittsburgh, take 8 images of the Heinz ketchup bottle, and given just a very coarse cuboidal initial shape, we can learn pretty accurate 3D reconstruction and also model some of the glossy view-dependent effects, and can do this for other shapes such as this PS5 controller, again, starting with just this cuboidal initialization and very coarse camera poses. And yeah, maybe just a few more results on some different scenes, where again, we can capture different kinds of shapes, though we don't model all of the details very well. For example, the milk frother in the espresso machine isn't captured quite well. But in some other cases, such as the fire hydrant or the desktop monitor, we are able to capture a lot of the details. And sort of, I think one interesting ambiguity that comes out is because we are modeling view-dependent effects that sort of are determined by the environment lighting, there is this inherent ambiguity that whether the car is sort of black and there's a lot of environment lighting out there, or whether the car is sort of gray and there is less of environment lighting out there. And so this is something that we really can't resolve in any model, but the output radiance that we get is still plausible. And one other limitation was that we were considering only sort of white environment lighting. And so the model doesn't do very well in the scene at the bottom, where the environment lighting is sort of more yellowish than white in this particular case. And just to very quickly highlight some future directions, I think one constraint of our approach is that it really is restricted to fixed genus surfaces, because we start with a sphere, or we could start with a donut, and we're modeling surfaces that are diffeomorphic to the initial geometry. And it does not, for instance, let us model things that have very thin structures or something like bagels. But for instance, some of the previous talks that we saw could address this, and you could imagine marrying this with the appearance model that we have built in our work. And talking of the appearance model, we were using a very simplistic Phong reflection model, and there are a number of generalizations that one could make to model more complex appearance or geometry. For example, use more powerful appearance models, or allow sort of variation of models or materials across different points on the 3D shape. And this one other limitation, which I think is really, really fundamental, and I don't think as a community we have very good solutions, which is all of these approaches still require at least some coarse camera optimization or coarse camera pose to begin optimization. In our work, we were relying on some off-the-shelf systems, or in some cases with very coarse annotations in 30-degree azimuth increments. But this is something which we don't have very clear ways of overcoming. And if we could, then this would really enable scalability, where we could just download K images of an arbitrary object and be able to run systems such as ours. But yeah, with that, I think I'd like to maybe leave you with this picture, where I really want to highlight that we have done a lot of great work on scaling up single view reconstruction, or getting accurate reconstruction in settings where we have sort of 50-ish images, but being able to do this sort of sparse view reconstruction where we only have maybe 5 to 10 images of a specific object is a very interesting and challenging setup. And I hope we see a lot more work in this. Yeah, with that, thank you. And I'm happy to take questions.
Thanks a lot, Shubham, for the presentation. Very nice results. There is a question from Shangce, which is actually very much the same question I wanted to ask, and I think partially you answered to already. That is, how critical are the initial shapes? Because the impression is that later you show a cuboid, and it doesn't seem to be very important that it is too close, but maybe you can say something more about it. It seems maybe you can start from a sphere, it would still work.
So I think it really is a trade-off between how accurate your cameras can be and how coarse your initial shape can be. So in our case, the cameras were sort of really coarse, in the sense they were annotated for some of these objects within just 30, 40-degree azimuth bins. So if you have more precise cameras that you can trust more, then a coarser initial shape is fine, because at initialization, you can refine the shape if you trust your cameras. But if you don't trust your cameras a lot, then, so in our case, we couldn't start with a sphere. We at least needed a cuboid which had the correct orientations, because otherwise at initialization with bad cameras, we would very quickly get stuck in some weird local optimas. So I think the question about how accurate a shape do we want is a great one, but I don't think it's an independent question of how accurate cameras do we have. It's really the combination of the two that we should be thinking about, and together relaxing the accuracy of.
Okay, and I suppose you could also, as Jitendra did, use the call map to get some initial poses, right?
So actually, surprisingly, in our settings, maybe because these are in the wild images with a lot of view-dependent effects, we did not, like Colmap did not work at all on any of these sequences. So if you have 8 images of a random car with very shiny and view-dependent effects, we did not see Colmap to work. Like we could not get Colmap to work and give us even reasonable initial camera estimates.
Okay. There's another question. Is there any approach which is volume-based, which is a volume-based representation?
Yeah, so I think that's a great point. And I sort of swept some of the comparisons under the rug, but there was this recent work on IDR by Yarev et al., I think last year ICCV, which has this STF representation. So it is sort of volumetric, but it more explicitly imposes a surface-based prior. And that can maybe let us sort of serve as an initialization, except, it all becomes a bit murkier because if you're trying to optimize these kind of volumetric approaches with very coarse cameras, they do often not tend to converge to a good solution. So I think it's really, if we had good cameras, then I think a volumetric approach would give us a good initialization, because even though it has more flexibility in the regime of good cameras, it will go to a good solution. But I think it's not very reliable if the cameras are far more approximate, as was in our case. And in the paper, which will hopefully be out in archive next week, we do show comparisons to IDR, and you will see that some of the geometry is not as accurate.
Okay. I have also another question, which is, do you need explicit masks in your optimization?
Yeah, sorry. So yeah, that's a good point. And we do have a mask loss. So for all the cars, we use mask RCNN to get sort of some approximate foreground masks, and we do use them in our optimization. And that is, again, sort of critical to making this work.
Okay. And by the way, since you added all these additional, generalization in the rendering of the image, did you design your own differentiable renderer to also handle the reflectance and?
Mm-hmm. So our differentiable renderer can be viewed as two things. One, if we have a pixel, what point on the mesh or the sphere are you rendering? And so that's sort of the rasterization process, and that we used an off-the-shelf rasterizer like Unsupervised. Once the rasterization is done, to compute the lighting at a particular pixel, there we sort of wrote our own code, which essentially did Monte Carlo rendering of integrating over all the viewing directions. But I'd like to mention that it's still very, very fast, and actually we could render the whole image almost in real time, and could use things like perceptual losses, which approaches like NeRF, for example, cannot, because they are limited to rendering individual pixels.
Okay. And so maybe one last question. So what do you think is the next step in this kind of line of work?
Yeah, so I think I was maybe trying to allude to some of those. I think there are really three things. One, we want to we want to allow more generic topologies. Second, we want to capture more complex appearance. So I think both of those we have some handles on how to do. For me, one of the larger open questions is, how do we get these approximate cameras? Like if I give you 4 arbitrary images of a generic object, we can't get cameras using a learning-based system. So just how do we get an approach that can even bootstrap learning? And that to me is sort of something that will really unlock application to a very broad class of things if we can solve that.
Okay. Well, I don't see additional questions. Then thanks a lot, Shubham, for the presentation and for answering all the questions. I guess that at this point we have a break. Is that correct, Shankta?
Yes, we'll have a 10 minutes break, and after that, we'll be back for the last session and the panel discussion after that.
Okay, then thanks everybody for the presentation again, and and for all the questions from the audience too. So let's meet again in 10 minutes, you said?
Actually, 7 minutes now.
7 minutes, okay.
Okay, welcome everyone to the last session. We already had 9 super exciting talks, but we have 3 more. And we are starting with Noah Snavely, who is associate professor at Cornell Tech and also a researcher at Google Research, who is working on computer vision and graphics, 3D scene understanding, and learning from about scenes from images. He has received many, many awards over the years. Maybe most notable is the Helmholtz Prize in 2019 for the seminal work of building Rome in a day. And today he's going to talk to us about something we have not talked about yet in this workshop, which is the incorporation of language into the 3D world. And we are very excited for the talk. Noah, the stage is yours. Take it away.
This is so cool. Can you hear me?
Yes.
That is so cool. Okay, so let me start the presentation. Okay, thank you, Christian. This is so cool. It's great to see y'all and excited to be here. Hope you're all having a good day so far and a good ICCV. And thank you so much to the organizers of this wonderful workshop. So yeah, to start with, when I was a kid, I came across this this wonderful book called Cathedral by David Macaulay, who, well, this was his first book. This was published in the 1970s. And you know, he's since become well known as a master explainer, especially to children. He had a very famous book called The Way Things Work that I also loved when I was a kid. But this book is all about cathedrals and how they were built and the story behind their construction. And so it's full of beautiful, you know, illustrations, many illustrations of things like, you know, all the tools that the craftsmen used when they were cutting stones or wood to make the cathedral. And then it goes on to, you know, step-by-step process. Okay, this is a medieval cathedral. So this is, okay, so in this story, the cathedral started being built in the year 1253. And the first thing to do is dig a big hole in the ground and then cut stones and very carefully lay them so that they're level to form a foundation for the cathedral. And by the way, this entire process of building a cathedral could easily take 100 years or more. You know, kind of an amazing process. And then at a certain point, you know, the walls start coming up and you have to build this big wooden circle and then hoist it up to the top of the cathedral. And then people can stand on it and turn it to lift heavy things to the top of the cathedral, and so on and so forth. And it explains how the cathedral's built and also why it is the way it is, you know, why it has things like arches and buttresses and so on. So I don't know, I just love that book and I loved thinking about how a cathedral works. A book in a similar vein, published later by Patrick Dillon with beautiful illustrations by Stephen Biesti, who again is a master explainer. In his case, his art is drawing cross sections. It has this wonderful illustration of the Notre Dame Cathedral, kind of a combination of cross section plus exploded view diagram, where, well, first of all, again, you can see how the cathedral works, like how the parts fit together, and has all these great, you know, annotations and labels about explaining different things. It has people drawn in so you can get a sense of scale and, you know, brings this to life. You know, just a wonderful, you know, magical illustration of this building. Okay, and as a kid, I really was fascinated by architecture, especially these medieval cathedrals, because, well, first of all, they're beautiful, and, you know, there's something amazing about how they were such a long-term project. But also, I just love learning, you know, every part has a name and has a function. And I was just fascinated by these names. Like, you've got your flying buttresses, you've got your vaults keeping the ceilings from falling down. You've got like more decorative elements. So you have portals, and then on top of them, you have a semicircular region called a tympanum, where you can carve relief. And then around that, you have semicircular things called archivolts. I loved it. Okay, all these great names of things. Okay, so today, you know, okay, well, we can reconstruct 3D geometry. You know, it's magical in its own way. You know, here's a point cloud reconstruction of the Notre Dame Cathedral in Paris from Flickr photos, you know, reconstructed with structure motion tools. And it is beautiful in its own way, but it's lost. It doesn't have a lot of the magic of that illustration I just showed, that explanatory illustration. And we can do better. Using modern tools, we can get better view synthesis results for cathedrals and other landmarks using techniques like North in the Wild. And also, one nice thing about structured motion is that we can scale it and reconstruct. As long as we can download Flickr photos of places, we can reconstruct 3D models of places around the world. It's very scalable. But at the end of the day, it's still what you might call point soup. Unstructured, low-level 3D point clouds with no knowledge of the rich meaning behind the points, the function of the parts, the semantic properties, the fact that there's correspondences between parts across models. Each cathedral is unique, but also there's similar parts that span all of them. Okay. A very far cry from this kind of illustration that we saw earlier, which again is imbued with all of this rich meaning. So how do we get back some of this meaning? Well, okay, I've been thinking a lot about this. So one approach would be to make use of different modalities like language. So for instance, it seems like we need some kind of data, maybe language data will help. So indeed, you can go to Wikipedia and find great descriptions of every cathedral on the planet, basically. There's a wonderful Wikipedia page for the Notre Dame Cathedral in Paris, which, if you scroll down, you can find descriptions of the architectural elements, floor plan, you can see descriptions of the vaults, the buttresses, etc. And in fact, there was a paper in 2013, a beautiful paper, a paper I really like, that utilized this kind of data. So this was a project called 3D Wikipedia from Brian Russell and co-authors at UW, where they took the Wikipedia page for a landmark, like in this case, the Pantheon, and they took a corresponding 3D model reconstructed from internet photos using structural motion and multi-view stereo. And they tried to associate text on the page with regions of the 3D model and created new ways of, new kind of browsing modalities based on that. So in particular, they took every noun phrase in the article and tried to find link it to something in the 3D model. So, well, first of all, you can explore the 3D model. And if you mouse over the web page, you can see a 3D, if it knows about that object, it will highlight a 3D bounding box. And you can click on it and see that in situ. This is the assumption by Andrea Kamasei. Here's another sculpture. So I just find this wonderful. You can create these associations between mentions in the text and 3D regions in the point cloud. Okay, but this works from a single category. So basically you have to analyze a page at a time. It only knows about the Pantheon. Okay, even though, as we said, there's kind of association that exist across categories of buildings. So if you consider all cathedrals in the world, if you look at their facades, they all have similar elements. They often have things like rose windows and portals and tympanums and towers and so on. And if you look at their floor plans, they all have, they're all, again, unique, but they have similar layouts and structures. Hey, Charlotte. Oh, I'll talk to you in a minute, Charlotte. Okay. Sorry, kids are home today. Let's see. So it would be great to have a technology that could understand all of the rich commonalities that underlie related buildings like cathedrals. Okay, so for that, we've turned to another project. I really love this. This is one of my favorite websites. It's called Wikimedia Commons. It's sort of a sister project to Wikipedia. And what it is, well, it says right here, it's a collection of 77 million freely usable media files to which anyone can contribute. It's kind of a crowd-populated database, visual database of the world. Visual, it has audio too, all kinds of media. And I think it's underexplored, especially in computer vision. So I'll talk about what this is, but it's a very, very rich visual data set. So it's organized into categories. So it's not just a flat set of 77 million objects. It's organized into categories. So there's a category of cathedral. And I apologize, there's going to be a lot of screenshots of websites because I really love this Wikimedia Commons. I kind of think of this as like it's what the internet was designed for, is kind of the vibe I get from this site. Okay, So there's a category called cathedrals. There's a bunch of subcategories under it. All categories have images in that category. So, okay, if you explore enough, you'll find a page of category of cathedrals organized by country, Austria through Vietnam. Here's the beginning of that webpage, a very, very long webpage. And each of these thumbnails links you to a category, which is a specific cathedral. Okay. There's cathedrals in France is its own page. I guess evidently there's many cathedrals in France. Here's a number of them. Again, each of these thumbnails links to its own category page. If you explore enough, you'll find a category page for individual cathedrals like the Notre Dame in Paris. And you see photos, you see many photos, tons of rich imagery. Well, the Notre Dame Cathedral is probably the most organized of these. The level of organization, this is all from the crowd. So some cathedrals are more lovingly curated than others. People love the Notre Dame Cathedral, it turns out. Okay, so you can see historical photos, labeled by year. Notre Dame Cathedral has its own rich subcategories, including exterior things that are inside and outside of the cathedral. If you drill down enough, you'll eventually find like specific objects like the great organ of Notre Dame de Paris. Again, each of these categories has pictures, in this case of the great organ. And there's subcategories of this too. So if you ever want to see pictures of chamades of the great organ of Notre Dame of Paris, they have that. I didn't know what a chamade was, but evidently it's an organ pipe that's oriented horizontally instead of vertically like most organ pipes are. Okay, so just very rich, beautiful data illustrating many different aspects of every cathedral in the world. Okay. And there's not just images, but also language. So many, not all, but many images have captions. Here's an example of an image with a caption, Notre Dame de Paris, the stalls designed by Robert Ducat and the choir organ seen from the gallery. Oh, there's another organ in the Notre Dame Cathedral. Here it is. These stalls, I think these are called choir stalls. These are where people in the church, for instance, the choir maybe sits. So, there's this richness of both imagery and also text associated with that imagery. And it's all imbued in this thing that we can reconstruct with 3D structural motion methods. Okay, so we pulled all this together in a paper that is appearing at this ICCV called Towers of Babel, with wonderful co-authors Xiaoshi Wu, Hadar Avabukalor, and Jin Sun, where we tried to, well, first of all, create a data set derived from Wikimedia Commons that connects the imagery, the language, and the 3D geometry, and then explore some applications, but mainly put this out there as a resource for exploring the connections between 3D geometry and language in computer vision. Okay, so how do we make this? So you can download all the images from a specific subcategory like Notre Dame de Paris and all of its subcategory, the tree of this hierarchy rooted at that node. You can download all those images, run structure motion. We use ColeMap to get 3D point cloud and camera poses. And you can run this on all cathedrals that are indexed in Wikimedia Commons. And so you have your 3D from structure motion, you have the images, and you also have the captions that are associated with these images, which are very varied and sometimes even mention very specific objects. Like, I guess this is a Strix in the lower right-hand corner here, kind of a demon. And you can, again, you can run this on all the cathedrals indexed in Wikimedia Commons and come up with a database of 3D scenes. We chose cathedrals just because of this. There's so many of them and there's this rich kind of structure underlying them. But we've also run this on other categories too that we're releasing. And taking these, again, raw point clouds and trying to, we sort of did some basic things to try and use this language to imbue them with meaning, like annotate things. And I'll talk about that. Okay, so I guess one main message is like, please, I think I'd love people to play with this data set. I'm very excited about this kind of data. So it's called WikiScenes, this data set. And it's comprised of 99 cathedrals and other types of landmarks as well, and 63,000 images paired with text descriptions. And another nice thing about Wikimedia Commons is that it's composed of freely licensed data, so it's easier to use for research purposes. We also have a data sheet along with this data set explaining how and why it was created. Okay, so a couple of goals just to start out with. So what we want to do with this is, well, one way to put it is bring structure motion into the 2020s. Right now, it's very popular, a very interesting topic to explore multimodal computer vision paired with things like language. So, it's high time we try to do that with these structure motion based reconstructions too. In particular, we want to create a resource for language understanding grounded in these 3D models. I'll talk about that. And with one goal being to learn semantically aware representations of 3D scenes. So things are not just point clouds, but have meanings associated with them. And you can also compute semantic correspondences across families of related scenes, like all cathedrals. And I think there's many more applications. I'll talk about some at the very end. Okay, so one key principle underlying the use of this data is that the images in the data set and the 3D structures ground language in an interesting way, meaning that they tie language with real world objects and settings. Okay, they tie language to the real world. So you might have an image with a caption like the large organ of Notre Dame de Paris. And because this image is registered with this 3D model, a 3D point cloud, for a given pixel in this image, you can look up, if that pixel corresponds to a 3D point in the model, you know that that point is associated with a specific 3D point. And you get some things fall out very naturally. So if you have another image that overlaps with that image, you can then say, okay, this point is the same point this point in image 1 is the same point in image 2. And therefore, if you want to learn things like semantic representations, let's say you learn semantic segmentation from this data. Whatever label you associate with this pixel in image 1, you should associate the same label with this pixel in image 2, because they're the same point in 3D. So there's this kind of very, very nice 3D consistency property that you can exploit if you're learning semantic representations from this data. Okay. By the way, this image may have a caption in a different language. We haven't exploited this in our work, but Wikimedia Commons is a multilingual corpus of data. And so there's also a potential to learn kind of cross-lingual representations from this kind of data. Now, these are ways to link concepts within the same cathedral, Notre Dame in this case, but from the language, you can also start to associate concepts across cathedrals. So you'll have other images in other cathedrals, in this case, an image from Chartres Cathedral, labeled organ. And so you can learn general visual concepts spanning these scenes. Okay. Okay, we have this data set. We did some very basic things to learn semantic concepts from it. Actually, it's things that are in some ways too simple, but we tried some simple approaches to learn semantic concepts. So the first thing we did is try to mine specific kinds of names of specific parts of cathedrals from this data. Okay, so we took all the captions, extracted all the nouns using NLP techniques, and then, if you just count nouns by frequency, the most frequent nouns are not necessarily ones that are associated with specific, parts, concrete parts of cathedrals. They're often things like, picture or photo or detail. Okay, but again, going back to this guiding principle that this 3D structure grounds the language. So you can look at, regions of 3D structure associated with images that have this, that refer to this noun. So if you take a more abstract noun like view, and look at the images and what parts of the scene those images look at, those parts will tend to be much more spread out and diffused over the entire model compared to nouns that refer to specific 3D concrete parts like portal. Okay, so these heat maps represent, okay, which parts of the scene are images that refer to these nouns looking at, and the portal part is much more encapsulated and compact compared to this more abstract noun view. Okay, so here's just an illustration of that. Images that contain the word view will tend to be looking at all parts of the scene, whereas images that have a concrete noun like portal, a concrete part like portal, will tend to be focused on a specific region. Okay, now you can formulate this as kind of like graph connectivity analysis problem. If you create graphs where for each landmark, the images are nodes and edges link images that are overlapping in see overlapping parts of the scene, then these subgraphs corresponding to images with concrete labels like portal should be more clustery and more compact. And that should be true across all, across different cathedrals. So here's a graph for a specific cathedral, but we create a graph for each individual instance. Okay, and using graph connectivity, you can kind of pull out the nouns that refer to specific parts. Again, going back to an older paper, this is related to a great work called Scene Segmentation Using Wisdom of the Crowds from more than 10 years ago, where they used basically image composition as a cue for segmenting the scenes into different objects. The idea is images tend to focus on objects rather than having a bunch of parts of different objects partially visible. Okay, so this analysis of 3D consistency allows us to distill a set of concepts referring to specific parts like facade, window, chapel, organ, nave, tower, choir, portal, altar, statue. Okay. So once we have those categories, or those concepts, what we want to do next is try to use them as a form of weak supervision of kind of feature-wise image representations. So, okay, here's an image again. I showed it before. It refers to organ, but there's more in this image than an organ. So we have sort of this weak supervision where we know that organ is a salient concept here, but we don't have labels as to which part is the organ. So somehow we want to take these weak image level supervision and learn feature, sort of dense feature maps that are where the features are correlated with concepts. And we also want these to generalize across all cathedrals, including ones you didn't happen to see during training. There may be cathedrals that aren't present in Wikimedia Commons. Okay, so we want somehow to be able to localize that this is the organ from this kind of data, from this weak supervision. So again, we rely on this 3D consistency to train these kind of representations. So here's two images. I think these are of York Minster. Here's 2 points that we know are in correspondence from the structure motion model. And so if you take, if you train a deep network to produce a dense feature representation of these images, you know that these 2 features corresponding to these 2 pixels are the same point. And so they should have a similar representation, a similar feature map, similar features at that point. So, this is sort of like a contrastive learning style thing. These are positive feature pairs that you want to have similar feature vectors. And then images that don't match those images, and you say all the features in those images and don't have overlapping semantic concepts associated with them. You know that these features should not be related to these. So you can kind of push those negative feature pairs apart. Again, this is basically classic metric learning or contrastive feature type learning. So far, okay, so we can use 3D consistency as a cue for learning feature representations. So far, it's very similar as described to how recent deep learning techniques for learning geometric feature descriptors. But we also have these labels associated with images. So in addition to this supervision on which features should be similar, we can also say that if you aggregate features across the image, you should be able to classify, you should be able to come up with an image label that is that matches the what we're able to extract from captions. So we also want to be able to use these features to classify this as tower. Okay, so we have both a kind of semantic loss and a feature-wise loss. Okay, so here's just some results. So you can learn concepts of portals, and you can learn to segment more or less portals and images just from this weak form of supervision. Here are some segmented organs from different cathedrals, including cathedrals not seen during training. Actually, I believe all these are unseen scenes during training. So this shows generalization to new places, unseen places. choir. So okay. This thing called a choir in a cathedral, and one common aspect is these thing called stalls where people sit. Okay, so it's learn the concept of choir and to look for choir stalls, statues, etc. And then you can lift these concepts to 3D as well. So if you have a 3D point cloud, you can classify each point in that point cloud by saying one simple way is every point that sees that, every image that sees that point gets to vote on a category label for that point, and you just take the winner, the winning label and color code the points accordingly. So here's a cathedral unseen during training, segmented into categories according to the learned semantic feature representations. Okay, so purple is nave, red is organ. There's an organ here. You can see choir stalls here. This is like this hot pink color. And so I'll just play this. You can see the 3D point cloud segmented. For some reason, I think it thinks that the dome is a chapel. So that's a limitation. It didn't actually discover the concept of dome by mining from this, from the captions. But otherwise, if you compare it to semantic representation trained without this 3D consistency, the results we achieve are much more coherent and more accurate. So this 3D consistency is a powerful kind of cue for training feature representations. Okay, that's our work in a nutshell. I just want to say, I think we've just scratched the surface of what is possible with this kind of data, and I'm very excited in general about bringing more language and more meaning into 3D models. So, okay, so for instance, we did sort of the most reductive thing possible. That is sort of the first thing I guess you do in computer vision, which is come up with category labels and classify things according to those labels. But that, language and structure is much richer than is captured by this kind of rigid classification of things into objects. So first of all, many concepts, we didn't discover every concept like dome. Concepts are hierarchical. You can have things inside other things. Language doesn't just describe parts. It describes, for instance, styles. You can have Gothic cathedrals and Romanesque cathedrals, and many other kinds of properties that can be captured in language. You can have positional language. Something can be the north thing. Something can be next to something else. There's all of this richness and compositionality that's inherent in language and in these 3D structures that I think would be very interesting to explore. Okay. These data sets have things that are not photographs. They have floor plans, cross sections, other architectural drawings like this one from Notre Dame Cathedral. It even has like the scale of this, how high things are. There's paintings, there's engravings. Some of these, these cathedrals, many of them have been around for centuries. So there's all sorts of historical media associated with them. And especially the floor plans would be very fun to try and do better reconstruction with that kind of data. And also we're working on extending this to more categories, mosques, castles, etc. Things that, categories of buildings that share some kind of commonality. Right now we're just using captions, but there's all sorts of rich descriptions, including Wikipedia pages. 3D Wikipedia is an example, but there's also a whole Wikipedia page just talking about the architecture of cathedrals. It seems logical that you try to use this kind of data to automatically understand, come to a better understanding of how cathedrals work. I also like the fact that there's both categories of objects, like tympanums. There's many, many tympanums in the world, and specific ones, like in the Notre Dame Cathedral, you have the tympanum of the portal, the Last Judgment, basically. So, there's like these individual artworks that exist as a category, and I guess I'm fascinated by that interplay between categories of things and specific instances that have names. And ultimately, I think it'd be great to be able to have such rich understanding of these models that we're getting that you can create illustrations like the one I showed at the beginning of this talk. I think there's other applications too, like learning cross-lingual representations. There's a very interesting paper from Carl Vondrich and others on using images as a way of helping machine translation, essentially. Again, you're grounding concepts with images, and you can use that to help train these concepts, the image of a bike might be the same between languages, and that can help you do translations, similar in this case, except you have this kind of 3D grounding. And in general, actually, I think you've seen this in a number of talks in this workshop. I'd love to have data sets that become kind of the next generation ShapeNet. Things where there's semantics, there's some kind of meaning inherent in the data, but that are more I guess, larger scale scenes, more complex scenes compared to ShapeNet. And in our case, we also have this very interesting language aspect of the data. But other data sets that I think are very interesting are things like common objects in 3D and Objectron that we heard about earlier today. Okay, so with that, I'll wrap up. Thank you so much for your attention. Thank you so much for the organizers and the co-authors on this work, Xiaoshe, Hadar, and Jin. And I really am excited about this idea. And please visit our webpage for data and code and other good things like that. Thank you very much.
Thanks a lot. This was really an exciting talk, and the data set is very interesting. I'm looking forward to looking into that. While people think about questions to type in our various chats, I'll ask one high-level question first.
Yeah,
and
great.
That would be, have you thought about the other direction? So currently you're using geometry to ground your language in, but there might be also the possibility to have the language help your reconstruction, right? If you know that a pixel is part of an organ, you have certain assumptions about these 3D structures that you expect in this region.
Totally. I think that's very interesting. So, I mean, one, I guess, secret behind running structure motion on internet photos is that very often, here's a very specific instance of that. The model will not be assembled into one coherent part, but will be broken into many parts. So, you'll have first of all, the interior and exterior will tend to be separate connected components because there's not a lot of visual features linking those. And, even inside, there might not be a lot of visual connectivity. So first of all, even if you don't do anything, you ought to be able to use language to assemble these parts in a better way. But yeah, ultimately, I think right now we're taking the view of, okay, we have these structure motion methods that just give us these God-given point clouds. But I think ultimately you want to rethink structure motion from the start with this kind of data. Now, for cathedrals, I think you might have to bootstrap it. How do you know where an organ should be in a cathedral until you've observed it in many different settings? Maybe you need to first build a data like this to learn those associations. But yeah, ultimately, I think you're absolutely right. We should be also using that kind of data to aid in reconstruction.
Thanks a lot. There's one question from Andrea, who is actually here, so he can ask himself.
Oh, cool.
Yeah, hi. Actually, I was wondering, so you showed that you cannot combine language and 3D reconstruction for things like buildings. What about applying that to, say, deformable categories like humans or animals? Would you be able to, say, learn the different parts of your human body by just, looking things up in Wikipedia and linking that knowledge to a 3D model like SMPL, for example?
Totally, yeah, I think so. I've been approaching this as a lover of architecture. So I think that's maybe cathedrals are very niche. I happen to love them, and they're beautiful objects. But yeah, perhaps this idea could be extended more generally. I think we're starting to see this rich, integration of vision and language in the community. There's all sorts of interesting things happening in that. I don't think there is enough work being done on this kind of, things that have 3D structure with named parts, doing analysis of what do you call the various things, that comprise that object. Cathedrals are kind of an extreme example of that because they have so many parts. They're big and huge and have they're hundreds of meters in size. But yeah, I think it would be very interesting to, use things like Wikipedia and Wikimedia Commons as a way of trying to get more common sense knowledge about the objects around us, whether it's a cathedral or a person or an animal. And I think it's, these data, these kind of internet projects like Wikipedia and Wikimedia Commons are so, I mean, in some ways they're extremely lovingly curated. And I know this, this workshop's on unsupervised learning, but I really think that these kinds of resources, these crowd resources, are a very rich source of knowledge about the world that we should be using.
Thanks a lot. If there are no more questions, then we are also perfectly on time to switch over. Thanks again, Noah. Very interesting talk.
Thank you so much.
Thank you.
Our next speaker is Adel Ahmadian, who is here. Yes. He has a PhD from UIUC and has been working over the years on various different computer vision projects. He is now a researcher at Google and has been working on pose estimation, tracking, and maybe most notably in this context, he is also one of the creators of the Objectron dataset, which he will be talking about in the next presentation. You can start sharing your screen if that works.
I'm trying to share the screen. Let me try it again.
Wonderful.
Can you see my screen?
Yes, everything works.
Perfect. All right. Thanks, Noah, for the connection between the cathedral and Objectron. I'm going to talk about the Objectron project that we did over the last year and its connection to 3D object understanding. This is a work with my co-workers, Lankai Artsian, Johnny, and Matthias at Google. So at Google, our goal is to organize the world's information. And for us, everything starts with that search box. So when you search for an object, like for example, an IKEA chair, we are very good at figuring out what you're searching for, like what you want to see. And the web is like a treasure trove of images. Like we're also very good at figuring out, hey, these are all the images of this object that you care about. So when we have all of these images, and all of them are from multiple views, it becomes very natural to start thinking about, can we build like a 3D model out of this search query? And this would help us with a lot of the problems that we wish to solve, including like pose estimation, what are the sizes, can we have a different views of the same object, and so on. So from this perspective, unsupervised 3D object understanding is very valuable to our products and our goal. Before I talk about the Objectron project, I want to plug a bunch of the models that we make, namely the Objectron solutions. We built these tiny and very fast small models that they can estimate the 3D pose of an object. And we put this on every device you can imagine. Like you can run them on your mobile, on the web via Python, or even you can deploy them on Edge. And if you want to like use them in your product, or you want to use them in your course project, we would be very happy to help. So going back to the 3D object understanding problem, recall that our goal is to understand the 3D pose or 3D shape from a still image, from a still monocular RGB image. But this is a very, very difficult problem to solve. And namely, understanding 3D from 2D images is difficult. We were looking for a way to boost the 3D signal in these images. And there are a lot of ways you can do this. Like many folks, they would incorporate different priors. They would use the stereo images, a structural light, or motion. We opted to use motion, and that's how you go from still images to object-centric videos. Like we were thinking, like if you have a video of object and you're looking at it from a different views, it would help understanding 3D better. And this also matches nicely the way that we as a human would also make progress in understanding 3D. Like, for example, there was this example I heard a long time ago that when you are a kid and you want to like learn what is an object, like what is a chair, you would crawl around it. You would try to look at it from different perspectives. But when you are an old man, you would just look at it and you're trying to recall it from your knowledge. So we went from still images to object-centric videos, and that is essentially the object-oriented data set. So in order to help with the 3D object understanding, we created this large data set. And one thing that is shared in this data set is it's a collection of videos, and they're all object-centric. Like they would look at the same object from different views. And we have annotated the pose for this. And we also have the camera poses, object poses, AR point cloud, and stuff like this. We try to make this very easy and accessible for both researchers and industrial applications. Like if you want to use it in your pipeline, it is super easy. There are a bunch of different wrappers and notebooks and everything. And for different tasks, for example, if you want to use it for 3D pose estimation, we also have a really good evaluation metrics like 3D IOU that you can evaluate your models and compare it with the state of the art. Overall, we roughly collected about 50,000 videos, and that translates to about 4 million annotated images in 9 different categories. And these categories, they range from small objects like cups and shoes to relatively large ones like chairs and bicycles. There are deformable objects and rigid ones, like you have both bikes and you have cameras. And there are objects with symmetries that makes the problem kind of difficult, for example, cups and bottles. So when we wanted to collect this, the very first problem that we had was how can we do this at the scale? Like we didn't want to have like a small data set of like 10 or 100. We want to have a data set of thousands of videos and images. And when you want to collect something at a scale, the easiest way is to use devices that everyone has. In this case, for us, it was a phone. So we went and we asked our data collector to use their phone to collect a video of the object. So it has its upsides and downsides. The upside is it is easy deployed to like 10 countries and 5 continents, and we could just do this at a very rapidly. Also, if your application is developed for phone, you are in distribution of the model. Like you're looking at the same type of videos that you get from the phone. But if you want to like deploy it on different devices, then you might have some shift in the distribution. To annotate this, remember all of our videos, they have a 3D pose of the object. We opted to use this annotation in 3D, where our annotators would put a 3D bounding box in one frame, and they would look at the different frame, and they would try to adjust it, as shown in the figure on the right. One specific thing about our dataset is because it was collected on the phone, during the recording of the video, we also collected the AR session metadata. And this is those SLAM algorithms that you run on device, for example, like ARKit or ARCore. And they provide a very accurate camera pose that is in meters. Because they have an accelerometer, they can record the pose in a scale. So all of our bounding boxes, they are actually at the correct scale. So this would look, for example, these are the example of samples that we have in our dataset for the category chairs. All of these 3D bounding boxes, they're very well sticky, and they're very accurate. When we say accurate, it is very hard to measure the accuracy of the ground truth. In order to have confidence in how accurate and with our annotations are, for some videos, we ask 10 different annotators to annotate the same video, and then we measure the variance. And for a class of chair, this variance is under 2% of the scale. So we can confidently say that these annotations are relatively accurate. The videos that we collected, we had two properties. One, we wanted this video to be like essentially 360 views of the object. When we say 360 views, there's an asterisk that this is a 360 view of the upper hemisphere. What does it mean is all of these are a camera. Okay? These are the phone camera. And usually when people collect a video with the phone camera, they hold it at a 45 degrees angle. So this pops up as a heavy bias in the elevation of the data set. And this is not just common to Objectron. Other data sets that are collected by videos or through YouTube, they would have the same elevation bias. This is just something to be aware of. Our elevation is heavily biased toward 45 degrees, and the azimuth of the object, they pretty much cover the entire 360 views. So I'm going to talk about two applications that we try to provide as baseline for the Objectron. One is 3D pose estimation, and the other one is 3D reconstruction. And if you come up with a new application for it, I'm all ears. So for 3D object detection, we came up with this very simple baseline model that we use the efficient net to extract features, and then we add a fully connected and then a regression layer to regress the XY key point of the 3D bounding box. And then it is followed by a EPNP to lift these three XY key points to 3D. And that would give us a 3D bounding box. So this baseline model, it works reasonably well. You can see some examples on the right side here. And we wanted to be able to evaluate this. Evaluation, there are different ways to do this, and you can refer to the Objectron papers for different metrics. The most interesting one that we have is a 3D IOU. So 3D IOU, intersection over union, it's usually in the 3D literature, it is approximated. So we tried to come up with an algorithm that would compute it very, very accurately. And we thought, okay, we have two bounding boxes and we want to compute the intersection of it. How can we do that? As it turns out, if we rotate one bounding boxes to become axis aligned, the other bounding boxes, there's a well-known algorithm in computer vision and computer graphics called polygon clipping that lets you clip the second bounding box with the first one. And this is actually used in a lot of game engines, like when you have a view and you want to render the world around you in that view, you don't want to render the world that's outside the view of the camera. So you clip the world outside and you just keep the one that's inside. And the same algorithm can be used for 3D IOU. So we intersected different faces of the polygon with the axis aligned one, and then we compute the intersection using convex Hall. This algorithm has some caveats for symmetric objects because with symmetry, you cannot really estimate that symmetric axis very well, right? For example, when you look at a cup, what is the front face of the cup? It is ill-defined in this case. And for these cases of symmetric object, we just rotate it and get like multiple instances, and we pick the one that produces the minimum. So with this 3D IOU, for example, you can see like what would be like the baseline results for different models across different categories. And these results, at the time that we are talking at this ICCV, this is not the state of the art anymore. Some new folks have come up with a better model that would beat these numbers. Everybody's talking about NeRF, so we are not an exception here either. We love NeRF. I mean, if you have object-centric videos, it adapts well to the whole NeRF infra and pipeline. And Objectron is not an exception. You can train NeRF model on Objectron. What's interesting for us is we actually use NeRF for generating novel views that are missing in the dataset. As I mentioned earlier, our dataset N is heavily biased toward specific views in elevation. And NeRF can actually help us avoid those biases. Like we can generate views that are typically not in the dataset. The second application of it is it gives us a depth map, and the depth map gives us a very, very sharp depth map, even to my own surprise. And these depth maps are not in the dataset, but we can use it. An interesting thing about NeRF is we also have a 3D bounding box, and if you call the depth map, given that 3D bounding box, you get a segmentation mask essentially for free. Now there are some caveats, like we assume that there are no other objects in that volume of the 3D bounding box except the object that we care about. And this is true mostly for many of the images in the bounding box, images in the object on dataset. There are also some trickery going on to remove the ground plane from the dataset, and those hacks would actually help to improve the segmentation. So thank you so much. If you want to get the data set or some examples of it, you can refer to our website. And if you want to download the pre-trained model, you can use MediaPipe, which is a framework for running inference on these devices.
Thanks a lot. That was a very interesting and comprehensive overview of the Objectron dataset. While people are thinking about questions, I have one question about the last part that you presented. You showed that NeRF can give you novel views. And then an immediate question is, have you tried basically supplementing your training data for your pose estimation with these NeRF views to see if that improves the detection performance?
That's right. Yeah. So there are two things. One is we can, for example, when we are training our models, especially the production model, we try to normalize our views for so our data set is breaking down into many parts, and they are classified into different views. Like we have a top view of the object, side views of the object, and so on. And we can actually use this. We have some prototype of it that we augment those missing views using this technique. The other one is when we have some objects that are only having a limited number of views, and you want to interpolate those between views from them. Again, NeRF would be a good way to augment the data set. The downside of it is training NeRF model, it can take a while. So this is a very expensive process.
Thanks. That's very interesting. Are there any more questions in the two different chats that we have? It does not look like it. Then thank you very much.
Thank you so much.
And then we're moving on to the last talk before our panel session. The next speaker is Shalini DeMello. She is a principal research scientist at NVIDIA and received her PhD from UT Austin. She has been working on self-supervised and few-shot learning, 3D reconstruction, viewpoint estimation, and human-computer interaction. And a lot of this work has also already been on 3D objects in the wild, images and videos, and that's why the talk is going to be very fitting for our workshop, and we're very excited to hear about part correspondences and temporal consistency. The talk will be pre-recorded, if I understand correctly, and then you will be here for questions afterwards.
That's right.
Hi, my name is Shalini DeMello, and I'm a principal research scientist in the Learning and Perception Research Group at NVIDIA. Among other things, I'm interested in learning with less labels and data, and also in 3D reconstruction. In line with the theme of this workshop, my talk is going to try and answer the question of whether we can use object part or temporal correspondences learned in a self-supervised manner to help us to improve 3D reconstruction of objects in the wild. Today I will describe two of our recent works that explore 3D mesh reconstruction in the wild. One which uses single view images and the other that exploits temporal information from videos. The first work that I will describe is called Self-Supervised Single View 3D Reconstruction via Semantic Consistency and was published at ICCV last year. The task that we're trying to solve is as follows. Given a collection of images of a specific category, we wish to accomplish two things. The first is to learn a category-specific 3D template from scratch, as shown in the top figure A, where we learned this template for the bird category. And the second is to learn instance-specific mesh reconstructions based on the learned template. We assume that the only supervision that we have is the collection of images themselves and a silhouette mask of the foreground object in each image. To solve this task, we adopt Angjoo Kanazawa's awesome work on category-specific mesh reconstruction from ICCV2018. In CMR, the model takes a single view image as an input and jointly predicts texture, the deformation of a 3D mesh template shape, and the camera viewpoint. In this work, the texture is represented as a texture flow that maps pixels from the input RGB image to the UV space. One of the nice things about this design is that the texture flow can map anything from the input 2D image space to the UV map space. For example, here it maps part segments or key points of a bird image to the UV space, which can further be mapped to the 3D mesh. This key idea plays a central role in the two projects that we will describe today. In its shape branch, CMR predicts the offset to be applied to each vertex of a 3D template shape. It models the camera as a weak perspective camera that basically tells us from which view the image is captured given the 3D mesh. Then it uses a differentiable renderer that takes the textured mesh and the camera viewpoint as input and outputs the rendered image. If the predicted camera viewpoint and the 3D shape and its texture are correct, then the rendered image should look like the input image, and we can use this photometric consistency between the two images as an objective for training. Besides comparing images, CMR also renders a foreground mask and compares it against the ground truth foreground mask. So that's the basic framework of CMR. However, in CMR, there's an assumption that both a category-specific 3D shape template and the viewpoints of all images are known a priori. Specifically, the viewpoints are computed from 2D key point annotations on images. However, this requirement makes it challenging to generalize CMR to other objects in the wild, for example to horses, cows, or even penguins, where we may not have the 3D template shapes or 2D key point annotations. So in our work, we focus on self-supervised single-view 3D reconstruction, where there are no ground truth 2D key point, 3D templates, or viewpoint annotations available. However, if we directly remove the camera viewpoints and the 3D templates from CMR, not surprisingly, the results become unrealistic, especially from unobserved views. Observe the red box. Here we reconstruct a bird from its side view, but if we view the reconstruction from the front side, it doesn't look like a bird at all. This is due to the inherent camera shape ambiguity present in the problem of single-view 3D reconstruction. To understand this better, let's look at another example. Here, given the image on the left, we show two possible reconstructed meshes and predicted camera viewpoints in the middle and their respective rendered images on the right. Although both the rendered images match the input image, the prediction in the first row has incorrect shape and wrong camera viewpoint. But note one key observation here. Since we obtain the shape of a particular object instance by deforming or moving the vertices of a 3D template mesh, the semantic part labels across the different mesh reconstructions should all be the same. For example, if the red part of the template represents the head of the bird, but during deformation, the first row incorrectly deforms it to be the tail, we know that the shape predicted in the first row is incorrect. So in order to make correct shape predictions, we need to make sure that the semantic part labels of the vertices on the template do not change. But the question is, how do we know which semantic part of the bird each vertex on the mesh belongs to? Although it is hard to get part information on 3D, we can obtain semantic parts across instances on 2D images using a self-supervised approach such as SCOPS, and from there we can eventually get the part labels on 3D meshes. As shown here, these parts are consistent and correspond to each other. For instance, all red parts in these bird images indicate heads, while the green parts look like their necks. In a correctly learned 3D reconstruction network, the part label of each point on the reconstructed mesh's surface should be consistent, however the shape of the bird may change. For example, here vertices labeled in yellow will always represent the wing part in the reconstructions, however the template is deformed. So how can we map these semantic parts from 2D to 3D to regularize our model? Recall that we can use the texture flow learned by a reconstruction model to map the semantic parts in 2D images to the UV space. We then average all semantic UV maps to get a canonical UV map. The average operation cancels out noise in each individual semantic UV map caused by inaccurate texture flow or occlusion. This obtained canonical semantic UV map is shared by all instances of the same category and assigns a part label for each point on the reconstructed mesh. In the dash box, we can see that by warping the semantic UV map onto these meshes, we're able to know which parts on the meshes are heads and which are wings, etc. So similarly, we can warp the canonical semantic UV map to the estimated shape and compare its rendering with the 2D semantic part segmentation that we obtained from SCOPS. If both the shape and the camera viewpoint are correct, then the rendering will match the 2D semantic part segmentation of the 2D image. Thus, we can use this loss to correct the predicted camera viewpoint and the shape. The effectiveness of the semantic consistency constraint can be visualized by this example. Given a flying bird like this, the model learned without the semantic consistency constraint reconstructs a bird that matches the image and its foreground mask. However, if we warp the canonical semantic UV map onto the reconstructed mesh, we find that the head part of the template is incorrectly deformed to form the wing, and hence is not consistent with the other instances from the category. But by adding the semantic consistency constraint, the camera viewpoint and the shape can both be corrected, and the semantic part label on the reconstruction will be consistent with the other instances from the category. So that's the semantic consistency constraint that we introduce in this work, which allows us to reduce ambiguity if we don't have camera viewpoint supervision. Another goal of this work is also to learn a category-specific 3D template mesh from scratch using only the collection of 2D images available to us. To learn the template shape, we start from a sphere and update it every k epochs during training. Each update introduces more details to the template until finally we get this template that looks pretty much like a bird. For each update, we first use the encoder to extract features of all training samples and then feed the average feature to the decoder. The output of the decoder is used to update the current template to a new template. Here we summarize our self-supervised single-view reconstruction framework. Our main contributions are a semantic consistency constraint that helps to jointly learn camera viewpoint and 3D shape reconstruction, and a progressive method to learn a 3D template shape for a category from scratch. Here we show some qualitative results on bird images. Our model can successfully reconstruct different types of birds, such as ducks, larger birds, or even a painting of a bird, as shown in the last column. We also train our model on rigid objects like cars and motorbikes and are able to successfully reconstruct them. And also on non-rigid objects like zebras, horses, and cows. Here, I also show some quantitative evaluations of the proposed method. We use the intersection over union or IOU metric for object mass and the PCK metric for the key point transfer task. I will skip the details of the evaluation process, but the results here show that our method performs on par with methods that require supervision from 2D key points or category-specific 3D templates for learning to reconstruct from single view images. So to summarize, in this work, we learn a single view mesh reconstruction model and a category level template. We learned this model from only a collection of images and silhouettes. Specifically, by utilizing cross-instance correspondences, we are able to reduce ambiguity of single view reconstruction and jointly learn both the camera viewpoint and 3D shape reconstruction. So that was all with regards to mesh reconstruction from images. Now, if you consider the temporal correspondence of frames in videos, and this mesh reconstruction network for images that we've just learned, one natural thought is how we can combine the two to solve the problem of video mesh reconstruction. This was the exact challenge that we set out to solve in the work titled Online Adaptation for Consistent Mesh Reconstruction in the Wild, which we published last year at NeRFs, and I will be describing this work next. In this work, we proposed a semi-supervised method to reconstruct temporally consistent 3D meshes of deformable object instances from videos in the wild. Most existing work on dynamic mesh reconstruction relies on strong shape priors. For example, the SMPL model for the human body or the 3D morphable model for dynamic faces is often used for reconstructing 3D faces or human bodies. Our work, on the other hand, focuses on reconstructing animals from videos in the wild. This is a more challenging task in the sense that we don't have access to any 3D scans of these animals and hence do not have any kind of shape prior for them, because it's virtually impossible to scan these sorts of wild animals in controlled environments. So the question is, how can we reconstruct these animals simply from their 2D videos? So one simple and naive solution that comes to mind is to apply the single view image reconstruction model that I described earlier independently to each individual frame of the video. However, on doing so, the reconstructed object shows temporal discontinuities in shape and flickering camera viewpoints. This happens due to many reasons. First of all, most of the videos we found on the internet are captured by mobile phones, and they contain low-quality video frames, small objects, and appearance variations like lighting, etc. Almost all of them also have large domain gaps with the image datasets, like the ones that we use for training the single-view reconstruction models. Another solution is to annotate the bird videos as much as possible so that we can retrain the image-based models for the video domain. However, to annotate all frames of videos is never easy. It requires extensive human labor, and we cannot guarantee the coherence of the annotations. So the question is, how can we resolve all these issues to be able to reconstruct wild animals in videos? In this work, we propose an online adaptation approach as a solution. We first train a single-view reconstruction network using a group of annotated images. During testing, we fine-tune the network to let it adapt to a specific video. Online adaptation is also called test time training. The benefit and the difficulty here is that we do not have any labels on the test data, which is, in our case, of the testing video. So we need to figure out effective self-supervised objectives that we can improve the network with during test time training. So let's first look more carefully at the improved single-view reconstruction model that we introduced as part of this work. So recall the single view image reconstruction model that we described in the earlier part of this talk that jointly predicts both the texture, the shape, and the camera viewpoint based on Angjoo's CMR paper. So the CMR method is mainly designed for symmetric objects. However, what if the objects are not symmetric? For instance, when a bird rotates its head as shown in the pictures on the right. So in this work, we dropped the symmetry assumption of CMR and modeled asymmetric objects as well. To model an asymmetric object, instead of directly estimating the coordinates of its 3D vertices, we decomposed the representation of the shape of the object into a combination of basis shapes and additionally vertex offsets applied on top of the base combination. The base combination is still symmetric, while the deformation delta V is not. And that, in our case, can be used to model subtle asymmetric motion, like that of the head rotation of the bird or the motion of its wings, etc. To obtain a set of base shapes, we apply k-means clustering to all the mesh reconstructions obtained from the single view reconstruction framework that we discussed previously. As you can observe here, a base shape discovered in this manner corresponds somewhat to the identity of an instance. For example, it could be an ordinary bird, a flying bird, or a duck, etc. Observe that for a single video clip, since the characteristics of a bird don't change, for example, whether the bird is a duck or a large bird, these attributes stay constant for the bird throughout the video. So during test time training, we enforce the predictions of the base combination shapes, or more specifically the coefficients beta in our case, to be the same for different frames in a short video clip. We will talk about and discuss these constraints more in detail in the latter part of this talk. So much like the prior CMR work, we train the single view based image reconstruction model in this work with supervision from ground truth 2D silhouette masks, images, and known camera viewpoints, along with surface smoothing regularization terms. However, differently from the prior work, to enable greater dynamic deformation of the 3D surface across the video, we further utilize a key point matching loss, which we will describe next in detail. So as shown here, given an instance, if we know both its 2D key points and their corresponding 3D key points on the mesh, we can encourage our model to correctly deform the 3D shape by matching the projections of the 3D key points to their 2D key point annotations. But the question is, how can we obtain both the 2D key points with their corresponding 3D key points on the mesh's surface? So our solution is as follows. For the 2D key points, we employ ground truth annotations. And to find the 3D key points, we compute aggregated key point heat maps using the texture flow. So the key insight that we use to find the corresponding 3D key points is the fact that each semantic key point is always mapped to the same point on the template mesh's surface, no matter how the template is deformed, which is the same idea that we used previously to solve the camera viewpoint and shape ambiguity in the self-supervised single view reconstruction work. So practically what we do is that we first represent the 2D key point annotation as a heat map on the image. And then we use the learned texture flow to map these heat maps onto the UV space, as is shown in this image. We average all the UV heat maps to get a canonical key point UV map. This key point UV map is shared by all instances and indicates the location of each semantic key point on the 3D mesh. Furthermore, we can also use the learned canonical key point UV map to find semantic key points on each individual reconstruction for each instance. For example, the orange circle that you see in this image here represents the tail key point in each bird instance for each reconstruction. So notice that if the shape is reconstructed correctly, then the projections of the 3D key points onto the rendered image should match exactly the input 2D key points that are provided as ground truth annotations. So we explicitly enforce this key point matching loss to encourage the model to learn to reconstruct better shapes by matching 3D key points projections to their ground truth 2D locations. We find that the key point matching loss pushes the 3D key points to correct locations in the 3D space and leads to greater deformation of the 3D meshes. However, one issue is that instead of correctly deforming the overall shape of the object under consideration, this loss can sometimes result in noisy reconstructions with many spikes and a rough 3D surface to satisfy the key point reconstruction constraint, as shown in the red box. And in order to resolve this issue, we also utilize the as rigid as possible or ARAP constraint to encourage consistent local surface deformation in the base combination mesh and the final reconstruction. The intuition here is that the base combination shape will always be a smooth surface. Thus, its local graph should be preserved during motion deformation. Here we show more results of this improved single view image reconstruction model, where our method is able to capture non-symmetric motion such as rotation of the head of the bird, as you can observe from the images. Now let's switch gears and talk about how we employ this improved single view reconstruction model to a series of video frames of an instance of an object to obtain temporally consistent mesh reconstructions. As we mentioned before, once we have the image reconstruction model, if we directly apply it to each frame of the video, the reconstruction will be incorrect and inconsistent, as you can see here. Also note that for videos, the setting that we assume is that we only have access to foreground mass for each frame, but without any other information such as the presence of 3D meshes or 2D key points on the frames, etc. So to solve this problem and to obtain coherent reconstructions across a video, we propose to use an online adaptation procedure on each testing video. The key idea here is that even if we only have one video, we can still adapt the image reconstruction model to it by exploring self-supervision signals for online adaptation. So the key to enabling online adaptation is to find self-supervision signals in unlabeled test videos besides the foreground object mass that we have available for them. We find that there are several inherent properties of objects with respect to their shape, texture, and random part correspondences that are invariant to the shape deformation caused by the non-rigid motion of the object. During test time training, we enforce these properties to be consistent among different frames of the same video clip. For shape invariance, as we discussed previously, since the identity or characteristics of an object, or of the bird in our case, don't change over time, we enforce that the predicted base combination shape of the object be consistent across all frames of the video. For texture consistency or texture invariance, we enforce that the predicted UV texture map of an object be consistent for each frame of the video over time. Besides the temporal shape and texture consistency constraints, we also explore a part invariance constraint which is defined in the UV space. In order to compute the UV parts constraint, we paint random strips only on the object in the first frame and propagate them across all the remaining frames of the video. Previously, we had also developed a method to learn dense correspondences across video frames in a self-supervised manner, which works quite well at propagating object part strips across frames. For the task of video object reconstruction as well, we can similarly propagate the random strips from the first frame to the rest of the video using a self-supervised method for establishing dense correspondences between video frames. After that, we map the individual parts to the UV space using the learned texture flow for each frame and average across all the frames to obtain a more reliable UV parts map. We warp the average UV parts map onto the predicted shape for each video frame and render it back to the 2D space with the predicted camera viewpoint. We then compare the rendered UV part projections to their original propagated strip versions for the 2D input frames. And by comparing them against the original propagated strips in 2D, the predicted 3D shapes and camera viewpoints can be regularized over time. Here we show an ablation study where we do not use the proposed shape, texture, and part invariants during online adaptation. In the last row, we show the results of this configuration of our model. Observe that for this model, the base shape of the object changes from that of a duck to a bird over time due to occluded observations. This demonstrates the contribution of the proposed temporal invariance losses in stabilizing 3D reconstructions of deformable objects over time. Here we show another example on the bird category. And yet another example. Despite the abrupt change in motion, our model still reconstructs consistent meshes over time. To further evaluate the proposed method quantitatively, we compare mask intersection over union, or IOU, and key point projection accuracy using the PCK metric. Again, I won't go into the details of these evaluations, but the results show that our improved image model outperforms the baseline CMR model for all three metrics, and the online adaptation further improves the model performance as shown in the last column. Furthermore, a comparison of the last two columns demonstrates the effectiveness of the proposed shape, texture, and part invariance modules at improving the reconstruction metrics over time even more. Finally, we show an example on the zebra category, where the proposed method can successfully capture the zebra's walking motion. We note that differently from all prior works that attempt to reconstruct the zebra, our method does not assume any prior model for the articulated motion of the zebra. This is a pragmatic concern for most animal species in the wild that are not well studied. Even without assuming any articulation prior, our method is successful at reconstructing the zebra's motion to some extent. To summarize, in this work, we explored the challenging problem of temporally consistent reconstruction of deformable objects in the wild, for which we don't have any shape or articulation priors. To solve this task, we proposed an improved asymmetric model for single-view reconstruction, which can be applied to each frame of the video. Additionally, we also proposed an online adaptation procedure to fine-tune the single image model to each video using a set of self-supervised temporal constraints. And that brings us to the end of my talk. I thank you for your attention, and I would be happy to answer any of your questions. Hi, my name is...
Thanks a lot. That was a very interesting talk with very deep insights into the mechanics of all these methods. While people are thinking about questions to ask in the chat rooms that we have, I have one initial high-level question, and that would be on your part masks. Basically, you have shown that you can use this supervision that comes from SCOPs or these part detection models to improve basically every part of the reconstruction, the temporal consistency, the shape, the camera poses, and so on. And now my question is, if you have thought about the backwards process where you basically get improved masks. I've worked with SCOPs in the past before, and it's working very well, but it sure has some problems every now and then. So maybe there's a way to even use this lifting to 3D to improve the semantic consistency of these part detection models.
Yeah, definitely. So actually, that's a very good question. We had, we did actually experiment with this as well. This exact thing that you mentioned, which is to basically use sort of the average. So we take an average across all the instances in the UV space, right? And so that particular averaging step helps to remove a lot of the noise that SCOPs has. And so we did explore this, and this is certainly possible to sort of incorporate that average UV mask to further improve the segmentation, part segments that you can get out of SCOPs. That's a really good point, yeah.
Thanks. There is one question in the chat from Shangzhe. That is, what are the pros and cons of the texture flow representation for appearance in particular?
Yes. So I think so in practice, what I have found is that the texture flow doesn't always result in very crisp and sharp renderings. It tends to be somewhat blurry for sure. But then the alternative is, having some kind of encoder or a GAN type model that can model the appearance space, right? That's kind of the alternative. And generally, like something like StyleGAN, it can be a lot sharper and give you much better quality now that it has become so good. So that's one disadvantage. The other one is that sometimes the flow can completely collapse. That's what we've observed, right? Like what can happen is that there can be just like a one-to-many mapping, like it just picks up the color from one region of the image instead of sort of having like a many-to-many mapping from RGB to UV. That's another thing that we've observed, that practically you can end up with that sort of a degenerate solution. But like the advantages, as I talked about in the talk, are obviously that it's nice that if you have other annotations besides RGB on the image space, right, you can transfer those as well to UV and sort of align them across instances, which is the nice thing that you can do with the flow representation.
Thanks. There is another question in the chat from So-Young Young, who says, thank you for the great talk. About the template, is there any approach using texture templates? Is there any pattern for the UV map in one category?
So we didn't, but I know that there are concurrent works that use, for example, I know, for example, in particular for the zebra image, which is quite hard. And like for animals, if you observe, they sometimes join the legs together. And that happens a lot because in the UV space, we didn't assume, for example, like an atlas for the object. And what we found was oftentimes for objects that have these deep concavities, like, like the space between the legs of the zebra and so on, it's much helpful to have and use an atlas template, which can help to prevent kind of like these things joining. But then it's a chicken and the egg problem, right? On the one hand, you're dealing with objects that you don't understand well because they're objects in the wild, right? And so so you're trying to come up with a method which is somewhat self-supervised and doesn't assume any priors. But on the other hand, if you do have those priors, they can be helpful, especially if you lay them out as an atlas in the UV space.
Thanks, that makes sense. I don't see, there's another question. Shangzhe asks if predicting XYZ vertices from the input image with CNNs is maybe too challenging with a viewpoint deformation being entangled in this representation. Do you think that there's a better way to predict this shape?
Yeah, that's a very good point. I mean, definitely. I mean, this is, especially since we're trying to do it from a single view image, there's always this there's always this ambiguity, right? You can get both of them wrong and still have the rendered image look right. Yeah, so we, in our work, the only way that we the key points really help to break that ambiguity, right? If you have the key points, and our sort of workaround to getting the key points was using these part segments that we could get in a self-supervised way. Other than that, I mean, having a category prior also helps, as prior work has shown, right? So it's just, you got to have like some way to break it. Yeah.
Okay.
Symmetry is another one people often use. Yeah. If you have a symmetric object, that is, yeah.
Sure. Perfect. Then I don't see any further questions. Thank you again for the great talk. And I hope you join us for the upcoming panel session that is happening right now. Okay. So to start the panel, I think listening to this second part of the workshop today, a good starting point to discuss would be the choice of representation. We have heard talks on both sides of the camp. Jitendra says meshes can do anything. We've heard a lot about NeRF representations, which are very used in the community. Is there a right choice? Is there anything we should be switching to? What do you think is happening with the choice of representation? There's also the implicit representations that are maybe underused currently. Is there anyone that wants to start with this question?
I guess I can start with the hot take I guess I have is that there is no good 3D representations. I think we can keep on talking about it, but it's really task dependent. It depends on what you want to do. And sometimes meshes are great. Sometimes volumetric representations are great. And I don't really think we actually have a specific thing. I think it's better probably to go brainstorming what are the properties that we want from these things. But it's very easy to move from one representation to another. Maybe not all of them in an easily differentiable way. But if you can go back and forth, I mean, you use whatever works, I think is kind of let me start that way.
I think our experience was having worked with meshes. I mean, we're certainly limited to, at least in our case, we started with the sphere. So we were limited to the 0 genus objects, right? And so if we wanted to have things that had holes and things like that, we were not addressing that at all. So I think that's the nice thing that brings, at least the volumetric representations can bring. So that was my sort of take on it, was like the next work that I do would probably be able to generalize more, probably look more at the volumetric representations.
I mean, I think I'm perhaps in the same position as Angjoo. I don't think it's worth being religious about it, but I do like meshes. Okay, let's take an example. I mean, they work across the board, right? Okay, and so for example, you want to do human stuff. Okay, we have great models like Simple and sort of work such as Angjoo's on sort of inferring those from images, and there it's very convenient to have this mesh representation, and like the triangles of the mesh mean something. So triangle 57 is my shoulder, okay? It has a clean, simple, easy to explain semantics and all of that, right? So I think there now the genus part, I mean the unchanging topology is an annoyance, but you can deal with it, right? You can just create a point cloud remesh, I mean, so I've been in a couple of projects where we had to deal with this annoying aspect. So the mesh RCNN work with Georgia and Justin had this issue. Then the thing I talked about today had this issue. So it's a bit annoying. I'll concede that, but it can be done. I mean, So, and then the nice thing is it's like you may find English as a language is annoying, right? It has these peculiarities of pronunciation, but the fact that so many people in the world use it means that every scientist better learn English, okay? Not Esperanto, so.
I will say that the mesh is also somewhat restrictive in, like, you don't model hair in, for example, as in the SMPL or most of the, face morphable models, right? And if you're going more towards something like digital avatars or something, then you do want that level of detail as well.
Sure, yeah. No, it's the advantage of and disadvantage of a lingua franca. It's like a basic, universally understood representation,
I want to add something that for a lot of this representation, application matters as well. Like, sure, we all like organization, and for that aspect, explicit models is really nice. Everything is well organized. But when you look at some applications, like for example, if you assume a lot of the graphics application, you want to go from a model to an image, and implicit models, they make a lot of assumptions about how they are being rendered. For example, in the case of NeRF, a lot of the lightening is already embedded in it, and it's already baked into the NeRF. And there are some works, like, for example, SNERG, which is some competition to PlenOctrees that Angjoo was talking about, that they try to decouple this sort of rendering part or bake lightening from that implicit model.
I think that gives a very nice segue to the next question we have on the list, which is how do we learn to decompose all these complex appearance properties from in the wild setting, like illumination, specularity, and do we care about these in the context of shape reconstruction? Anyone want to take the question?
So again, not the full answer to it, but when we are thinking about handling specularities, etc., in the NeRF land, what we are doing is you have these K images, and that is the entirety of what you know. There is no prior about how the world works. There's no prior about structure of shapes, how cars looks, etc. And that definitely makes the problem much harder, whereas being able to incorporate some prior experience about the world in some way can regularize sort of the solutions you typically infer that, amongst these two solutions, that where the material of the car is varying arbitrarily versus there's a constant and lighting is varying, you prefer the second solution. And somehow these trials have to come in. And I don't think we are doing a very good job at that right now in all of these multi-view reconstruction approaches.
Maybe I wanted to bring the conversation also on another aspect of the 3D reconstruction in the wild. I liked in Jitendra's presentation at the beginning, starting from the baby. I think it's a good way to start thinking about it. And my question is, so in all the works we've seen, there are some form of supervision, some form of priors that we rely on. This could be maybe some knowledge of the cameras, maybe some knowledge of the masks, but also it could be something more general, like knowing some reflectance models. And more in general, one could say also just knowing the 3D projection, right? But if you think about babies, then the question is, do they have this kind of prior knowledge that, okay, a point projects on a plane through a ray and this kind? What do you think would be a reasonable set of priors that one could start from if one really wanted to be inspired by, say, how a baby learns to understand 3D, maybe not in an explicit way, maybe in an implicit way, but in some way make sense of 3D. What are your opinions and your views?
Okay, maybe I'll jump in. So I think that, I mean, in the whole learning business, there is this, we have to separate out various things. There may be some amount of learning which has happened over an evolutionary time scale. So when you are born, at that moment in your genetic code, the basic brain you have has, for example, a kind of spatial structure, right? Your retina has a 2D spatial structure, and there is a mapping which is consistent, which is relating the external world to the image on the retina. Then there is this retinotopic mapping which goes off from the retina to the visual cortex. So this kind of spatial mapping, where proximity in the image typically means proximity in the scene, is already captured in the hardware, if you will, and it might be there in the basic structure. Now, what cannot be there in the basic structure are the kinds of features which enable you to distinguish, a Honda Civic from a Honda Accord, or recognize one individual from another. So that's where the experiences of the child come in. Now, I think that our current models of learning have significant differences with respect to how a baby learns, right? So for example, the experience of a child with objects is with a very few objects, but with a very detailed experience. So it's like the opposite of the ImageNet, where you have like, okay, 1,000 categories with 1,000 examples. Okay, think about the child in the crib, and for the first year or 2 years, she might just be in her home, right? Okay, and playing with some toys, and sees mom, sees dad, sees a milk bottle, Okay, it might be like 100 objects that the child deals with. Even when the child starts to walk, it's in the couple of rooms of the house. So, but on those objects, she may have seen the object from many different points of view, and can even do active experiments, right? Pick up the object, throw it, so forth. So there is little explicit supervision, but there is a lot of this kind of experimentation and this contact with the motor system. So if I take an object and I rotate it with my hands, then I'm getting a cross calibration because my motor system is telling me something about how much the object has rotated. So I'm just, in summary, what I'm trying to say is that there is quite a rich supervision that a child's environment has, but it is different from the one that we find very easy in computer vision. But my conjecture is that over time, we are going to be moving in the direction of more natural supervision. And because I think applications such as robotics applications will demand it. I think rich environments like simulators will enable it. Egocentric data will permit it. So I can't prove it, but my vague notion is that I think we'll be moving in the more natural direction.
No other opinions from the rest of the panel?
I think I just want to add to Shenz's, he asked a two-part question of how do we do this separating lighting and shape and so on, and whether that's important. So I think I'd just like to comment on the second part of it, which is I think it is important. And I think it's important specifically for augmented reality type applications where you would want to embed 3D objects in real world scenes. And then in that scenario, you do need to be able to separate out the shape and the reflectance properties to be able to relight it properly. And I think these kinds of applications are, from what my view of if the industry, I think they're going to come very soon. They're going to be very real. So it's very exciting.
There is a follow-up question from Vedaldi. So you could say
I can
that.
ask actually, but if you want.
Oh, sure. Go ahead.
Yeah, Jitendra, you were saying about kids becoming expert of a small number of objects, right? So this is something I also thought about a while back. And one of the questions I had back then is, okay, if I learn now for 2 years 100 objects, how come I am able then to generalize to everything else? So if I train a machine on 100 objects only, then it's not going to do a very good job on all the rest, right? So it seems that whatever the kid is, the children are learning is highly generalizable, which is not something you would expect of a typical deep network, for example. Not as much anyway.
Yeah, so I think that you're correct. I think our current networks do not squeeze as much information out of the multi-views of 100 objects that then a child does. I think that's correct. And to me, that's like one of the mysteries and one of the great research problems. Because I think what we have is take a canonical example, okay? So the child has this experience with 100 objects, right? Which is very intense. Then the child goes to the zoo. And then, okay, the parent says, this is a zebra. So now you got like one side view of one zebra. Okay, and that's enough, right?
Yeah, that's right.
After that, you can guess how that zebra looks like from different viewpoints and so on. Okay, I mean, I've done these experiments on my own child when he was 1 and 2 and so forth, and it was amazing. I mean, I tried to, actually take notes and observe this carefully. So I think our systems can't do it. Our current machine learning systems can't do it. And to me, this is probably reflective of the fact that the architecture hasn't captured the 3D inductive bias enough. Because I think 3D is worth building an inductive bias on, because, I mean, the 3D world is the 3D world, and that's just true. It's not like some proposal that let's first detect edges. I mean, that's a kind of thing we have thrown out in the deep learning era. But the 3D-ness of the world, or in fact, the 4D-ness of the world, is something completely to build in as an inductive bias. And what we really need to learn is how do we predict these views in a sort of in a good way. And I think our architectures are not quite there. That's at least my belief.
So maybe to add to that, I mean, we were discussing this in context of 3D and multi-view, but I'm not sure if this is a thing specific to 3D or just an issue with the machine learning tools we use in general, that, kids, even if you're thinking of grasping, they can grasp new objects, even though they have little experience with grasping few. You can navigate in new scenes, even though you've only navigated in a very small number of houses as you're growing up, or new cities, etc. And it's more just that the machine learning tools we use, I think to quote Alyosha, requires so much data that the problem becomes like an interpolation problem. And it's sort of a mystery on how we get to more general machine learning tools that get more juice out from very little data. As in, I agree with everything, but I'm not sure it's a very 3D specific issue, or we need just better ways of learning in general.
Yeah, I mean, I agree. I mean, I somehow think that 3D should be more approachable. Okay, I mean, it's there in other settings, like it may be there in language and this and that, but I feel that, see, I'm making the following analogy. Vision has historically been the part of the brain which has been the most approachable compared to, say, something like language. I mean, motor control is also approachable, okay? Because we kind of understand the first few stages of processing in the visual pathway quite well. So I would conjecture that the area where we might be able to tackle this problem most successfully, or what might be the most, plausible place to attack first might be vision and 3D, though it may be a universal issue.
Yeah, I'd like to add, I agree with all of these directions. I'd like to add 2 points. One is that I think it's also like a matter of the training paradigm in which do things, where there's like a fixed set of data sets. And then from then on, we close our eyes and like never look at the world again. And I think it needs to be like, you need to have some kind of feedback system where, you know, in reality, you actually get multiple views. And so you update your model and like you continually learn. And I think that kind of direction would be really cool to see in 3D. But another thing is that even if you get to see the 100 objects, I really want to emphasize that the lighting and the environment is very complex in the real world. And so the baby is looking at 100 objects maybe, but they get to look at it in like all sorts of lighting from like the morning, night to like fluorescent and all of these things. And it's actually quite diverse. I think it's a really good learning signal. And another thing that I feel is that maybe it doesn't, I can't really express it, but I feel like the reusable pieces, 3D priors, are actually going to be small pieces. And for those things, maybe that's a lot of signal. Either way, I still think you need some kind of online learning, but I'm saying it's a lot for the baby get to see a lot.
Maybe to add a little bit more to this point. So I think that the work we're referring to is the one of Linda Smith, right? Where basically, and she notices that from all these videos that basically the babies learn mostly from very few objects. Then the question is, why is it better to learn from very few, but very, very much in detail, like with very high accuracy so that they can recognize a bottle, although it's mostly occluded, rather than from a variety of objects, right? That's, I think, a little bit maybe one point of the question. Why does the first one generalize seem to be favored by evolution? Maybe.
Well, we may not have a choice, right? I mean, today, yes, we can go to a Walmart and have thousands of objects. But imagine any animal's ecological niche. They're in like some part of space. They're in their forest or in their tree or whatever. And in general, it's your life is local, right? Even humans as hunter-gatherers, they would be in like some place, or if they lived in a village, they were like, I mean, the idea that you can roam around the globe, I mean, this is like a very 20th century thing, right? So you in general had a very local context, a local cultural context, a local context of vegetation, local context of flora and fauna. So I don't think there was a choice. Now, why is it that computer vision has found it easy to use knowledge like this ImageNet thing, and yeah, I mean, Shubham referred to this line that maybe all we are doing is interpolation. In fact, there is some amazing work from some machine learning people, Ben Recht and co, which show that networks can memorize basically anything. So you could take a set of 1,000 digits, arbitrarily label, I mean, and just give them random labels. So instead of 0, 1 to 9, you can label a 6, a 3, or whatever, any number, totally by random assignment. You label all those 1,000 digits, and now you can train your network, and the neural network, you can get the training loss to go to 0. So it will overfit to this data set. So there is no generalization here. So all that it is doing is memorizing those 1,000 examples. So our networks have amazing, they memorize this, which is what we are exploiting, which must mean that there is some hidden secret sauce somewhere, which we should be able to incorporate in our network, and then you'll win.
Maybe just to add to that, it's true that you can force a network to learn anything you like, but it doesn't mean that the network really likes it, right? So it would typically actually not do that, probably, right? So otherwise nothing would work. So you can make it do it. Maybe you can make it do that, but you really need to press it, I think. It's a bit like when we did a deep image prior, which we could fit random noise with a generator network, but that was very hard. So it was much easier to fit a natural image. So I think, it's true that the network can do anything, but not necessarily something that is not necessarily something which would be preferred if another solution could be found.
No, fair enough. Look, I think that the search for network architectures is not over yet. Look, for so many years, we just went with ConvNets, right? Okay. There were people who didn't like ConvNets, like Jeff Hinton, right? He wants capsules because he thinks that the operation of pooling is losing some vital information. Fine. Okay. Those were difficult to make work. Okay. Then we got to transformers like maybe 3 years ago or something in language, and then last year in vision. And this is a different architecture, right? It's completely ignoring spatial invariance of these patches. It's doing these long range connections, and we can use it for all our things. So why should we assume? So I'm essentially saying that earlier I really think we might have next year, we might have something quite new and revolutionary. So the space of architectures is, I don't think, exhausted. And they might, like, to me, like transformer, like ConvNets seem to capture low level structure, but at higher level, they didn't seem to make sense. And it seems to me that transformers do something more natural for more high level structure, but why nothing captures the 3D nature of the world? Who knows? I mean, I think we should not, I think people will come up with new things. Who knows? So I'm an optimist.
Good.
I want to make a connection back to the question I asked earlier. Like, oftentimes when we want to predict shape, like 3D shapes, like throw in the 2D image into CNN and predict all the vertices in XYZ coordinates, which are like far too different from the input space, which are pixels. And it completely ignores the 3D projection in this encoding process. I do really wonder, like, if there's any way of incorporating these knowledge about 3D or other like properties in this prediction process.
You mean more than just? I mean, we are doing it, right, with the cameras and perspective projection and all the rest. You mean more than that? I mean, so obviously the brain knows about triangulation, right?
The prediction model, like, you cannot just like throw in a 2D image into a CNN and predict everything, right? Or do you think like that's not a problem?
Yeah, no. I mean, my belief is that the reason why that 2D image evokes a 3D is that you have learned across modalities. So here is this object in front of me, right? Okay, so right now I'm seeing it with 2 eyes. So it has got a certain pattern of disparity associated with it. Okay, now what I do is I shut 1 eye. Okay, but I have this mental association of this 2D pattern of pixels with a certain pattern of disparities. That pattern of disparities evokes a certain depth. So therefore, just the pixels evokes that pattern of depth. So A is associated with B, and then B is associated with C, and then A goes with C. Something like that. I think that's a fairly reasonable thing to assume in a learning system, right? And it's more than that. It's also because, I mean, humans are also very adaptable. That's one of the impressive things. So there is this classic experiments where you have your 2 eyes, and now in front of one of your eyes, I'll put a prism. So what happens is all the rays are like deviated by 10 degrees. Okay. So now if I try to pick up an object, I'm in trouble, right? Because my stereo system has got messed up. So I keep trying. Okay. After 10 minutes, I will basically succeed in grasping. And now my brain has quickly got rewired. So this hand-eye coordination has been adaptively reconfigured in like 10 minutes of action, but it was active interaction. So there seem to be a whole lot of these features where there is this geometry built in, these constraints built in, and yet they seem to be very, very adaptable and plastic and so forth.
Yeah, I think like that totally makes sense.
So I think another point that we have slightly touched on that would be interesting to talk about that follows out of the previous discussion is what kind of data should we be working on? So we now talked about that we should be learning like the children. So do we strap cameras to babies and record videos and train on that? Or do we go towards the interaction aspect and use simulators to actually learn from the interaction with objects? Or should we just continue what we're doing now and use, I don't know, image and video data sets across hundreds or thousands of categories and try to generalize from there?
I might be a bit biased, but I think it really depends on your application. Like if you are trying to make AGI from babies to young adults, sure, you should put a camera on a baby. Don't ask Google to do it. It has a lot of privacy issues for the babies. But if you, for example, care about product that people sell on the web, that's a different application and it would require different data. So if you ask different person, you might get different answers for your question.
Okay, I don't mind what you use so long as you stop using ShapeNet. I think ShapeNet should be retired. It's outlived its usefulness. But I think all the answers you suggested are good. Like I like simulators, I like egocentric data. I think multiple views is the most natural. Okay, so anything, and I think we can get some. I mean, from Berkeley, we are releasing this something we did in collaboration with Amazon, which is like lots of images of and CAD models of Amazon products. So that will be like more like CAD models. So honestly, anything you can get. We are really quite limited by data. I think the 3D space, we are starving for data. I think why is 3D not why is the field not bigger than what it is? I think Shalini referred to the fact that like upcoming applications like AR, VR will really emphasize the need for 3D. Okay, but why are the number of papers in this area and the progress in this area would really benefit from having tons of data. And for 5 years, we wrote papers just on ShapeNet. Okay, between like 2015 to 2020, it was all ShapeNet. Okay, well, okay, fine, retire it. You know.
I completely agree, and I think that we need 3D, like videos, maybe multi-view videos, but I think we actually also need good 3D data, not like with holes and good quality, which can capture a lot of the photogrammetry, scans and things like that. I think that will really help to progress the field further, because at the end of the day, we're estimating all this 3D, but then how good are we doing, right? Like, are they good enough for a real world application? Like, is there detail in it? We don't know. And the only way we can know how well we're doing is if we have some good ground truth to compare against. I think there was this spurt when we had Connect and there was a lot of 3D data of research in 3D, but then now that's kind of all sort of not as, that's not as prominent anymore.
Yeah, I want to raise a point though that I think it should be images in the wild, and I think that's very important. And the moment you go to in the wild, it's much harder to get the training data, but we'll always figure out how to do the evaluation. Like Shubham was proposing one way. Yeah, I think it's very important that not only does it has to be data, not ShapeNet, but ShapeNet has multiple things, right? It's synthetic, but also the problem is that things in the world don't exist in a vacuum of white background, and so we can't just go back to a rolling object on a thing with a rolling table with a green screen background. That's also not so great either, I think.
Yeah, I mean, maybe we might hit lucky, right? So So all these new generations of phones, they have quite, they have the ability to capture 3D.
True.
So suppose we get into the setup where, look, think about the basic setup for images. Back in the late 1990s, early 2000s, what happened was, everybody started to own a phone with a camera. Then they started to upload those pictures. And then in those days, we didn't care so much about privacy and so forth. So people started downloading those pictures and making data sets, right? And that's the basis of data sets like ImageNet and so forth, right? Okay. Now imagine that if everybody was uploading 3D pictures, at the same rate at which people were doing for 2D pictures, maybe we would find a way to exploit it. Now, I think the difference is the sort of the legal and socio-cultural context has changed from 10 years ago. So I think the way people could just download images and annotate them and make a data set, I think that era is gone in my view. Okay, so we'll need to be more careful and particular. But that could be the source ultimately. That the beauty of that is that it's truly crowdsourced. You get huge variety, because if I collect any one person collects data, it lands up being from their own sort of niche, right? Whereas if everybody is collecting, if you've got like 1 billion people in the world uploading data, it's going to be much more varied.
Yeah, we need a framework to buy this data though, or to commission this data. So we have done this in the Code3D data sets where we paid people to capture images of objects. And of course, once people have these 3D phones in their hands, we could just ask them to capture 3D videos or 3D pictures.
Yeah.
So, but we can get probably hundreds of thousands of images, maybe 1 million, but not 1 billion like that.
Yeah, but I think that's a promising direction, right? Yeah.
It's interesting, Angjoo, that you say that in the real world there are not the white background scenarios, but basically all the methods we heard about today, or that are state of the art, need mask supervision, which basically directly translates into having the white background during training. So that's one of the very interesting things that basically is consistent across all methods, that we need this supervision of the shape of the object, at least in 2D.
But the issue with relying on user-generated content in these instances, it creates two bias. One is you're assuming that users are taking them with their phone, and then you're limited to the locations where the phone is and how the phone is viewing the object and so on. For example, think under the table. Like if I ask any one of you what does under a dining table looks like, you all know what it looks like. But if you rely on the internet images to understand or learn that might not exist. Number two, you also would be relying on countries where people have a lot of phones, and two, they have a really good internet access to upload these phones. For example, think